All right, people. I believe everybody is doing great, nice, and absolutely fine. So, what's up? What's up, people? Good morning, good morning, good morning. Okay. How is everything going? Let me know in the chats, okay? Burn the chat box with the fire emojis, everybody out there. And make sure you like this particular session. I want everybody out there to like this particular session because marking the attendance is mandatory, okay? And let the people join. We will start accordingly. Let me know if I am perfectly audible and visible. Okay. So this is basically the part second of the complete physics marathon. Okay. We will be finishing the rest of the chapters today. As promised, I'll be starting from the scratch and I'll be starting from the optics chapter. Okay. A lot of students out there were saying, sir, when will you take the optics? When will you teach optics on YouTube? Today is the time. Okay. Every single topic will be discussed. All the problem patterns will be discussed. So make sure you like this particular session. Hit the like button. Everybody out there. Okay. Okay. Great, 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 great. So how is everything going? Yo, 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 yo. Okay. So I want you guys to basically stick to this particular session till the end. It's not like right now there are so many people watching, okay? Then after 2 or 3 chapters, they leave. No, no, no. We have to complete all the chapters. And let me just tell you, we will be completing approximately 45 to 50 marks in this particular session, okay? 7 chapters, 6 chapters we have to cover in this one. Total of 6 chapters will be covering in this one. Complete modern physics, semiconductors, complete optics. Okay. All the chapters which belong to your part 2, so will be completed in this particular session. Okay. So make sure you like this particular session. That is very much mandatory. All the people out there and show some love, show some fire in the chats. Everybody out there. Okay. Okay, great, 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 great. So for next few days, we are actually traveling to Bangalore, okay? Tomorrow we are going to Bangalore, the complete NEET English team. We have the big mega event over there. That's the reason there are no classes scheduled on the channel for next few days. That's the reason. Okay. If you want to come over there in that particular session, you can basically join. Even you can watch that live. The link is in the description. Okay, so guys, the first thing is I want you guys to like this particular session because that's mandatory, okay? Then only I'm starting the session. So let me just tell you over here, my dear friends, in this particular marathon, we will have to cover these chapters, okay? We are starting with the ray optics, okay? And in this ray optics, we'll be covering all the concepts and we will have to cover the optical instruments also. Ray optics plus optical instruments, both the chapters, both the portions will be covered in this particular session. Okay. 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 Great, 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 great. Just a second, people. Okay. And once we are done with this particular chapter, then we will move on to the wave optics chapter. Okay. This will be the second chapter that we'll have to cover over here. And once we are done with the wave optics, then we'll move on to the dual nature of matter and radiations. Over here, we'll be discussing complete photoelectric effect as well as the de Broglie waves, all the concepts. Okay. And afterwards, we'll be moving on to the chapter that is atoms. We'll be studying different models of the atom. Okay. And all the problem patterns out there. And then once we are done with the atoms, we'll be moving on to the nuclei. Okay, all the concepts of the nuclei, which are important. And then afterwards, we say semiconductors, and we will be talking about the logic gates also. Okay, logic gates also. We will not leave any single topic. Every single thing will be covered in this particular session. Okay. Okay. Now, my dear people, listen to me very carefully. We are starting the chapter 1, that is ray optics. And in this particular chapter, listen to me very carefully. In this particular chapter, we say it is made up of 4 different portions. Okay. The first one is we say reflection, then we say refraction, then we say refraction, then we say dispersion, okay, and then we say optical instruments. Optical instruments. So we'll be covering all the 4 portions over here in this particular one shot, okay, in this particular marathon. So first of all, we'll have to start with the concept that is a reflection, okay, reflection of light. Listen to me very carefully. As I have told you before also, I'll have to cover the 6 chapters with all the concepts and all the problems. So I will be to the point, the amount of theory which you actually need in order to solve the question, I'll be giving you that much only, okay? If I tell you at some point, remember this point as it is, you have to remember that. Don't ask me for the logic, sir, where does this come from? Where does that come from? Then, if you want those logics, then already big marathons for every single chapter are available on this channel only, which I have done previously. You can watch those. But right now, whatever I say, you have to remember all those things and keep those things in your mind. Okay, that's it. Now, the first topic that we need to exactly discuss over here. The first topic that we need to discuss over here. Just a second. Okay. Now see. Yeah. Okay. Now see, the first topic that we need to discuss in this particular case is, we say, sir, that is reflection. Okay. Reflection of light. What does this reflection of light actually mean? Listen to me very carefully. What does the reflection mean? Let's suppose I have a ball in my hand. Okay, I'll take a ball and I'll throw that ball on this particular surface. What will happen? Ball will be thrown on the surface and then afterwards it will be reflected. When the ball hits the surface, after hitting, it will be reflected. After hitting, it will be reflected from the surface. That is reflection. Here we have to discuss a reflection of light. Okay, so light is also reflected in the same way. Let me just tell you, my dear friends, if we say we have got a light ray over here, we have got, this is a surface, okay, and on to this particular surface there is a light ray which is falling something like this, okay, and in this particular chapter we consider light as a ray. In case of ray optics, we consider light as a ray, okay? Like in modern physics, I have told you, we consider light as we say, sir, small photons, particles. But here we consider the light as a ray, okay? If I say, sir, there is a light source over here. From the light source, the light is basically falling. It is incident onto this surface. This is a surface, okay? This is a surface. Or we say reflecting surface. So light rays falling onto this surface, we say it gets reflected something like this. This light ray which falls on the surface is what we call the incident ray, and the light which is reflected is what we call the reflected ray. This is what we call the reflected ray. Now, my dear friends, we'll take a line and which is perpendicular onto the surface. This red color line is perpendicular onto the surface. Sir, this is what we call the normal. Okay. So normal is basically that line which is perpendicular onto the surface. Okay. Now, my dear friends, the angle between incident ray, the angle between this incident ray and this normal, this is what we call angle of incidence, and we represent it with I. And the angle between normal and the reflected ray, we say this is what we call the angle of reflection. We represent it with R. Okay. And my dear friends, we call this angle as alpha. What is this angle? This angle is the angle between reflecting surface and normal. Reflecting surface and incident ray. My dear friends, this is the angle which is the angle between reflected ray and reflecting surface. I hope you got these points. Now listen to me very carefully. We say, sir, when it comes to the reflection, this is the phenomena of reflection. When light falls onto the surface and it gets reflected, this is what we call the reflection. This is the angle of incidence. This is the angle of reflection. Now, there are two laws of reflection that everybody of you must be knowing. So what is the first law? Sir, we have observed, we have seen this experimentally. This angle of incidence is coming out to be equal to the angle of reflection. This is the first law. Angle of incidence is coming out to be equal to angle of reflection. The second law is the incident ray means this one. The reflected ray means this one. And the normal and this one, we say all lie in the same plane, all lie in the same plane, all lie in the same plane. Like over here, this is the plane, this is the incident ray, this is the reflected ray, and this is the normal. All are lying on the same plane. So this is the second law of reflection. First is we say angle of incidence is equal to angle of reflection. Second is this one. This is what you guys are supposed to remember in, we say, reflection of light. Okay. Okay, now my dear friends, listen to me very carefully. Listen to me very carefully. What is the first thing that we need to understand in this particular topic? That is deviation by plane mirror. Sir, what does plane mirrors mean? Let me just tell you one thing. Sir, in our rooms, okay, in your house, in your room, so you might have seen a mirror, okay? Like this is a mirror, plane mirror. This is a plane mirror. Sir, what is the work of this plane mirror? Sir, when we have to make the hairstyle, we come in front of the mirror. That's it. So that's what we call the plane mirror. If you check that plane mirror is polished from the back side, okay, then only you are able to see your image inside that particular mirror. So we say this is the polished surface and this is the reflecting surface. This is the polished surface and this is the reflecting surface. Okay, this one. If you have to look yourself into the mirror, you have to sit over here and image will be formed inside the mirror. Okay. Now tell me one thing, my dear friends. Let's suppose we have got this mirror over here, or you say reflecting surface, or you say plane mirror, one and the same thing. My dear friends, if I say the incident light ray is falling onto this particular mirror, what will happen to this incident ray? We say it will get reflected something like this. So that's why we call it the reflected ray. My dear friends, let's suppose I say if there was no mirror, if there was no reflecting surface present over here. Imagine there is no reflecting surface present over here. What will you say? Sir, in that case, this incident ray would go simply along this straight path. It would have gone simply along the straight path. But because of this surface, it is going something like this. Now tell me, can I say, sir, this light ray got deviated? How much? This much. This much is the deviation. And my dear friends, if somebody asks you, what is the value of this deviation? You will simply say, sir, the value of this deviation, this is what we call the deviation. That is 180 minus 2 theta. 180 minus 2 theta. Okay. This is what we call the deviation. This is what we call the deviation. Okay, so how much incident ray got deviated from its actual path, from its original path? That is this much. That is how you are supposed to find it, like this. Let's move on to the next concept. That is this much. Listen to me very carefully, my dear friends. We say over here, deviation by two plane mirrors. Now, let's suppose we have got one plane mirror, something like this. This is the polished surface. And we have got another plane mirror, something like this. Okay, this is the polished surface from this side. Okay. Now see, if I say incident ray is falling onto this mirror, incident ray is falling onto mirror 1. This is the mirror 1. And this one is, we have got the mirror 2 over here. Listen to me very carefully. We say incident ray is falling onto this mirror. And we say whenever the incident ray falls onto the mirror, it gets reflected. So we say it gets reflected and falls onto the mirror 2. After first reflection, it falls onto the mirror 2. Then, my dear friends, we say it again gets reflected something like this from the mirror 2. This is the initial ray. Okay, this is the initial ray. Then it gets reflected and falls onto the mirror 2. Once again, it gets reflected, from the mirror to something like this. Can I say this one will be the final ray? This is the final ray. And this is the original ray. This one is the original ray. Sir, the angle between the original ray and final ray, that's what we call the deviation. The angle between original ray and final ray is what we call the deviation. And in this case, we say deviation is 360 minus 2 theta, where theta is the angle between the two mirrors. Keep this thing in your mind, my dear friends. Keep this thing in your mind. Where theta is the angle between the two mirrors. Guys, in this particular case, this was the original ray. This was the path of original ray. But this is, we say, the reflected ray, or we say the final ray. Now, my dear friends, in this particular case, we say angle between the original ray and the final ray is what we call the deviation. Same is the concept over here. Angle between the original ray and the final ray is what we call the deviation. So here we say deviation is 360 minus 2 theta. Let me know in the chats, is this crystalline clear? Let me know in the chats, is this crystalline clear? Everybody out there. Let me know in the chats if this is crystalline clear. All the people out there. Everybody, guys, if you have not liked the session yet, I want you guys to like this particular session as soon as possible, because liking the session is mandatory. Everybody out there. Okay. Now, let's talk about something which is also important. That is, we say object. That is object. Sir, what does this object actually mean? What does this object actually mean? Listen to me very carefully. Listen to me very carefully. Let's suppose, my dear friends, let's suppose if I say over here, I have got a plane mirror. Okay. I have got a plane mirror. So this is polished from the back side. And in front of this plane mirror, I am placing someone. Can you tell me, sir, what's gonna happen? You'll say, sir, if you place someone in front of this object, its image will be formed inside the mirror. This is what we call the object. And this is what we call the image. Remember it directly. In front of the mirror, we are placing the object, and behind the mirror, image is being formed over here in this particular case. Okay. Now, guys, listen to me very carefully. Sir, technically, what is the physics definition of object? We say, when it comes to the physics definition of the object, we say it is defined as the point of intersection of incident rays. Technically, we have to define the object is, sir, it is that point at which incident rays meet, We say, sir, if this is an object over here, we say incident rays will leave from this particular object, okay? And they fall onto the surface. If I say I have got mirror in front of me, incident rays will leave from object, and that will fall onto the mirror, and they get reflected. Okay, that's why we say it is the point of intersection of incident rays. Guys, if I say at some point you have to remember this, remember it, okay? Because once we keep on moving forward, every confusion will be cleared. Right now, I'm telling you, sir, object is where incident rays meet. After 15 to 20 minutes, you will get the feel of this particular point also. Okay. Now see, if I say this object is that point at which incident rays meet. Okay. Now, guys, listen to me very, very, very carefully. Come over here. I say, sir, if this is an object, if this is the object over here, I'll write this as object. This may be some person, something else. Okay. We say, sir, incident rays will leave from this particular object and fall onto the mirror, and they get reflected. So they get reflected something like this. My dear friends, if they get reflected something like this, listen to me very carefully. We say, if you extend this, the point where this reflected ray and this reflected ray meet is what we call the image. So how image is formed? The logic behind this is, if you have the mirror in front of you, incident rays will leave from the object. After reflection, if we meet those, if the two reflected rays will meet at some point, at that point image will be formed. So I can say it is the point of intersection of reflected rays. It is the point of intersection of reflected rays. The point where reflected rays meet, image will be formed. Okay, okay. My dear friends, let's suppose these are the incident rays. These are the incident rays. Okay. Now after reflection, they are meeting at this point. After reflection, they are meeting at this point. So we say this is what we call the image. So the point where reflected rays meet is what we call the image. The point where incident rays meet is what we call the object. Come over here once again. Come over here once again. Guys, see, this is the object I'm saying over here. Actually, in reality, the two incident rays are in reality meeting over here. Okay. So that's why we call it the real object. Real object is that object at which incident rays actually meet. See, let's suppose if the incident rays are something like this. Incident rays are something like this. My dear friends, after reflection, they go something like this. Okay. But if we extend these incident rays, they appear to meet at this point. I'll write this point over here. We say incident rays appear to meet at X. So if incident rays appear to meet at X, but they are not actually meeting, here the incident rays are meeting. In this case, incident rays appear to meet. It looks like they will meet, but they are not meeting. So this is what we call the virtual object. Okay, similarly, my dear friends, come over here. If I say in this particular case, sir, this is the object, which is what we call the real object. So the light ray will leave from the real object. After reflection, it will be reflected something like this. This light ray will be reflected something like this. If you extend this, the point where they meet is what we call the image. This reflected ray is appearing to meet at this point. They are not meeting actually. So we say this is what we call the virtual image. If the reflected rays appear to meet at some point, that's what we call the virtual image. Now come over here. What is this real image? Let's suppose incident ray comes something like this and it goes. This is after reflection. This incident ray after reflection, they are meeting over here. So reflected rays, these are the reflected rays in this case. These are the reflected rays. So reflected rays are actually meeting at this point. So we say this is what we call real image. This is what we call real image. Tell me in the chats, is this clear? Is this clear? Real object, real image. Virtual object, virtual image. Let me know in the chats. Okay. Let me know in the chats. Okay. Come over here. Let's suppose, my dear friends, I have got a plane mirror over here. In front of the plane mirror, I am placing an object. Okay. Now we know, sir, if you are placing an object at distance d in front of the mirror, sir, at distance d itself, its image will be formed. At distance d itself, its image will be formed behind the mirror. Okay. So what is happening actually in this case? Listen to me very carefully. We say, sir, incident ray is leaving from the object and it gets reflected something like this. Another incident ray is leaving from the object, it gets reflected something like this. Now, if we extend this reflected ray, okay, and it meets over here. If we extend this reflected ray, it meets over here. So the point where reflected rays meet, image will be formed. So can I say in this particular case, sir, this is what we call the real object and this is what we call the virtual image. Why? Because reflected rays appear to meet over here. They are not actually meeting. They are going something like this. Okay. And in this case, we say incident rays are actually meeting. Okay. So that's why we say this is the real object and we say this is the virtual object over here. Now, my dear friends, come over here. Now there is a question. Listen to me very carefully. I'll make you understand this particular question. What is this? See, let's suppose I have got a plane mirror over here. This is the plane mirror. And in front of the plane mirror, I have placed an object. Okay. My dear friends, listen to me very, very, very carefully. We say, sir, behind this plane mirror, its image will be formed. Yes. Now, what is happening actually? We say incident ray is leaving, okay, from this object. Let's suppose there are so many rays which are leaving and falling onto this one. We'll take the lowest ray, okay, which comes from the foot of the object. So we say it falls onto the mirror, okay. And we'll take one more ray, okay, which comes from the top head of the object, okay. Now, my dear friends, it gets reflected something like this. Tell me one thing. If we extend these reflected rays, if we extend this reflected ray, can we say the point where these reflected rays meet, image will be formed at that point? 110%. We say image will be formed at that point. So, my dear friends, if the incident ray is leaving from this point and it gets reflected something like this, so I can write in this particular case, this is what we call the incident ray, and this is what we call the reflected ray. Similarly, this is incident ray, this is reflected ray. So the point where they are meeting, so this is what we call the image over here. Okay. Now, guys, listen to me very carefully. If I say, sir, the highest reflected ray is this, okay? This is the highest reflected ray. And this is the lowest reflected ray. Yes or no? So, my dear friends, we can say all the reflected rays are crossing through this part of the mirror only. See, clearly over here, no reflected ray is passing through this part, no reflected ray is passing through this part. But all the reflected rays which come from the image are passing through this part only. So, my dear friends, we have to find how much is the size of the mirror. So, what is this question? Find the minimum size of the plane mirror. Find the minimum size of the plane mirror required to see the full image. How much mirror do we actually need in order to see the full image? You say, sir, only this much, because all the reflected rays are crossing through this part only. And directly you will be remembering, sir, this will be x is equal to h by 2. And what is h? H is basically the height of the object. Okay. So if you have got a h height object over here, and if I ask you, tell me what will be the size of mirror required so that complete image of this object should be made over here, you'll say, sir, x is equal to h by 2. Directly, like over here, the question on the screen. In this question, it is saying that a man of 180 centimeter height, means height of object in this case is 180 centimeters. Okay. Stands in front of a plane mirror. I have got a plane mirror over here. Okay. And in front of the plane mirror, we have got an object which is having the height of 180 centimeters. Okay. His eyes are at the height of 170 centimeter. This is the height of the person. This is the height of the eyes. Okay. From the floor. Then the minimum length of the plane mirror for him required to see the full image. Here we have to see what should be the minimum size of the plane mirror required to see the full image. Recently we calculated, sir, x is equal to h divided by 2. Means height of the object. How much is the height of the object? 180. You don't have to take 170 because height of the object is from the top to bottom. So that is 180 divided by 2. That is 90 centimeters over here. So 90 centimeters of the mirror is required to see the full image of the object. I hope this is clear. Let me know in the chats, guys. If you have not liked the session, like it as soon as possible, because that is mandatory. Okay. Now this is something which is important. Okay. See. Before this, I want to tell you something. Let's suppose I have got a mirror over here. This is the mirror. Okay. This is the mirror. in front of the mirror, let's suppose I'm placing a box. This is the box, or we say, sir, this is the object. We know, sir, its image will be formed inside this mirror. Okay. If this is at distance d, we say, sir, image will be also at the distance d. Now, guys, listen to me very carefully. There is a person over here. There is a person over here standing. Okay. We say, sir, this person is, guys, the case is like I have the mirror in front of me, and in front of the mirror, I'm placing some box, and I'm okay. I'm also over here. I'm also over here. In front of the mirror, I'm placing the box, and then I am behind the box. Okay. So I'll consider myself right now observer. Sir, what does observer mean? Observer means that person which is looking at the image. I'm saying, sir, I have got the mirror in front of me, and in front of the mirror, I'm placing the box. Now, if I have to see its image, what will I do? I'll look into the mirror. So means I am the observer. I am looking into the image of this particular object. Sir, my image will be also formed in the mirror. Yes, my image will be also formed in the mirror. But we are analyzing the object. So what will happen in this case? The incident ray will leave from this particular object, and it gets reflected and falls into the eyes of the observer. Then only observer is able to see this one. Guys, this is something which is important. I say, if observer has to see the image of this object, what will happen? We say incident ray will leave, that gets reflected and falls into the eyes of the observer. One more ray will leave, and it falls into the eyes of the observer. So this part of the mirror is required to see the full image. And who is seeing the full image? Observer is seeing the full image in this particular case. I hope you got it. Then only I am able to see when the light rays falls into my eyes, then only I am able to see this particular object over here. Same is the case in this one. You'll get all the confusions clear from this particular question. See. I have got a mirror over here, and in front of the mirror, I am having a person. Okay, that is a child. This is a child, son. And behind the son, we have his father. The height of the father is h2. The height of the son is h1. And the son is placed at the distance of d1 from the mirror. Father is placed at a distance of d2 from the mirror. Now, my dear friends, in the question it says that if the child wants to see the complete image of his father, guys, child wants to see the complete image of his father. Means in this particular case, we say child is the observer. This is the observer, and this is the object. If I say child is looking at the image of the father, means child is observer in this case. So, my dear friends, if child is observer, so we say, sir, this is the object, and we have to make the image of the object. So we say, if this is the object, its image will be this one. If this is having the height h2, its image will be also having the same height. It's like you are in front of the mirror. The height you are having same height will be having your image also. Okay. So my dear friends, this is h2. Okay. Now this is also placed at the distance d2, because this object is placed at the distance d2 from the mirror. Now listen to me very carefully. In this case, we have to find the minimum size of the mirror required. To see the full image. See, what will happen in this case? If this is the object, the incident ray will leave from the object, and after reflection, it gets reflected and falls into the eyes of the observer. One more light ray will leave from the top of the object, and it falls into the eyes of the observer. Now, can you tell me, sir, this is the reflected ray, and this is the reflected ray. If we extend this reflected ray, so the point where they meet, image will be formed. And can I say all the rays will be passing through this part of the mirror only? And in this case, we have to say what is the length of this part of the mirror, how much
is the length of this part of the mirror. Directly, you will have to remember in this particular case, my dear friends, we say this will be the length of the mirror. That is a D1 H2. Sir, what is a D1? D1 is the position where this observer is placed. H2 is the height of this object divided by D1 plus D2. I hope this is clear. I hope this is clear. Let me show you one more question on the same pattern. One more question on the same pattern. Sir, if father wants to see the sun's image, see, in this case, can I say, sir, if father wants to see the sun's image, means father is observer and this is object. Now, what will happen in this particular case? We say, sir, incident rays leave from the object. See, incident ray is leaving from the object and falls into the eyes of the observer. Another incident ray will leave from the object from its foot and it will fall into the eyes of the observer. So if we extend this, see, its image will be formed here. So if this is the object of height h1, image will be of the height h1. And this part of the mirror is required to see the full image. This part of the mirror is required to see the full image. So can I say in this particular case, this x will be over here, d2 h1 upon d1 plus d2 upon d1 plus d2. Is that clear? Is that clear? Let's move on to the next one. Let's move on to this one. Come. Hey guys, is this clear? I hope I am giving you the exact feel of this particular chapter. Huh? Let me know. And if you have not liked the session, like it as soon as possible, because liking the session is mandatory. And make it 1000 right now. It is 725 only. Make the like count 1000 right now. Right now. Everybody out there. Okay. Now, listen to me very, very, very carefully. Relation between velocity of object and image. Guys, it is simple. Let's suppose if you have got a mirror over here, okay? And in front of the mirror, you have an object which is moving with some velocity v, okay? So its image will be formed over here. And I am asking you to tell me what is the velocity of the image. You will simply say, sir, velocity of the image will be 2 times of Vm. Sir, what is Vm? Vm is, we say velocity. We say velocity of mirror. In some cases, maybe let's suppose mirror is also moving with some velocity. So that's why we are saying 2 times velocity of mirror minus velocity of object. If you have got a mirror over here, mirror is also having some velocity and object is also having some velocity. You have to find the velocity of the image. You have to find the velocity of the image. That will be 2 times Vm minus V naught. Sir, in 99% of our cases in our syllabus, we say mirror will be at rest. Okay. We say in 99% cases, we say velocity of mirror will be 0. If velocity of mirror in 99% cases is 0, so can I say this term will be 0? So we can say velocity of image in that case will be minus velocity of object. As simple as that, as simple as that, as simple as that. What does that mean? That means if this mirror is at rest, if this is moving with, let's suppose 10 meter per second, okay, towards right, we say image will be also moving with 10 meter per second towards left. So that's why we call it minus 10. It's like you have got a mirror in front of you. You are walking towards the mirror. You will find that image is walking also towards the mirror that is moving towards the left. That's why its image is negative. Okay. Now, let's suppose we have got this particular question on the screen. I want you guys to basically answer this particular question over here. A man runs towards a stationary mirror. We have got a stationary mirror over here. Let's suppose we have got this stationary mirror over here. Okay. We have got this stationary mirror over here. And a man is basically running towards the stationary mirror. Okay. With a velocity of 15 meter per second. Okay. This is velocity of man. Okay. With a velocity of 15 meter per second. We have to find the magnitude of velocity of man relative to his image. This is a very good question. Guys, simply, basic question if I say, sir, if this man is moving with 15 meter per second, I say its image will be formed over here. This will also be moving with what velocity? We say velocity of image in this case will be minus 15 meter per second. Okay. If this is moving towards right, if the velocity, guys, I have told you this before. If body is moving towards right, we take its velocity positive. If body is moving towards left, we take its velocity as negative. So if this is positive velocity, this is negative velocity. But we don't have to find this VI. We have to find the velocity of man, velocity of this man with respect to this, We have to find velocity of man with respect to image, This is what we are supposed to find out. And my dear friends, you might have studied one single concept. What is that? We say, sir, velocity of, you might have studied this, velocity of A with respect to B. It is velocity of A minus velocity of B. This is the relative velocity concept. Now here also we'll say, sir, velocity of man with respect to image. I can simply say velocity of man minus velocity of image. Velocity of man minus velocity of image. What will be the velocity of man in this particular case? We say, sir, that is 15 minus velocity of image is how much? That is minus 15. Okay. Minus into minus is plus. So answer in this case is 30 meter per second. So this is with respect to the ground frame. Its velocity is minus 15. But with velocity of man with respect to this is, we say, 30 meter per second. Let me know in the chats if this is crystalline clear. Let me know in the chats if this is crystalline clear. If this is crystalline clear to each and every one. I hope you are liking this particular session. Huh? Make the like count 1000 plus, guys. Everybody out there, I want you guys to make the like count 1000 plus. Okay, let's move on to the next question. We have got the question over here. An object is moving towards a stationary mirror, plane mirror, with a speed of 2 meter per second. See, in the left direction, we have got a mirror over here. Okay, this is the mirror we are having in this particular case. And let's suppose I'll polish it from this side. I am polishing it from this side. And there is a person, okay, which is moving towards the mirror in the left direction. With a speed of, we say, sir, 2 meter per second. Okay. And we call this as minus 2 because it is towards left, in the left direction. The velocity of image with respect to the object is, we are supposed to find, if this is an object, its image will be formed behind the mirror. Okay. And this will be having the velocity of 2 meter per second. Okay. If this is minus 2, this is plus 2. Okay. This is velocity of image. Okay. And we are supposed to find velocity of image with respect to the object. Means we have to find velocity of image with respect to the object. How do we find it? VIO. We say simply, sir, it is velocity of image minus velocity of object. And what is the velocity of image in this case? That is plus 2. Then we say minus. What is the velocity of object? Sir, this is velocity of object, that is minus 2. Why do I have to say it is minus 2? Because it is moving towards left. So I say this is minus 2 over here. So can I say 2 plus 2 is 4 meter per second? So velocity of, yes, a lot of people are giving the correct answer. Is that clear? Okay, an important question that you guys need to understand in this particular case. Okay, guys, I have told you, if we have a mirror, let's suppose over here. Okay, in front of the mirror, if I am placing an object, this is the object in front of the mirror. We know, sir, its image will be formed behind the mirror. This is the image of this particular object behind the mirror. Okay, everybody knows that this is the image of the object behind the mirror. This will be image. Okay. Now, let's suppose I say in this particular case, guys, do not use your brain over here. Don't use your logic over here. Whatever I say, you have to follow that. If I say, my dear friends, I have got the mirror 1 over here, that is M1. Okay, this is the mirror 1 I'm placing over here. Like it is something like this, mirror M1. And then I have got one more mirror at some angle. This is one more mirror at some angle, that is M2. Whatever I say, just remember it and take a look over here completely. Okay, I have got one mirror over here, it is polished from this side. And I have got one more mirror over here, that is M2. Angle between these two mirrors is theta. Okay. Like over here, if I say in this particular case, if I say this object is placed at some distance, we say, sir, 15 meters, we say its image will be also at 15 meters. Okay, we have placed the object and image over here linearly. In this particular case, it is some sort of angular things. Okay. Now see, if I say in this particular case, angle between the two mirrors is theta. Let's suppose I am placing an object over here. At what angle? Sir, at an angle of alpha. I am placing an object at an angle of alpha with the mirror M1. Now tell me one thing, sir. Everybody knows that if you place an object in front of the mirror, it will create its image. If object is at angle alpha, can we say its image will be also formed at angle alpha? Its image will be also formed at angle alpha. Yes. Its image will be also formed at angle alpha. Now, my dear friends, if this image I1, listen to me very carefully, we call this as image I1. We say, sir, this is the first image which is formed at an same angle alpha over here. Now, this image over here, I1, don't you think that, sir, this image will act as an object for mirror M2? 110%. Guys, it is like for this mirror, this is the object. This is the image. Now, this image will behave like an object for this mirror. Now, can you tell me this image is at what distance? This image is at what distance from this mirror M2? You'll say, sir, this angle is alpha. This angle is theta. Means from this mirror till this image. From this mirror till this image. What is the angular distance? You say, sir, alpha plus theta. So this mirror M2 will form the image of this I1 at what angle? At the same angle, that is alpha plus theta, behind the mirror. Okay, I hope I am not confusing you. We say in case of the M1 mirror, we say I1 is formed at, we say alpha. So in case of the M2 mirror, this M2 mirror will form the image of this image. This will now behave as an object for this mirror at an angle. We say, sir, I2 is formed at we say alpha plus theta. Why? Because the angular distance between this mirror and this image is alpha plus theta. Now tell me one thing. Now this is the image I2. This image I2 will behave like an object for this particular mirror. 110%, sir. So we say, what is the distance between this mirror and this image? You say, sir, this angle is alpha plus theta and this angle is theta. So how much will be total angle? Alpha plus theta, that is alpha plus 2 theta. So we say in this particular case, this I2 behaves like an object for this one at an angle what? Alpha plus 2 theta. So this mirror will again form its image at what angle? Alpha plus 2 theta. This mirror will again form its image at alpha plus 2 theta. Okay. I'll write over here. So this is mirror M1, this is mirror M2. So once again, this M1 mirror will form the image I2 is formed at, we say, alpha plus 2 theta. Similarly, once again, this image will behave like an object for this mirror, and it will again form its image, and it keeps going. It keeps going. I hope this is crystal and clear. This is super clear. Okay. Now, my dear friends, in general, what I'm trying to say, if somebody asks you to tell me how many number of images will be formed in this particular case, how many number of images will be formed in this particular case, what will you say? Sir, in order to find the number of images, first we'll find M. Sir, what is M? What is M? Let me tell you. M means 360 divided by theta. What is theta? Theta is the angle between the two mirrors. Okay. So if you have to find M, sir, is M number of images? We say no, M is not the number of images. M is something else. Okay, what is M? M is 360 by theta. Theta is the angle between the two mirrors. Okay, you got M? Now. This is a bit confusing, but once we solve the questions on this, everything will be clear. If M is an integer, like if M is coming out to be even, if the value of M is coming out to be, let's suppose 12, 14, that is even. We say in that case, number of images will be M minus 1. We say number of images will be M minus 1. Let's suppose if M is, we say, sir, 15. Sorry, we say if M is, we say, let's suppose even 14. What will be the number of, if M is 14, what will be the number of images? 14 minus 1, that is 13. And my dear friends, if M is coming out to be odd, we say there are two cases. If object is at angle bisector, sir, what is this? You will get to understand. Please wait for a few seconds. If object is at angle bisector, we say number of images will be M minus 1. And if we say object is placed at an angle, is not at angle bisector, number of images in that case will be M. Okay, let me show you the question that will clear all the confusions over here. The first question we have got over here. Two plane mirrors are inclined at an angle of 30 degrees. It says that we have got two plane mirrors. Okay. So let's suppose this is M1 and let's suppose this is M2. Angle between these two is, we say, sir, 30 degrees. Okay. And it is saying that an object is placed at 10 degree. This is the object placed at 10 degrees. Okay. Over here, the object is placed at 10 degrees. This is 10 degrees. Okay. And in this case, we have to find the total number of images. In order to find the total number of images, what is the first thing? We say, sir, M. M will be, sir, 360 divided by theta. So I can say this is 360 divided by, what is the value of theta in this case? That is 30. This and this will cancel. 3, 8, this is 12. So we say, sir, this is even. Now tell me one thing. If M is coming out to be even, number of images will be M minus 1. So we say number of images is M minus 1, that is 11. Number of images will be 11. Okay. Now, let's suppose I am giving you this particular question. In this question, what is mentioned is that we have got mirror M1, we have got mirror M2. Angle between these two is theta. This is the object over here. If theta is equal to 60 degrees, the first part, we say, sir, theta is 60 degrees. I'll write theta is 60 degrees. Can you find the value of M? We say, sir, that will be 360 divided by theta, that is 6. 0, 0, 6, 6 are. So M is 6. M is even in this particular case. If M is even, what is the number of images? So that will be M minus 1. So that will be 6 minus 1, that is 5. Okay. Second part of the question. Let's solve second part of the question. So what is second part of the question? I'll write over here. That is if theta is equal to 72 degrees. Okay. And object at, we say, sir, 40 degrees from M1. Let's first find the value of M. We say, sir, M will be, sir, 360 divided by, M will be simply 360 divided by theta. What is the value of theta? That is 72. Okay, that will come out to be 5, and that is odd. if m is odd, now come over here, come over here. If m is odd, there are two cases. Object is at angle bisector. Angle bisector means, see, what is the angle between the two? That is 72 degrees. Angle bisector means 72 divided by 2 is 36. If I say an object is at 36 degrees, then we say object is at angle bisector. Exactly at the midpoint, at the midway. That is what we call the angle bisector. 36 plus 36 is 72. So we say in this particular case, object is not at angle bisector. So number of images will be in this case m. So we say object is not at angle bisector. So number of images in this case will be m. So that will be 5 because object not at angle bisector. Okay. And then we have next we say a third point. Third question. We say theta is equal to, we say, sir, 72. So in this particular case, we have to find the value of m. M will again come out to be 5. And number of images in this case will be, guys, it is mentioning object it as angle bisector. We say object at angle bisector. That is 36 degrees. So number of images in this case will be m minus 1. So that is 4. 5 minus 1 is 4. Tell me in the chats, guys, if this is crystalline clear. Yeah. In this last case, it is coming out to be 4.5. So then you have to take 4. Then you have to take 4. In the last case, in the fourth case, we say m is coming out to be, we say 4.5. So in this case, n will be 4 only. Number of images will be 4 only. Is this crystalline clear? Let me know in the chats, everybody. And like this particular session if you have not liked this session. Let's come on to the spherical mirrors. Let's come on to the spherical mirrors. Let's come on to the spherical mirrors. Okay, now listen to me very carefully. If we talk about the spherical mirror over here, let's suppose we are taking a complete sphere. I'm taking the complete sphere over here. Okay, and you need to cut this complete sphere in this particular case. Cut it somewhere around over here. Okay, you have got a spherical ball and cut the spherical ball. And once you cut the spherical ball, this bowl will come out of that ball. That bowl shaped structure will come out. Okay. Now this side, this back side is what we call, we say, sir, convex side. This back side is what we call the convex side. This curved side is outside. This outer part is what we call the convex side. And this inner part is what we call the concave side. Okay. Now, my dear friends, listen to me very carefully. If we polish from this outer side, from convex side, if we polish from the convex side, then we say, sir, reflection would take place from the inner side. So we call this as concave mirror. Okay. If we polish it from the convex side, then we say this is the concave mirror. And if we polish it from the inner side, that is convex side. Sorry. If we polish it from the concave side, then we say it is a convex mirror. Okay. So in simple words, from now onwards, if I have to make the concave mirror, I'll be making it something like this. This is what we call the concave mirror. Polish it from the convex side and reflection takes place from the concave side. And if I have to make the convex mirror, I can make it something like this. This is convex because it is polished from the concave side. Okay, this is convex. Or you can also make it something like this. This is also convex. Okay, let's move on to the next one. Okay, now in this particular case, if I say I have got a mirror over here, let's suppose I'm taking a spherical mirror, or we convex or concave. Spherical mirror from now onwards is simply convex mirror or concave mirror. Okay. Spherical mirror from now onwards is simply convex or concave mirror. Now, my dear friends, listen to me very carefully. If this is a spherical mirror over here, we say, sir, take a line which should exactly cut this mirror from the center. Okay. This is what we call the principal axis. This line is what we call the principal axis. Okay. Now, my dear friends, if we say, sir, this sphere has some center, that is this one. Okay. So means if you cut some part of the sphere, that is this one, so it will also have the same center like this. Okay. If you complete it, this will be the complete sphere. So this will be the center. So in this particular case, we call that center. If you complete this, it will become the complete sphere. So we call this center as center of curvature. So center of spherical mirror is what we call the center of curvature. Okay. And my dear friends, from center of curvature, if you take a line and it falls at this till this sphere, so we say this is what we call the radius of curvature. Sir, what is radius? Simply it is, if this is center, from center to surface, this is what we call the radius. So that is radius of curvature. Here we say it is radius of curvature. Okay. And if this is center of curvature and this is what we call the pole. So between center of curvature and pole at the midpoint is what we call the focus. Okay. And this focus F is equal to R by 2. R means the radius. Half of the radius is, we say, sir, focal length, that is focus over here. Simply, if we make a spherical mirror, sir, this is the principal axis. This is the center of curvature. Sir, this is the radius of curvature. Sir, this is the focus. This is the pole. And this would be some incident ray falling onto this mirror. Okay. Now, let's suppose we talk about the image formation. What does image formation actually mean? Image formation in case of, I'll write over here, image formation in case of concave mirror. Okay. Listen to me very carefully. Guys, previously we discussed if we have got a plane mirror over here, okay, if we place the object in front of the plane mirror, it forms its image something like this. This was the case of the plane mirror image formation in the plane mirror. But right now we're talking about, we say image formation in case of spherical mirrors. First, we'll talk about the concave mirror. Listen to me very carefully. Okay. Now, my dear friends, let's suppose I'm taking the mirror over here. Listen to me very, very, very carefully. Sir, this is what we call the center of curvature. Or 2F. Twice focus. Okay. And my dear friends, this is focus and this is, we say, sir, pole. If we place, this is what we call the object. If we place the object, listen to me very, very, very carefully. If we place the object beyond 2F, beyond 2F means here. If we have placed it over here, we say this would have been between F and 2F. If we place the object beyond 2F, listen to me very carefully, whatever I say over here. If you have got a concave mirror and you are placing the object over here beyond 2F, in that particular case, directly remember, my dear friends, the image will be formed. This is the image. We say, sir, the image will be formed between F and 2F. Remember directly. You don't have to focus on you have to remember. Okay. You don't have to focus on the logic. If object is beyond 2F, image will be formed between F and 2F. Okay. Now, image is formed between F and 2F. Done. Now, my dear friends, in this, sir, why wasn't the image being formed behind the mirror? This is a spherical mirror, concave mirror. And this is the logic which happens. This is actually the case which happens over here. So we say in this case, object is from this side, image is also from this side. So we say, my dear friends, image is formed between F and 2F. It will be real. Sir, what does the real image mean? Real image means that image where reflected rays actually meet. Now see, one ray will leave from the object and it passes and goes over here. Another ray will leave from the object and it passes, and the point, this is the reflected ray, this is the reflected ray. The point where reflected rays meet, can I say image will be formed at that point? So see, this is the image. So we say this image will be real. In reality, the two rays are meeting. So we say in reality, the two rays are meeting. Okay. It is inverted. What does inverted mean? Inverted means we say upside down. This means erect. Okay. Something like this. Okay. And this means we say inverted, upside down. So we say this is inverted over here. Okay. And diminished means smaller than object, Object is bigger, image is smaller. Directly, my dear friends, remember one thing. If you have got a spherical mirror, concave mirror over here, and if object is placed beyond 2F, image will be formed between F and 2F. And image will be real, inverted and diminished. Directly remember, next case. If object is between F and 2F. Now, this is 2F, this is F. This is concave mirror. We are placing the object between F and 2F. Now see, first ray will leave after reflection, it goes something like this. Second ray will leave after reflection, it goes something like this. So the point where it is meeting, that's what we call the image. In this particular case, we say image is formed beyond 2F. We say image is formed beyond 2F. This is the image. And it will be real. See, these two rays are actually meeting. It is not appear to meet. They are actually meeting. So we say it is real. It is inverted, upside down. See, this is object, this is image, upside down. It is magnified, bigger. Magnified means bigger. Or you can also say enlarged. We say, sir, this is smaller and this is magnified. I hope this is clear. You have to remember all of these points. Question will be directly from this one. Next, third case, if the object is between focus and pole, if you have got a concave mirror and this is focus over here and this is, we say, this is the zoomed view. That's why you are saying focus over here. 2F will be over here, center of curvature. So if the object is between focus and pole, in this particular case, my dear friends, the light ray will go and leave something like this. And another light ray is reflected something like this. Now these two reflected are divergent. They cannot meet over here. But if you extend these, they will meet over here. So the point where reflected rays meet, image will be formed. In this case, these two reflected rays are, we say, appear to meet. They are not actually meeting. So we say here, image formed will be virtual. We say this is virtual image. It is erect. It is not upside down. Erect means this one, upside up. Okay. That is erect. And magnified, it is bigger than the object. You can clearly see. An image can be formed between this point to infinity anywhere. Hey, tell me in the chats if this is crystalline clear. Everybody out there. If this is crystalline clear. Guys, tell me. Is this clear? Is this crystalline clear? Great. Okay. Image formation in case of convex mirrors. Now let's suppose I am taking the convex mirror. Guys, here we have only two cases. Why? Because see, if this is a convex mirror, its focus will be from this side. Why, sir? Why? Because if you complete this particular sphere, it will be something like this. You cannot complete the circle something like this. No. So if you have to complete this sphere, it will be something like this. So obviously center has to lie from this side, from right side. and radius of curvature has to lie from this side only. So in this particular case, if we say object is placed near to the mirror, if we are placing the object close to the mirror, okay, let's suppose here. So the light ray will incident on this surface and it gets reflected. Another light ray is something like this and it gets reflected like this only, okay. So if you extend these two, the point where they meet, image will be formed. So first of all, in this particular case, image formed is virtual, image formed is virtual, image formed is erect, image formed is erect, image formed is erect. Image is diminished, smaller in size. Diminished means smaller in size. Okay. And it is between pole and focus. It is between, this is pole and this is focus. This is, we say, in case of convex mirrors. So in case of convex mirrors, first case is if the object is placed near to the mirror. So what is the next case? Next case is if the object is placed very far from the mirror. Very far from the mirror is at infinity, okay. In that particular case, we say, sir, light rays are coming from the infinity, parallel light rays. Okay, we say here object is at infinity, object is at infinity. Light rays are parallel. And in this particular case, we say these light rays get reflected something like this. So this will be the image where it is formed at focus. Let me show you directly. In case of convex mirror, if the object is placed at very far distance at infinity, image formed is virtual. See, you can see the virtual because light rays gets reflected from this side only. So they appear to meet at this point. So that's why this is virtual. It is erect and it is very small. It will be small as compared to the object. Keep that thing in your mind. Okay. And it is formed at focus. It is formed at focus. Sir, do we have to remember all of these? Yes. Okay. Do we have to remember all of these? Yes, we have to remember all of these. Okay, I hope this is clear. Now comes basically the mirror formula. What does mirror formula actually say? If we talk about the mirror formula, listen to me very carefully. It is 1 by V plus 1 by U is equal to 1 by F. I can simply say, wait. I can simply say this formula helps us to find position of object, image, position of object and position of image, comma, focal length. Means if you have to find the focal length of the mirror, this will help you. If you have to find the position of the object, this will help you. Okay, I'll show you the question on this one. Just give me a second. See, if we talk about this particular formula, it is 1 by V. What is V? V is the position of the image, where image is formed. What is U? U is the position of object. What is F? F is focal length. Let me show you in the question. Let's suppose I have got a mirror over here. Its focal length is given 10. It's, we say, sir, position of image over here. This is, let's suppose, image in this particular case. Image is formed over here. So position of image is 30. We have to find the location of the image, where image is formed. We say in this particular case, U is given as, we say, sir, 30. We say, sir, focus in this given as how much? We say, sir, 30. We are supposed to find the value of V. Where will be the image actually formed in this particular case? That's what we are supposed to find out. Sir, which formula we'll use? We'll use this particular formula. That is this one. 1 by V plus 1 by U is equal to 1 by F. This is the formula we will be using over here. Okay. Okay. Now listen to me very carefully in this particular case. One thing I just want you guys to remember over here, that is sign conventions. We said take that direction as positive in which incident ray is moving. What does that mean? Let's suppose we have got a mirror over here. This is the mirror, okay? And in front of this is the principal axis. in front of the mirror I have an object. Everybody knows that, sir, from the object incident rays will leave. This is the direction of incident rays. What is mentioned over here? Take that direction as positive in which incident ray is moving. Incident ray is moving in this direction. We say we'll take this side as positive and we'll take this side as negative. Because take that direction as positive in which incident ray is moving. Okay? Now, my dear friends, if I say this is the object, from the object we say, sir, incident rays leave. Incident rays will leave from the object. Okay? So it is mentioned over here. Okay? So this is the direction of incident rays. Can I say this side will be a positive and this side will be negative? Yes. Now, if this is the mirror, from this side, we say, sir, object is placed at what distance? At U. U is 30. But plus 30 or minus 30? Minus, because this is from the negative side, so it is minus 30. And what about the focus? Focus of this mirror is also from this side, so that is minus 10. So we have to find in this case, what is the value of V? We'll use the mirror formula. We say, sir, use mirror formula. What is that? That is 1 by V plus 1 by U is equal to 1 upon F. So what is 1 by V? I'll write over here. See, we'll have to find V. I'll write 1 by V is equal to 1 upon F minus 1 by V, 1 by U, 1 by U. Okay. Now cross multiply. So I can write 1 by V is equal to U minus F upon U minus F upon U into F. Now do the reciprocal. So V is equal to U into F upon U minus F. This is the formula that we got. Now tell me in this particular case, sir, V is equal to, what is the value of U? U is, we say, sir, minus 30. Okay. What is the value of F in this case? That is minus 10 upon, what is the value of U? That is minus 30. Then we say minus, formula is minus, okay? Minus, and then we say in this case, minus 4, this is minus 10, okay? Minus into minus is plus. So I can write it, 30 into 10 is, we say, sir, 300 divided by minus 30 plus 10 is minus 20. This and this will cancel. So V in this case is minus 15. Is that clear? Is that clear? Is that clear? Is that clear? Great. Let's move on to the, okay, tell me in this particular case, find the location of the image. Find the location of the image. Okay. Here we have taken the convex mirror. In this case, it was the concave mirror. It is convex here. See, if object is placed at this particular point, this is the object. Can I say, sir, this is the direction of incident rays? This will be the direction of incident rays. If this is the direction of incident rays, listen to me very carefully. I can say, sir, this side in this case will be positive. Okay. And this side in this case will be negative. This side in this case will be negative. Okay. This side in this case will be negative. So means, my dear friends, if this is the convex mirror, this side will be the focus. So in this case, focus is given as 20 centimeter. So focus will be minus 20. Okay. And we say, sir, over here, U is from, focus is plus 20 because focus is from positive side. And U is, we say, sir, from negative side. So we say in this case, U is how much? That is minus 20. Okay. That is minus 20. Now tell me in this particular case, we have to find the value of V. We know, sir, V is equal to U into F upon U minus F. So V is equal to, what is the value of U? That is, we say, sir, minus 20 into, we say, sir, focus is plus 20 upon U. U is minus 20, then minus of this 20 over here. So V is equal to, this is minus 400 divided by minus 20 minus, this is minus 40. So this will come out to be 10. So V in this case is, we say, sir, 10 centimeter. Plus 10. Yes. Great, 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 great. Okay, let's talk about the magnification. What does magnification actually mean? What does magnification mean? Magnification, we say it is simply, it is defined as the height of image upon height of object. Simply, I'll write one more definition over here. It tells us how much. Okay, it is not visible. I'll write over here. It tells us how much image is magnified. So magnification simply tells you how much image is magnified, how much image is bigger than the object. Okay. So I say M is equal to, what is the formula for magnification? Height of image divided by height of object is equal to my magnification. Sir, is there any other formula? So we say, sir, that M is equal to minus V by U. V is the position of image, U is the position of object. Sir, is there any other formula in terms of focal length and position of object? What is the formula? F upon F minus U. Sir, in terms of focal length, in terms of position of the image, sir, we say F minus V upon, we say, sir, F. This is the magnification. This is the magnification. Okay. Let's move on to the next one. Okay, this is the question that we have on the screen. Can you tell me in this particular case, listen to me very, very, very carefully over here. I have got the mirror. I have got the mirror. In front of the mirror, the size of the object, height of object, this is object. This is object over here. We say, sir, this is object. Height of the object is 1 mm. And U in this case is, we say, sir, 15 centimeters. 15 centimeters. Okay. My dear friends, we are supposed to find the position of the image, height of the image, and magnification in this particular case. Can you tell me the answer of this particular question? Everybody out there in the chats, what is the answer of this particular question? First, try to find out the magnification. Okay. First, try to find out the magnification. Okay. See, I'll tell you. Guys, if this is the object, we say, sir, this will be the direction of incident rays. Why? Because incident rays will leave from the object. So this side will be positive side and this will be simply, sir, negative side. Sorry, this will be negative side and this will be positive side. This will be, sir, negative side and this will be, sir, positive side. Okay. If this is negative, can I say position of the object, where object is, that is at minus 15 centimeters. Okay. And focal length of this, it is, radius is 20. What is focal length? Focal length is R by 2. So that is 10. And focal length in this case is also minus 10 centimeters. Minus 10 centimeters. Okay. And what we are supposed to find out? We are supposed to find out the magnification. So we'll first find the magnification. M is equal to F upon F minus U. Why do we use this formula? Because we know F, we know U. Recently we calculated magnification formula, F upon F minus U. So can I say in this case, sir, this magnification will come out to be, what is the value of F in this case? What is the value of F in this case? F in this case is, we say, sir, 10 upon, what is the value of this? This is 10 minus U. What is the value of U? That is minus 15 over here. Okay. This is minus 10 minus 15. This is minus 10 minus 15. So this will be minus 10 upon, see, minus 10 plus 15. That is 5. Okay. Because minus 10 plus 15. 15 is bigger, so it will be 5. 5 ones, 5 twos. So magnification in this case will come out to be minus 2. It will come out to be minus 2. If magnification is minus 2, tell me one thing. There is one more formula for magnification. Which one? M is equal to minus V by U. Use this one. As we say, M is equal to minus V divided by U. So we can write over here, what is the value of M? That is minus 2 is equal to minus V divided by, what is the value of U? That is, U is minus 15. U is minus 15. Okay. Minus 15, this is minus 30. So V in this case will be minus 30. So position of the image in this case is minus 30. Position of the image in this case is minus 30. Okay. Okay. Next, what we are supposed to find? See, magnification is done. Position of the image is done. We have to find the height of the image. One more formula we also studied, that is this one. Magnification is height of image divided by height of object. So I can write over here, as magnification is height of image divided by height of object. Okay. So I can say magnification comes out to be -2 multiplied by what is the height of object, that is given as 1 mm. So that will be height of image. So I can say height of image in this case will be -2 mm. Is that clear? Tell me in the chats, everybody, is this crystalline clear? Is this crystalline clear? Okay. One more important concept that I want to tell you in this particular case, that is, listen to me very carefully. That is velocity of image. Let's suppose you have got a spherical mirror over here. Okay. And you have an object something like this. And this object is moving something like this. Okay. It has got the velocity of object, this one. It is moving with the velocity of object. And this mirror has got the velocity of mirror, Vm. Okay. So we say when object and mirror are moving along the principal axis, this object is moving along principal axis, this mirror is moving along principal axis. Okay. In that case, you will be asked to find if this mirror creates the image of this object. What will be the velocity of the image? Guys, previously we talked about in case of plane mirrors. Right now, this is the spherical mirror. If this is the object over here, I hope you remember. I'll show you that slide. See. This one. If you have got this mirror over here, and this is the object which is moving with some velocity, what is the velocity of the image? Velocity of the image in this case will be 2 times of Vm minus V0. Okay. This is in case of the plane mirror, but right now we are talking about the spherical mirror. Okay. We are talking about the spherical mirror. So we say if we have got the spherical mirror over here, and this is the object which is moving parallel to principal axis, the first case, what is the velocity of the image? See, this is the formula which you have to remember. Velocity of image with respect to the mirror. Keep that thing in. Directly remember, guys. Don't use your mind over here. I'll show you the questions on this format. That will clear the confusions. We say velocity of image with respect to mirror is equal to minus times m square. What is m? M is the magnification. We know how to calculate magnification. Recently we saw. V, velocity of object with respect to the mirror. Okay. This is how do you find. As I told you, in 99% of our cases, we say mirror is at rest. Mirror does not move. Velocity of mirror is 0. So can I say, my dear friends, see, you can write this particular formula. If you have got this formula, what does magnification mean? Magnification M. We recently calculated magnification over here. Come. Sir, magnification is minus V by U. So if we can do one thing, instead of this M, can we put V by U? So we say V square by U square. We can write this equation something like this also. Okay. I hope this is clear. Where M is the magnification. Okay. Is this clear? Tell me in the chats. Is this clear? Tell me in the chats. Is this crystalline clear, guys? Tell me in the chats. We'll have the question that we need to solve. This one. This is the question that is important in this case. This is the question that is important. See. I have got a mirror over here. Focal length of mirror is 30. This is, we say, 20. See. I have got an object in this particular case. Object is moving with a speed of, this is velocity of object, that is 5 meters per second. Okay. Yes, sir. If object is moving with a speed of 5 meters per second, focal length is, we say, sir, 30. Tell me, sir, incident rays will leave from the object something like this. Okay. So we say this side will be the positive side. And we say this side will be the negative side. Everybody knows it. This side will be the positive side and this side is negative side. Can I say in this particular case? Can I say in this particular case? Sir, U is the position of the image. Can I say image in this case will be position of the image is minus 30 centimeters? Why, sir? It is 20. It is minus 20 centimeters. Why, sir, in this particular case, it is minus 20 centimeter? Because it is from this negative side. Object is lying from the negative side. And focal length is also, sir, minus 30 in this particular case. Okay. We are supposed to find in this particular case, this is the velocity of the object. This is the velocity of the object. We are supposed to find in this particular case, velocity of the image. Find the velocity of the image. We have to find velocity of the image. Now tell me one thing. What is the formula that we have recently studied? Sir, in case of spherical mirrors, this is the formula that we recently studied if we have to find the velocity of image. We can write it something like this also. If we consider mirror at rest, then we can say velocity of image is equal to minus magnification square velocity of object. If mirror is at rest, then you can consider, forget about this formula, rub this. Remember this formula directly. Velocity of image is equal to minus m square into velocity of object. Now, how to find this m? Come here. Sir, when it comes to the magnification, can we say, sir, magnification will be simply f upon f minus u. Because we have seen this formula also. So can I say, sir, this magnification will be simply, what is the value of f over here? That is, we say, sir, minus 30 divided by, what is the value of, we say f, that is minus 30 minus of, this is minus 20. Okay. So can I write it something like this? This is minus 30 upon, see, minus into minus is plus, 30 minus 20 is minus 10. So it will be 3. Magnification in this case will be 3. Okay. Now tell me, what is the formula? Sir, velocity of image is equal to minus m square into velocity of object. Velocity of image is equal to minus, what is the value of this? This is 3 square. Velocity of object is how much? That is 5. So this will be 5. So this will be minus 3 square is 9. That is 9 into 5 is 45 meter per second. Yeah. This is minus 45 meter per second. Minus 45 meter. Minus represents body is moving towards left. Away from the mirror. Yes, away from the mirror. Okay. On the same concept, solve this particular question. Okay. Is this crystalline clear, guys? Let me know in the chats. If you have not liked the session yet, like it as soon as possible because that's mandatory. Liking the session is mandatory. Everybody of you like this particular session. All the people out there. Okay. Make the like count 1000 plus. I want you guys to make it in next 10 seconds. I'm counting. In next 10 seconds, you have to make this 1000 plus. Okay, next 10 seconds, you have to make this 1000 plus. Everybody out there. Now see, in this particular case, what does the question actually say? A point object is moving along the principal axis on a concave mirror of focal length 24 centimeter. We have got a concave mirror. Let's suppose this is the concave mirror over here. Okay. And if this is the concave mirror, we have an object which is moving along the principal axis. Let's suppose this is the object which is moving along principal axis. Okay. And its velocity is, we say, sir, 9 meter per second. and we say it is at a distance of, 60 centimeters. Okay, it is mentioned it is at a distance of 60 centimeters from the mirror. And focal length of the mirror in this case is 24 centimeters. Okay. What is the velocity of the image? We have to find the velocity of the image. We have to find the velocity of the image. Me one thing, sir. In order to find the velocity of the image, we know, sir, velocity of the image is simply m square. That is velocity of object minus m square velocity of object. First of all, in this particular case, we say, sir, focal length will be, sir, minus 24. Already discussed so many times. Sir, you will be in this case 60 centimeter. Okay, minus 60 centimeter. This is also minus 24. And we say velocity of image in this case is 9 meter per second. 9 meter per second. Now, if I tell you in this particular case, what is that? What is that? Sir, we have to find the magnification first. We'll write m is equal to f upon f minus u. Sir, what is the value of f? That is minus 24 upon f minus u. Minus 24, we say, sir, plus 60 over here. Minus 64, minus 24, plus 60. I can say this will be minus 2 divided by 3. Magnification in this case is minus 2 by 3. Now, let's put it in the equation first. So I can write, if we have to find this, I can say, sir, velocity of image in this case will be simply minus m square. That is minus 2 by 3 whole square into velocity of image. How much is the velocity of image? That is 9. So into, we say, sir, 9. So I can write this is minus 2 square is 4, 3 square is 9. This is 4 by 9 into 9. This and this will cancel. Velocity of image is minus 4 meter per second. Velocity of image is minus 4 meter per second. Okay. Let's talk about the power of the mirror. Yes. Away from the mirror. Let's talk about the power of the mirror. What does power of mirror actually mean? It is simply, see. Power of the mirror is defined as the ability to converge or diverge the light rays. Okay. If we say I have got a mirror over here, okay, let's suppose I have got a mirror over here. The light ray is falling onto this one and it gets diverged, something like this. Okay, how much diversion is possible? Okay, it is defined as how much is the ability of the mirror to diverge or converge the light rays. More it diverges the light rays, more power it has. Less it diverges the light rays, less power it has. Okay. So if we have to find the power, we simply use this particular formula. 1 upon focal length minus 1 upon focal length. If it is given in meters, we say 1 upon f in meters. If it is given in centimeters, we say minus 100 upon f in centimeters. If f focal length is in centimeters, then we say this formula. If focal length in meters, then we say this formula. Let me show you the question. We are given in this particular case, we are given a question. Find the power of a concave mirror of focal length 20 centimeter. If we make the concave mirror, this is the concave mirror we have. Okay. Now everybody knows that if this is the concave mirror, everybody knows that, sir, object will be placed somewhere around over here. This will be polished, something like this. Okay. So this direction in this case will be, sir, direction of incident rays. So I can write over here, this will be positive side and this will be negative side. If this is the negative side, can I say in this particular case, my dear friends, focal length of this is minus 20 because its focus is from this side? Yes. Now, if focal length is minus 20 centimeter, can I say what is the power? Power is simply, sir, minus, we say, sir, 100 upon focal length. Focal length in centimeters, so this will be minus 100 upon, what is the focal length in this case? That is minus 20. So can I say this will be 5 plus 5 diopter, Similarly, if you have got over here, this question, over here, find the power of the convex mirror. See, if we have to make the convex mirror, we say, sir, in case of convex mirror, we say focal length is, we say, sir, negative. Okay. Sorry, in this case, we say focal length is negative. Here we say focal length is positive. Focal length is positive. Okay. Okay. And if we have to find the power, that is minus 100 upon focal length. Focal length is how much? That is 25. So this will be minus 5 minus 4 diopter. Okay. Is this clear? Is this clear? Is this clear? Is this clear? Because if you make the convex mirror, that will be something like this. Okay. So focal length in this case will be from this side, and that is positive because you will place the object something like this. So this will be the negative side and this will be the positive side. As simple as that. A refraction of light. Let's talk about the refraction of light. Sir, what does refraction of light mean? Listen to me very carefully. We'll take the break at 1:30. We'll take the break at 1:30. See. Refraction of light. What does refraction of light mean? Sir, what is a reflection? A reflection of light means we have previously studied, if we have got a surface, light falls onto the surface and it gets reflected something like this. Okay. So this is incident ray, this is reflected ray. Let's suppose this is a medium 1 from this side. Okay. And this is a medium 2 from this side. This will be air from the upper side. This will be the water from the lower side. These are the two mediums. Okay. So if the light is reflected in the same medium, so we say it is the reflection. Now, in case of refraction, we have got over here, this is the incident ray. We say, sir, this is the medium 1, this is the medium 1, this is the medium 1, and this is the medium 2. Okay. We say if the light comes something like this and then it is moving into the another medium. When light enters from one medium to another medium, I'll write over here, when light enters from one medium to another, it is called refraction. It is called a refraction. Okay. And remember, my dear friends, everybody out there, remember this important point. What is that? If velocity of light in this medium is v, we say if it is reflected in the same medium, its velocity will remain same. If its wavelength is lambda, if it is reflected in the same medium, this is reflection, its wavelength will remain same. Frequency is same. But if the light is basically, we say, moving into the another medium, if light moves from one medium to another medium, we say if here velocity is v, here velocity will be v2. Here it is lambda, here it will be lambda 2. But frequency remains same because frequency depends upon the source. So in case of refraction, we say, sir, velocity, wavelength changes. Okay. And it is when light moves from one medium to the another medium. Okay. And this is what we call the incident ray. Let's talk over here. Laws of reflection. Okay. Refraction. We say this is the reflecting, this is the surface. We say this is the incident ray. I'll write over here. This is the incident ray. Okay. This is the refracted ray, which gets refracted afterwards. Okay. This is the refracted ray. And this is normal. Okay. My dear friends, listen to me very carefully. This is the incident ray, this is the refracted ray, and this is the normal. What is the first law? Incident ray, refracted ray, normal, all lie in the same plane, This, and this. Okay. Now tell me one thing, sir. If there would have no separation, if there was no any other medium over here, can I say in that case, sir, then this incident ray would have gone straight, something like this? Yes. So, but in actual reality, it went something like this. So this is the deviation. So deviation in case of this is I minus R. Deviation, this is angle of incidence, this is angle of refraction. Deviation in this case is I minus R. Angle between incident ray and normal is angle of incidence. Angle between refracted ray and normal is angle of refraction. And this will be I minus R. Okay. So this is the first law. What does first law says? Incident ray, refracted ray, normal all lie in the same plane. What does next law say? Next law is basically Snell's law. Next law is Snell's law. So before that, let me tell you something about the refractive index. We say refractive index of this is a refractive index. Okay. So this is refractive index of this one. Refractive index. So refractive index of this medium is mu2, of this is mu1. Guys, for different mediums, refractive index is different. Refractive index tells you how much optically denser the medium is. Like for air, we say refractive index mu is equal to 1. Okay. Similarly, for any other mediums, it may be different. For some medium, it is √2. For some medium, it is 2. Okay. So we say directly remember, sir, if there is a medium, it has refractive index. Refractive index tells us how optically denser, thick the medium is. Optically. Okay. What is that? We don't have to go there. Directly remember. Refractive index of different mediums is different for this. And let me just tell you, there is a formula. V is equal to C divided by mu. V is equal to C divided by mu. Sir, mu is refractive index. C is speed of light. So refractive index tells you what will be the speed of light in a medium. Refractive index tells you how much is the speed of light in any medium. If refractive index is more, we say, sir, speed of light in that medium will be less. I hope now you got the feel. If I say refractive index of this medium is more, we say speed of light here is less. As simple as that. Okay. Now come over here. Now use the Snell's law. This is the second law. What does Snell's law say? Snell's law says that here we don't say angle I is equal to angle R. We say mu I into sine of I. What does mu I mean? We say, sir, mu I is the refractive index of that medium. Mu I is the refractive index of that medium in which incident rays are present. Incident rays are present. Okay. And mu R is the refractive index of that medium in which refracted rays are present. Okay. In which refracted rays are present. Now see, can I say in this particular case, this will be mu I and this will be, sir, mu R. Why? Because this is that medium in which incident rays are present and this is that medium in which refracted rays are present. So this will be mu R. So what does Snell's law say? Snell's law says that multiply mu I with sine of I. What is I? I is the angle of incidence. Sine mu I into sine I, that will be equal to refractive index of that medium where refracted rays are present multiplied by sine R. Sine R is the angle of refraction. This is we say, sir, Snell's law. Directly remember, when it comes to the laws of refraction, first law is we say angle of incident, incident ray, refracted ray and normal all lie in the same plane. Second law is Snell's law. What does that say? Mu I into sine I is equal to mu R into sine R. As simple as that. Okay. Now, an important question in this particular concept, in this particular case. What does it actually say? Let's suppose you have got, this is what we call the apparent depth or apparent height. Let's suppose you have got a swimming pool over here, or you have got the bucket over here. Have you ever experienced this? If you have got a bucket over here, in that bucket there is a water. And if you place a stone inside that water, it feels like, for you, it looks like if you want to basically hold that stone inside the water, you will place your hand inside the water. It looks like, see, if the stone is at this depth, it looks like the stone is at this height, at this, it doesn't look like it is at more depth. It doesn't look like it is at more depth. Okay, have you ever experienced this? Tell me in the chats. Have you ever experienced this? If I say you have got a bucket over here, okay, I say the stone is present over here. You are looking from, this is you, okay. So when you put hand inside your water, it looks like you have the stone over here, but in reality, it is present at this depth. Have you ever experienced this? So that's what we call the apparent depth. So we say, my dear friends, actually the stone is at this point, but this is the observer over here. With respect to the observer, it feels like it is not at that depth. It is at this depth. This depth is actually D dash. This is D dash. What is the actual depth? Actual depth is, we say, D. Why does it actually happen? Let me show you. This is the object, stone. Incident rays will leave from the object, okay? And it gets refracted something like this. It gets refracted something like this, okay? One more point I forgot to tell you. That is, if you have got incident ray something like this, let's suppose this is the rarer medium, okay? And this is the denser medium. When the light ray enters from rarer medium to denser medium, it is bent towards the normal. See, this was the original ray, it is bent towards the normal. So whenever the light ray moves from denser to rarer, it is bent away from the normal. It is bent away from the normal. See, in this case, this is the denser medium. This is the denser medium. I'll say this is the denser medium. Okay. And this is the rarer medium. So we say in this particular case, denser means it is air, it is water, it is air. So means if the light ray is coming something like this, it goes away from the normal. This is the refracted ray. And if you extend this refracted ray, it will meet over here. The point where refracted rays or reflected rays meet, image will be formed at that point, okay, in both the cases. So we say that's why image is formed over here. So this is what we call the apparent depth. This is what we call the apparent depth. At what depth it looks like the object is present, but in reality the object is present at depth D. So if somebody asks you to find the value of D depth, so that D depth will be, D dash will be simply, that is D upon mu I by mu R. What is mu I? Mu I is the refractive index of that medium in which incident rays are present. Mu R is the refractive index of that medium in which refracted rays are present. Okay. Okay. Now let me show you the question on this one. That will give you the more feel. Find the apparent depth of the fish with respect to the bird. This is the bird over here. We have to find the apparent depth of fish. This is water. Okay. This is water. Okay. Inside the water, we have got the fish over here. So this fish is at a depth of 24 centimeters. It is mentioned over here, 24 centimeters. So D dash, so we say D is equal to, we say, sir, 24 centimeter. But this is the observer over here. With respect to the bird, we have to find the apparent depth. So that will be at what depth the fish will appear to look like at. The fish will be at the apparent depth with respect to the bird. So that D dash will be D upon mu I divided by mu R. So D dash is simply, what is D? D in this case is 24 upon mu I. Mu I is the refractive index of that medium in which incident rays are present. Now tell me one thing. Sir, if this is the object, we say from object incident rays will leave. Yes. So what is the refractive index of this medium? That is 4 by 3. That is 4 by 3. I can write over here 4 divided by 3 upon mu R. Mu R is the refracted rays in refractive index of that medium where refracted rays are patterned. That is air. So that is 1. That is 1. Okay. So I can say it will be, if you go take it over there, this will be 24 into 3 by 4. Okay. 6 into 3 is 18. So D dash is equal to 18 centimeters. That's why I was saying, my dear friends, see, this fish is at a depth of 24 centimeter. But with respect to the bird, we say the fish is at 18 centimeters depth. The fish is at 18 centimeters depth. So bird will look, if for bird, it will look like it is at 18 centimeters only. But in reality, it is at 24 centimeters. Similarly, you have to find the apparent height of the bird with respect to the fish. Now you have to find the apparent height of the bird with respect to the fish. You'll use the same formula. What is that? we say apparent height h dash is equal to h upon, we say mu I divided by mu r. Now, if we talk about the height of the bird, what is the actual height of bird? That is 36. So I'll write over here, this is 36 upon mu I, refractive index of that medium where incident rays are present. Now guys, this is the observer and this is the object. So if this is the object, incident rays will leave from the object. So here mu is, we say sir, 1. Mu is, we say sir, 1. For air it is 1. So mu I is 1. Mu r will be 4 by 3. So if you take this in the numerator, this will be 36 into, we say sir, 4 by 3 only. Don't get confused over here. It is 1 upon 4 by 3. If it was 4 by 3 over here, then I would have said 3 by 4. But it is 1 upon 4 by 3. It will be this. Okay. So this will be 12 and that will be 48 centimeter. Okay. So bird will look like it is at 48 centimeters with respect to the fish. But in reality, it is at 36 centimeters only. Is this clear? Is this clear to each and everyone? Let's make the 1K likes. Yes, yes, you have to make the 1K likes. Everybody. Now see, critical angle and total internal reflection. What does critical angle actually mean? And what is total internal reflection? Critical angle and total internal reflection. Let's talk about critical angle and total internal reflection. See, my dear friends, let's suppose we have got this surface over here. Okay. From the upper side, we have the rarer medium. From the lower side, we have the denser medium. My dear friends, if I say, sir, there is a light ray which is moving from denser medium to rarer medium. Okay. Now, guys, I told you, whenever the light moves from denser medium to the rarer medium, it is bent away from the normal. If it was going from denser, rarer to denser, then it would have bent towards the normal. Okay. Now, my dear friends, listen to me very carefully. Listen to me very carefully. Listen to me very carefully. If I say, in this particular case, angle of incidence is directly proportional to angle of refraction. For a second, I will say, sir, if you increase the angle of incidence, we say angle of refraction will increase. Now, see. Let's suppose, guys. What I'm trying to say is that, let's suppose angle of incidence in this case is 30 degrees. So angle of refraction, let's suppose it came out to be 60 degrees. Now, if you increase it by 10 degrees, let's suppose it is 40 right now, angle of incidence. We say it will be more bent away from the normal. Yes. Can we say, listen to me very carefully. At some value of angle of incidence, let's suppose you are sending this light ray. At some value of angle of incidence, the refracted ray becomes something like this. This is the refracted ray. This is the refracted ray. This is the refracted ray. The refracted ray becomes parallel to this one, or it makes 90 degrees with the normal. So we say that value of angle of incidence at which refracted ray makes 90 degree with the normal, is what we call the critical angle, As if you keep on increasing the angle of incidence, we say, sir, angle of refraction will increase. So we say at that value of angle of incidence at which refracted ray becomes perpendicular to the normal, we say that is what we call the critical angle. And we represent that with theta c. I is equal to theta c. In this case, can we say, sir, angle of refraction is, we say 90 degrees because this is angle of refraction in this particular 110%. This is what we call the critical angle. Now, if we use the Snell's law over here, let's suppose this is the rarer medium and this is the denser medium. So this is the normal. If you are sending the light ray something like this and it gets bent something like this, this is the angle of refraction, that is 90 degrees. Okay. And this is, we say, sir, angle of incidence, that is theta c. Okay. And in this particular case, we have, this is mu I, and we say, sir, this is mu r, angle of refract. This is refractive index of this medium. Can we use the Snell's law over here? Yes. What does Snell's law say? Snell's law simply says that, sir, it is, listen to me very carefully. Mu I sin I is equal to mu R sin R. This is the Snell's law. I'll write over here. What does it say? Mu I sin of I is equal to mu R sin of R. Tell me in this particular case, sir, mu I means the refractive index of this medium. What is this? This is denser medium. That's why I'm writing mu D, refractive index of denser medium. And this is rarer medium, this one. So I'm writing mu R, refractive index of rarer medium. Okay. Now see, mu I, that is mu D, sine of I, what is angle I over here? Theta C. So sine of theta C. Mu R, we say, sir, this is mu R, refractive index of this medium. And sine of R, R in this case is 90 degrees, so sine of 90. So can I say in this particular case, sir, sine 90 is 1. So I can write sine of theta C is mu R divided by mu D. So this critical, and this is the value of critical angle, mu R by mu D. If you have to find the critical angle, simply refractive index of the rarer medium divided by refractive index of the denser medium. Okay. Come over here. One more concept. Guys, you said, sir, if we keep on increasing the angle of incidence at some angle, we say there will be critical angle. The refracted ray will make 90 degree. Now, can I say, sir, if we again increase the theta C, if we again increase the value of angle of incidence, if angle of incidence is greater than critical angle also. At critical angle, this was light ray was going something like this. This was the refracted ray at critical angle. But if you again increase the value of critical angle, we say then the light ray will again go something like this, and this will be the refracted ray in that particular case. This will be the refracted ray in that particular case. Now tell me one thing. This is the incident ray. In this denser medium. This is the refracted ray in the same denser medium. Tell me, is this refraction or reflection? This is what we call the reflection, and this is called total internal reflection. If the light ray is reflected in the same medium, that's what we call the total internal reflection. We say this is, if you keep on increasing the angle of incidence, if it becomes greater than critical angle, then total internal reflection takes place. I hope this is crystal and clear. Let me know in the chats. Is this crystal and clear, guys? Let me know in the chats. And this is the question where you have to find, the light falls on the surface to find its critical angle. We have to find its critical angle. Guys, this is, we say denser medium, this is rarer medium. I told you when it comes to the critical angle, sine of theta C is simply mu, come over here. What is the value? See, mu R divided by mu D. This is how do we find the critical angle? So we say mu R divided by mu D. So I can write, sir, in this particular case, sine of theta C is equal to, what is the value of mu R? That is 1. What is the value of mu D? That is root 2. So theta C in this case is 45 degrees. When is the value of sine theta is 1 by root 2, that is 45. Okay, this is one more question. This I'll give you as homework. I need to see how many of you people can solve this particular question. If the critical angle for total internal refraction from vacuum to is 30 degrees, then the velocity. Okay. This is homework. This is homework to you guys. Okay. Solve it later on and let me know the answer of this particular question in the comments. Okay. In this case, what is given? A critical angle for total internal reflection is given as this. Critical angle in this case is given as 30 degrees. Okay. Then the velocity of light in that medium will be, okay. It is saying that I have got a medium over here, okay? So this is the normal. This is denser medium and this is rarer medium. This is denser medium and this is rarer medium. Let's suppose this light ray is going from denser to rarer. It is going from denser to rarer, okay? Something like this. So this is, we say, sir, critical angle theta C. And this is given as 30 degrees in this particular case. We are supposed to find, first we'll find the refractive index. Let's find the refractive index of this medium, okay? Let's find the refractive index of this medium. It is going from medium to vacuum. This is medium and this is vacuum. A light ray is basically going from medium to vacuum. Vacuum means this is air or vacuum, you say. Vacuum, they are having the same refractive index, that is 1. Okay. So can I say in this particular case, we say, sir, sine of theta C is equal to mu R divided by mu D. So we say this is sine of 30 degrees because theta C is 30 degrees is equal mu R. Refractive index of this medium is 1. So that is 1 divided by mu D. Okay, divided by mu D. So I can say in this particular case, it is 1 by 2. So this is 1 by 2 is equal to 1 by mu D. So I can write over here mu D in this case is 2. So refractive index of this medium comes out to be 2. It says that a light ray goes from a medium to vacuum. Critical angle is given as 30. Find the refractive index of this medium. We use the formula. We got it 2. Now, what is the speed of light in this medium? So we have to find the speed of light in the medium. So speed of light in any medium is simply speed of light in air divided by refractive index of that medium. Okay. Now we say V is equal to C. What is the value of C in this particular case? 3 into 10 raised power 8. Speed of light in air is 3 into 10 raised power 8. Divided by refractive index of this medium is 2. 3 by 2 is 1.5. So V is equal to 1.5 into 10 raised power 8 meter per second. This is the speed of light in that particular medium. Yes, very nice. A lot of people have actually given the correct answers. Let's talk about the prism. Let's talk about the prism. See. Guys, listen to me very, very, very carefully. Let's suppose we have got a prism over here. Let's suppose we have got a prism over here. What does prism actually mean? See, what does a prism actually mean? You might have seen this in your school, okay? This is the prism. This is the picture of the prism, okay? So, we say, let's suppose a light ray is entering the prism. Prism has some own refractive index. It is made up of glass. So, we say, let's suppose a light ray is entering the prism, okay? Okay? And this outside is air. So, it is rarer medium. So, this is denser medium inside the prism. Again, when the light comes out, it is again rarer medium. This is what we call the incident ray. And this will be the normal in this case. This is the angle of incidence. So we say when the light ray enters from rarer medium to denser medium, it is bent, we say, towards the normal. See, this is normal. It is bent towards the normal. Okay. This was the actual path. It is bent towards the normal. Now guys, listen to me very carefully. Now this light ray is moving something like this. This will be the angle of refraction. This will be the angle of refraction R1. On first surface, this is what we call S1. This is what we call S1. This is what we call S1. And this is what we call S2, second surface. Okay. Now this light ray goes something like this. This light ray goes something like this. This light ray goes something like this. Tell me one thing. This is denser medium. Now it is moving from denser medium to rarer medium. So when the light ray goes something like this, it will move from denser to rarer medium. Whenever the light moves from denser to rarer, we say it is bent away from the normal. So here on this surface, this will be the normal. This will be the normal. So we say it is bent away from the normal in this particular case. Whenever the light moves from denser medium to rarer medium, it is bent away from the normal in that particular case. See, it is bent away from the normal. Now guys, on surface 1, this is the angle of incidence, this is the angle of refraction. On surface 2, this is the angle of incidence R2. Why, sir? Because for surface 2, this behaves like an incident ray. This behaves like an incident ray. For surface 1, this behaves like an refracted ray. Okay. And for surface 2, this is what we call the refracted ray. Or you also call it the emergent ray. So R2 is the angle of incidence for surface 2, and this E is the angle of emergence, or this is the angle of refraction for surface 2. It is mentioned over here. If this is a prism, prism has its own angle. That is what we call the angle of prism. Okay. And then we say I. What is I? I is the angle of incidence on surface 1. Angle of incidence on surface 1. What is R1? R1 is the angle of refraction on surface 1. Okay. What is R2? R2 is the angle of incidence on second surface, What is E? E is what we call the angle of emergence, or we say angle of refraction on surface 2. And what is this? This is what we call the deviation. This is what we call the deviation. This is what we call deviation. This is what we call deviation. Okay, this is what we call deviation. Okay, because deviation means this was the original path of the light ray. This is the final path of the light ray. How much it got deviated from the original path, that is a deviation. Okay, you have to remember some points in this particular case. Sir, deviation. This deviation will be simply I plus E minus A. What is I? Angle of incidence on surface 1. Angle of emergence minus angle of prism. You have to remember this directly. And if somebody asks you what is the value of angle of prism, we say R1 plus R2 will be the angle of prism. Okay. And now, can we use the Snell's law on the surface 1? Yes, why not? Because light enters from rarer medium to the denser medium. So we can use Snell's law. So if I say I have to use the Snell's law on the surface 1, how can we use it? So can I say mu I sin I? What is mu I over here? That is mu I. Sin I. Sine of I. Okay. And instead of mu I, this is air over here. I'll write for air, it is 1. Or it is 1. Is equal to, we say mu R, that is mu of prism, into sine of, we say, sir, R1. Similarly, we can use over here. Then we say mu I. We say mu I for this is, we say mu for this is, for second surface, this is, we say, angle of incidence. Okay. So mu in this case will be mu, and sine of angle of incidence is R1 is equal to mu R sine of R. Mu R in this case is 1, and sine R in this case is E, sine of E. So this is the Snell's law on first surface, this is the Snell's law on second surface. So you can see it over here. Snell's law on first surface, mu air into sine of I is equal to mu of prism into sine of R1. Snell's law on the second surface, mu of R2, mu into sine of R2 is equal to mu of air into sine of E. Okay. Okay. If you are getting any sort of confusion in this one, I want you guys to watch later on. Okay. Once more. Okay. Now. Come over here. This is a question which we need to solve in this particular case. Find R1, R2, E and deviation. Okay. We are given a prism over here. This is the angle of incidence. I is given as 45. Okay. And angle of prism A is given as 75. This will be the light ray will go something like this, and afterwards it will go something like this. So this will be the deviation. Okay. And this will be R2, this will be R1, this will be angle of emergence. Okay. Now tell me one thing. If we have to find in this particular case, R1, R2, E. Let's find first R1. How do we find R1 in this particular case? See, use Snell's law on S1. Let's call this as surface 1. This is surface 2. Apply Snell's law on surface 1. Okay. If we use the Snell's law on surface 1, listen to me very carefully. What do we say? Sir, mu I, this is air over here. That is mu I is 1. Sine of I, then we say, sir, sine of 45 is equal to mu R. That is the refractive index of the prism, that is given as a √2 into sine of R1. I can write sine of R1. So sine 45 is 1 by root 2 is equal to root 2 sine of R1. Root 2 into root 2 is 2. So sine of R1 is coming out to be 1 by 2, means R1 will be 30 degrees. If R1 is 30 degrees, tell me one thing, my dear friends, if R1 is 30 degrees, if R1 is 30 degrees, can I say, sir, as angle of prism A is equal to R1 plus R2. Okay, angle of prism is R1 plus R2. Angle of prism in this case is given as 75. R1 we got as 30 minus 30 is equal to, we say, sir, R2. 75 minus 30 is how much? That is 45. So 45 degrees, we say, sir, R2. Okay, we got R2. Let's find the angle of emergence. How to find angle of emergence? Use Snell's law. Snell's law on surface 2. So how do we use Snell's law on surface 2? We say, sir, what is that? That is mu I sin I. In this case, what is the value of mu I? What is the value of mu I? That is root 2 sine of I. That is sine of R2. That is sine of, what is the value of R2? That is 45 is equal to. Then we say from this side, mu R. What is the value of mu R? That is 1. And then we say sine of R. Sine R in this case is E. So then we say sine of E. Okay. Sine 45 is 1 by root 2. This is root 2 into 1 by root 2 is equal to sine of E. Root 2 that is 1. So sine of E in this case is 1. E will be 90 degrees. When is the value of sine as 1? When theta is 90 degrees. Now tell me deviation. If we talk about the deviation, sir, we recently saw the value of deviation is I plus E minus A. So I can write over here that this deviation is I plus E minus A. So what is the value of I? I is 45 plus E is 90 minus 75. This is 60. So deviation is 60 degrees. I hope this is crystal and clear. Okay, also remember this. This is the graph between deviation and angle of incidence. Remember, my dear friends, if somebody asks you to plot the graph between deviation and angle of incidence, this will be the graph. Tick. Okay. Now in this particular case, you can see, sir, minimum deviation is over here. Minimum deviation is shown in the graph over here. Minimum deviation will be, remember this, when value of angle of incidence is equal to angle of emergence. Whenever you see angle of incidence is coming out to be equal to the angle of emergence, in that case, we say deviation will be minimum. And we say when R1 is equal to R2 is equal to R, then we say deviation is minimum. Directly remember this. Sir, when is the deviation minimum in case of the prism? We say, sir, when I is equal to E, R1 is equal to R2 is equal to R. And in that case, we say, sir, R will come out to be A by 2. Why? Because we say, sir, A is equal to R1 plus R2. So both are equal. So R1, R plus R, that is 2R is equal to A. So R will be simply A divided by 2. That's what I mentioned over here. And deviation will be 2I minus A. Why? Because we say, sir, deviation is equal to simply I plus E minus A. Both I is equal to E. So I plus I is 2I. So it becomes 2I minus A. Okay. Let's suppose a refractive index of the prism. If somebody asks you to find the refractive index of the prism, this is the formula which you will be remembering directly. That is mu is equal to sine of A plus minimum deviation. A is the angle of prism. A is, we say, angle of prism. Okay. And this is the minimum deviation, delta, minimum deviation divided by 2 sine of A by 2. This is the formula which you will be using in order to find the refractive index of the prism. Okay. 60-degree prism has √2 angle of incidence. This is your homework, okay? Let me know the answer of this question in the comments. I'll show you this particular question. If the angle of minimum deviation in this particular case is 60 degrees, so minimum deviation in this case is how much? 60 degrees. For an equilateral triangle, if we say, sir, the triangle is something like this, means this is a prism, equilateral prism. So in this case, angle will be 60 degrees. Because for an equilateral triangle, theta is 60 degrees. Okay, so we say angle of prism in this case will be 60 degrees. Okay, minimum deviation is also 60 degrees in this case. Then the refractive index of the material will be, we have to find the refractive index of the prism. Which formula you will be using? You will use this particular formula, that is sine of A plus, I'll write over here, sir, mu in this case will be sine of, we say A plus minimum deviation divided by 2 upon sine of, we say A divided by 2. Now tell me, we say, sir, sine of A. What is the value of A in this case? That is 60 plus. What is the value of S minimum? Sorry, this is delta minimum. That is 60 by 2. That is 30. Divided by sine of A by 2. That is 30 over here. Just put up the values and solo. You'll get the answer in this particular case. Is this crystalline clear? Everybody in the chats, let me know, guys. Is this crystalline clear? Yeah, √3 should be the answer in this case. Great. Okay. Let's talk about the dispersion of light. Let's talk about the dispersion of light. Let's talk about the dispersion of light. Guys, break I'll be giving at 1:30, okay? Let's talk about the dispersion of light. What does dispersion of light actually mean? We say it is the process of splitting the white light into 7 different colors, okay? Let's suppose, my dear friends, you have got over here, this is air medium, and you have got some medium over here, okay? Now, my dear friends, you are sending the white light over here, okay? So white light is entering from air to some medium. So we saw that this light is divided into 7 different colors. This one, violet, blue, green, yellow, indigo, red. Okay. This is violet. Okay. Okay. Now see, we said divided into 7 different colors. VIBGYOR. Okay. Okay. Tell me, is this clear? Is this clear? So the splitting of white light into 7 different colors, okay? Violet, indigo, blue, okay? Everybody in the chats. So we say when a white light is divided into 7 different colors, we say that's what we call the dispersion of light. Like you have the prism over here. White light is entering the prism. You can see, sir, violet. You can see indigo, you can see blue, you can see green, you can see yellow, you can see orange, and you can see red. Or I always get confused in this one. VIBGYOR, VIBGYOR, VIBGYOR. Okay, this is the. So we say, okay, violet, VI, indigo, okay. Green, blue, 1, 2, 3, 4, 5, 6. It is 6 only. So make 7th one over here. Make 7th one over here. That's why I got confused. It's 6 made over here. So we say the splitting of white light into 7 different colors is what we call, we say dispersion. We say dispersion. Okay. Now, my dear friends, in this particular case, if we talk about the prism more specifically, let's suppose we have got the prism over here, okay? You are sending the white light in the prism. It gets divided into, splitted into 7 different colors, okay? Now I'll not make all the 7 colors. I'll make the 3 colors only. First one I'll make over here. This is violet. Okay. Then I'll make this is yellow, and then I'll make this is red. Guys, see, this white light is divided. First, it goes from air to this medium. So it is splitted. It is splitted like this. This is the first color, violet. Then you have yellow, and then you have red. I'll take only 3 over here. Then once again, it moves away from the medium, away from the medium, away from the medium. Guys, can I say this was the actual path of the white light? Yes, sir. Now, tell me one thing. This is the violet. Can I say, sir, this violet light has been deviated by this amount? Yes, by this angle. So that is delta V. Delta V is what? Delta V is basically the deviation. This is the deviation. This is the deviation. Deviation of, we say, okay, this is delta Y is the deviation of yellow light. Delta V is the deviation of violet light. Delta R is the deviation of we say sir red light. Okay. And if somebody asks you, what is this, my dear friends? What is this, my dear friends? Between red light and yellow light, sorry, between red and violet, what is this theta? This theta is what we call the angular dispersion. This theta is what we call the angular dispersion. Okay. So, and this theta will be equal to, see, this is whole angle minus this angle. That is delta V minus delta R. Let's suppose this much is 60 degree. This is 30 degree. So 60 minus 30 will be this 30. So this is what we call the angular dispersion. Angular dispersion. Okay. 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 And my dear friends, remember over here, what I'm trying to say is that if somebody asks you, find the value of this delta V, how much violet got deviated from its original path, you say mu V minus 1 into A. A is the angle of prism. Sir, what is this mu V? Mu V, listen to me very carefully. Mu V will be the refractive index of this light. Reflective index of this color. Refractive index of this color. Mu R is the refractive index of this red color. Mu Y is the refractive index of yellow. So I say delta V, if you have to find the deviation of this violet, you'll say, sir, refractive index of violet minus Y into A. Refractive index of red is, deviation of red is refractive index of red minus 1 into A. Okay. Okay. And guys, this theta you can also write refractive index of violet minus refractive index of yellow, red into A. A is the angle of prism. A is the angle of prism. One more important thing I just want to tell you over here. What is that? That is mean deviation. What does mean deviation actually mean? What does mean deviation actually mean? Mean deviation is simply. Sir, where does this concept come from? Don't go over there. Mean deviation is simply refractive mean refractive index. That is mu mean minus 1 into A. A is the angle of prism. Sir, how to find this mu mean? See, mu mean you can simply find refractive index of violet plus refractive index of red divided by 2. If somebody asks you to find the mean deviation, how to find the mean deviation? We say, sir, that is mu mean refractive index of mean minus 1 into A. So how to find the mu mean? That is mu V plus mu R divided by 2. One more important concept, that is dispersive power. What does dispersive power mean? Dispersive power says how much a material is able to disperse the light. If I say over here, listen to me very carefully. This prism is able to disperse the light more. Dispersion in this case is more. So we say in this particular case, dispersive power of the material is more. Dispersive power is equal to theta divided by mean deviation. What is theta? Theta is the angular deviation, angular dispersion. If this angular dispersion comes out to be more because of some material, we say that material has more dispersive power. That material has more dispersive power. That material has more dispersive power. Okay, that material has more dispersive power. Okay, So how to find this dispersive power? Sir, theta. What is theta? Theta is angular dispersion divided by mean deviation, divided by mean deviation. Theta is angular dispersion divided by mean deviation. Okay. You can also write it something like this. Okay. Dispersive power. Directly remember this point. Okay. Okay. I hope this is crystal and clear. I hope this is crystal and clear. Let me show you the question on this particular case. Let me show you the question on this particular case. It is saying that compare the powers of two prisms if one of them deviates the violet and red light by 10 degree and 6 degree. Let's suppose we have got the prism 1 over here. Let's suppose we have got the prism 1 over here. This is the prism 1 that we have. Okay. And this prism deviates the red light and violet light by 10 degrees. Okay. 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 We are supposed to find the value of dispersive power. If this is the prism 1, P1. Can we say, sir, dispersive power is simply, sir, that is angular dispersion upon we say, sir, mean deviation. Okay. Let's first find angular dispersion. How to find angular dispersion? Sir, we recently studied the formula for angular dispersion. What is that? What is that? That is S deviation of violet minus deviation of red. Deviation of violet minus deviation of red. In this case, it says that when one of them deviates violet by 10 degrees and red by 6 degrees. So deviation of violet minus deviation of red. So can I say this will be 10 minus 6, that is 4? Yes. Now, how to find the mean deviation in this particular case? Mean deviation will be, guys, I told you the formula for mean deviation. Come over here. How to find the formula for mean deviation? Sir, this is the formula for mean deviation. Remember one more formula for mean deviation. Sir, mean deviation also we can find deviation of violet plus deviation of red divided by 2. Arey yaar. Divided by 2. Okay. This is also the formula for mean deviation. Okay. So we say, guys, if you are getting confused in this case because there are so many formulas, you have to remember all of these. So I can simply say, sir, deviation of violet plus deviation of red divided by 2. So I can say this will be deviation of violet is how much? That is 10 plus 6 divided by 2. 16 by 2, that is 8. 16 by 2, that is 8. Okay. Now find the dispersive power. That will be simply theta divided by mean deviation. So what is the value of theta in this case? That is 4 by 8. That is 1 by 2. Similarly, you can find for the next prism also. You can find for the prism 2 also, which deviates the violet by 8 degrees and deviates red by 4.5 degrees. You can find for this one. Refraction. Refraction at spherical surfaces. Refraction at spherical surfaces. Let's suppose we have got a spherical surface over here. Okay. Guys, previously I told you the refraction at the plane surfaces. Like this was a plane surface over here. This was a plane surface over here. Okay. And the light were falling on this plane surface and then it got refracted something like this. Now, right now we will be talking about the refraction in case of plane surfaces. Let's suppose you have got this plane surface, this spherical surface over here. Now guys, in this particular case, if I say object is placed at this point, the light ray will leave from the object, okay? If it was the case of refraction, it would have refracted something like this. But this is not the refraction, this is the refraction. In case of refraction, we say the light will move from one medium, which has refractive index mu I, into the another medium. See, it goes from one medium to another medium. This has got the refractive index of mu R. Now, if I say this refracted ray will meet at this point, so the image will be made at this particular point. This is the image at this point. If object is at a distance u, we say, let's suppose image will be at the distance v. V is the position of image, u is the position of the object. Okay. And we know, sir, this sign conventions here also will be same. Sign conventions here also will be same. So we say this is the direction of incident rays. We say this is the direction of incident rays. The direction of incident rays is taken as positive. So this will be positive side, this will be negative side. Okay. So my dear friends, you have to remember one formula in this particular case, which will help you to find the position of image object, position of image over here. What is that? Sir, that is like in case of plane mirrors, we were having 1 by V plus 1 by U is equal to 1 by F. Here we have the formula, this one. Mu R, refractive index of that medium in which refracted rays are present, divided by V, divided by V. V is the position of the image, minus mu I, refractive index of that medium in which incident rays are present, divided by U, U is the position of the object, is equal to mu R minus mu I into divided by, we say R, divided by, we say R. Okay, R is the radius of curvature of this one, radius of curvature of this one. And here, if you have to find the magnification, how much image has become bigger, we say magnification, we can simply find in this particular case, that is V divided by mu R upon U divided by mu I, U divided by mu I. Okay, if somebody asks you to find the velocity, if somebody asks you to find the velocity of the image with respect to the spherical mirror, so this will be the formula to find the velocity of the image in this particular case. That is V square by U square. Let's suppose if I say object is moving with some velocity, you have to find what is the velocity of image in this particular case. We say V square by U square. Then we say mu I divided by mu R into velocity of object with respect to the mirror, with respect to the spherical mirror. You need to keep all these formulas in your mind. That's it. That's it. Okay. Okay. Now let's move on to this one. Given the spherical mirror, given the spherical surface, radius of curvature is 20, mu I is 2, mu R is 3. Find the position of the image. Okay. The question on the same concept. You guys are supposed to tell me the position of the image in this particular case. Can you tell me what is the position of the image in this particular case? Can you tell me? See. How do we solve this particular question? Guys. See, I have got an object in this particular case. Okay, this is the object over here. Object is placed at, we say 15 centimeters. Okay. Listen to me very carefully. Listen to me very carefully. I say, sir, this will be the direction of incident rays. The direction of incident rays is considered as positive. So this will be positive side, this will be negative side. Can I say in this case, sir, U is equal to minus 15 centimeters, 100%? Okay. Okay. And if we have to find the position, we are supposed to find the V. We are supposed to find V. Which formula we'll be using? Can we use this formula? Mu R by V minus mu I by U. We say, sir, mu R by V minus mu I by U is equal to mu R minus mu I divided by, we say, sir, R. R is the radius of curvature. R is the radius of curvature in this particular case. Okay. Radius of curvature in this case is given as 20. And that radius of curvature in this case will be considered as positive because that will be from this side. So R in this case is, we say, sir, plus 20. Okay. That will be plus 20. Now tell me, mu R, refractive index of that medium in which refracted rays are present. So that will be this side, this side. Incident rays will leave from this side and they will enter the this portion. So we say in this case, mu R is 3 divided by V minus mu I. What is the value of mu I? That is 2 divided by, what is the value of U? That is the position of the image, that is 15, is equal to, what is the value of mu R? Mu R in this case is, we say, sir, 3 minus 2 divided by radius of curvature is 20. Radius of curvature is 20. So V in this case will come out to be minus 36. V in this case will come out to be minus 36. Is this clear? I hope this question gives you the proper feel of the previous formula, of this formula. If refraction takes place at the spherical surfaces, how do you find the position of the image object? Okay. Now let's talk about the lenses. Let's talk about the lenses. Let's talk about the lenses. Guys, like this session because that's mandatory. Let's talk about the lenses. If we have got a thin lens over here, don't say thin lens, let's talk about the lenses simply. We say a lens is made up of two surfaces in which refraction takes place. Okay. Now see, I'll tell you. If I have to make a mirror over here, spherical mirror, you will say, sir, this is a spherical mirror. This is a surface. This is the surface of spherical mirror. Okay. My dear friends, I am saying join one more mirror to this particular surface. So this has got surface, let's suppose S1, this is, we say, sir, S2. And this surface has a radius of curvature, let's suppose R1. This will have radius of curvature, let's suppose R2. So this is what we call the lens. And more specifically, if I say, I say this is what we call the biconvex lens. Because why do we call it the biconvex lens? Because this outer side is what we call the convex side. Okay, this I have told you before, this is convex side. Now let's suppose I have got over here this mirror. Let's suppose I have got surface something like this. Okay, and the person is looking at the surface from this side. Can I say, sir, this will be concave side, and I'll take one more concave side and I'll join these. Okay. So now two surfaces, concave surfaces. See, from the outer side, this is the concave side. This is the concave side. So we say this is biconcave lens. This is biconvex lens. This is biconcave lens. Okay. That's what is mentioned over here. Concave lens, convex lens. This has got radius of curvature R1. This has got radius of curvature R2. Lens maker's formula. Now see, what does lens maker's formula say? Like you have the mirror formula over there. Okay. Similarly, we have the lens maker's formula. What was that? 1 by V plus 1 by U is equal to 1 by F. Okay. So we say, my dear friends, listen to me very carefully. Here, we have lens maker's formula in case of the lenses. Directly, you have to remember this. You don't have to confuse yourself. Whatever I say, just follow it. We say, here we have the lens maker's formula, which helps us to find focal length, okay? Focal length of the lens, which helps us to find position of the object, which helps us to find position of the image, everything. Okay, like let's suppose I'll show you the question. The question in this case is given as, I am giving a lens over here. This is the lens, biconvex lens. The radius of curvature of this surface is 30. Radius of curvature of this surface is 60. Okay, this is the incident ray. It is saying that find the focal length of this particular lens. Which formula I'll use? Shall I use the mirror formula or shall I use the lens maker's formula? I say I'll use the lens maker's formula. What is that? This is the lens maker's formula. 1 by V, V is the position of the image, minus 1 by U, U is the position of the object, is equal to mu L by mu S. What is mu L? My dear friends, if I say I have got a lens over here, this lens has the refractive index, that is mu, what we call mu L. And this surrounding has refractive index, that's what we call mu S. Mu L by mu S, okay, minus 1. Then 1 by R1 plus 1 by R2. R1 will be the radius of curvature of this one, R2 will be the radius of curvature of this one. Or you can also write it something like this, 1 upon F is equal to mu L divided by mu S minus 1 into 1 by R1 plus 1 by R2. So these two formulas help us to find the focal length, position of image, position of object. Simply you will remember it. Okay. And in this particular case, if somebody asks you to find the magnification also, this is the formula to find the magnification. Sir, magnification of the image, you can say, sir, that will be V by U. Either you say V by U, or in terms of focal length and position of the object, F upon F plus U, or you can also say F minus V upon, we say, sir, F, focal length and position of the image. These are all the formulas of magnification in case of lenses. Okay. And To find the velocity of the image, if I say, my dear friends, let's suppose I have got a lens over here. I have got a lens over here, and there is an object, which is moving parallel with to find the parallel component of the image, velocity of the parallel component. I say, let's suppose this object has some velocity in this particular case. My dear friends, this is the formula by which we can find the velocity in that particular case. That is v square divided by u square into velocity of the object with respect to the lens. Velocity of the object with respect to the lens. This is the parallel component. If I say this is the mirror, something like this, object is moving something like this, parallel to the mirror, parallel to the lens. Let's suppose image is also moving something like this for a second, I would say. How to find the velocity of this image? We'll use this formula, Similarly, perpendicular component of the velocity of the image. So we say, sir, perpendicular component will be, let's suppose this is velocity of the image's object is this. Okay, so in that case, you will be using this particular formula. Simply, guys, I'm repeating the things which I have told you before. I'm repeating the things. To find the velocity of image parallel component, to find the velocity of image perpendicular component, we use this formula and we use this formula. Is that clear? Is that clear? Let's talk about this particular question. Let's talk about this particular question. Is this clear, guys? Let me know in the chats. Everyone with the fire emojis. Everyone with the fire emojis. All the people out there, let me know. Calculate the focal length. Everybody out there. Everybody means everybody. Guys, let me know in the chats if this is crystalline clear. All the people out there. All the people out there. Okay. We have got the lens over here. Let's suppose this is the direction of incident rays. So this side will be considered as positive. This side will be considered as negative. So mu surrounding in this case is 1 and refractive index of lens is given as 3 divided by 2. Radius of curvature R1 is given as 30 centimeter. R1 in this case is given as 30 centimeter. Now the question is, shall we take this positive or negative? Guys, radius of curvature of this lens, that will be from this side. Radius of curvature of this lens, that will be from this side. So from this side, we take positive. This is the positive side. So this is plus 30. So R2 will be then minus 60 centimeter. So radius of curvature of this lens. We are supposed to find the focal length. Which formula we'll be using? We'll use this formula. So this formula is simply, I'll just write over here 1 upon F is equal to mu L by mu S minus 1. I'll write over here, that is mu of lens, refractive index of lens, refractive index of surrounding minus 1. Then we say 1 by R1 minus 1 by R2. I can write it something like this over here. Okay. Now put the values. If I have to find the value of 1 by F is equal to refractive index of lens, that is 3 by 2. Refractive index of surrounding, that is 1. 3 by 2 by 1 is 3 by 2 only. Minus 1. 1 by R1. R1 is given as 30. Then minus 1 by R2 is given as minus 60. That is minus 60. Okay. Okay. And if you solve this, focal length will come out to be, that is 40. Focal length will come out to be, that is 40. Great. Focal length in this case will come out to be 40. Okay. Let's talk about the lens cutting. See, let's talk about the lens cutting. See, let's suppose if this cutting of lens means, let's suppose if you have got the lens over here and you are cutting this lens something like this, okay, in these parts, this one. If we cut the lens parallel to principal axis, if we cut the lens, this will be the principal axis, parallel to principal axis. we say focal length of these parts will remain same. Focal length of these small parts will remain same. If this has f, so these parts will also have f. And if you cut the lens perpendicular to the principal axis, if this has got the focal length f dash, now this part will have the focal length of 2 times of f dash. This will have the focal length of 2 times of f dash. Now, if combination of lenses, if you basically combine different lenses with each other, focal length of this is f1, f2, f3. Now, what will be the net focal length after the combination? This is how you can find the net focal length. 1 upon f equivalent is equal to 1 by f1 plus 1 by f2 plus 1 by f3. Okay. And when it comes to the power, what is, sir? Power of this is P1, P2, P3. What will be the net power? What will be the net power of the lens? So that will be P1 plus P2 plus P3 up to Pn. How many lenses are over there? Okay. Next. If we have got the 2 lenses at some separation, let's suppose at separation D. In this particular case, if somebody asks you what will be the net equivalent focal length over here, in this case, if somebody asks you what will be the equivalent focal length, you say simply, sir, equivalent focal length in this case will be 1 by f equivalent is equal to 1 by f1, focal length of this one, plus 1 by f2, focal length of this one, minus d upon, d is the separation between the two, f1, f2, d upon f1, f2. All of these you guys have to remember. Now let's start the optical instruments. It is 12:56. 1:30 I'll give you the break, okay? At 1:30 I'll give you the break. We'll finish optical instruments in next 30 minutes. We'll have to finish it. Okay, guys, make sure you like this particular session. Likes are only 1K. I want you guys to increase it. Hit the like button if you have not liked the session. Everybody out there, if you have not liked this session, all the people, like this particular session. Hey, yo. Yes, PDF will be shared to the in the Telegram channel. PDF will be shared in the Telegram channel. Now see, optical instruments. In case of optical instruments, the first instrument is basically simple microscope. We say, why do we use the microscope? In order to see the very small things. If you can't see the small things with the help of the normal eye, so you'll use the microscope, okay? So small microscope is this one that you might have seen this at your schools, okay? That small, we call it in normal language, we call it the lens, okay? So we say, sir, this lens I'm using, that will be the simple microscope, okay? So it is mentioned over here. The work of simple microscope is to magnify the things, If you have got the small things, it magnifies those things so that you can see those very clearly. Okay. To make us see small things large, to make us see small things large. Okay. If we want to see an object with our normal eyes, it should be at least placed at 25 centimeters. My dear friends, if I say I have to look at this pen, I have to see this pen very clearly, you will say, sir, place it very close to my eyes. Do you think that I would be able to see it? No. So at least it should be at what distance? We say minimum distance should be 25 centimeters. If you place it at 25 centimeters, I would be able to see it properly. This 25 centimeters, it is called least distance of distinct vision. Least distance of distinct vision. Okay. Least distance of distinct vision. Okay. 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 Now listen to me very carefully, my dear friends. Let's suppose you have got an object over here. You have got an object over here. Okay. And this object is small. This object is small. This object is small. Okay. And you want to see this object, but with the help of your normal eyes, you are not able to see it. Okay. So what will you do? You will use the simple microscope. You will use the simple microscope. Simple microscope means this lens. Sir, what is this? This is simple microscope. This is simple microscope. This is simple microscope. This lens over here. Now, my dear friends, if this is a simple microscope, in front of this particular lens, you will place this object. Now. This is your eye. This is your eye. Your eye is looking at this particular object. Directly, whatever I say over here, do not use your mind. Whatever I say, just keep on remembering that. Okay. If you have to see this particular object, what will you say, sir? You will use the lens over here. So when you place the lens in front, you have this object, you place the lens in front of this object. Now, there are two cases. What is that? Image of this object will be formed at infinity by the lens. Means sometimes you would have experienced this. If you are placing the object in front of you, you place the lens, you observe that the image of the lens is made at very far. It looks like the object is placed at very far distance, but in reality it is close. It looks like it is very far. After you remove the lens, hey, it is close, bro, it is close. So when you place the lens, it looks it is far. So that's what it is saying. Image at infinity. Image of this object is placed at infinity. So my dear friends, what we are saying that we are placing an object over here on the focus. Okay, this is the lens, this is the focus, this is the focus. Now, we say the light ray is basically going something like this is the incident ray, this is the incident ray. After refraction from the lens, it will go something like this. It will be refracted. This will go something like this. Now, these two light rays are parallel to each other. These two light rays are parallel. They are parallel. So, we say parallel rays meet at infinity. Parallel rays meet at infinity. If the two light rays meet at infinity, listen to me very carefully. So, we say, and these are the refracted rays. Sir, that point where refracted rays meet, image will be that point. That image will be made at that point. So if they are meeting at infinity, so can I say image formed by lens at infinity? Yes, image will be formed by lens at infinity. And my dear friends, magnification, how much magnified it has done, how much magnification it has done in case of image, that will be D divided by F. D divided by F. Sir, what is D? D is least distance of distinct vision. What is F? F is the focal length over here. This will be the magnification in this particular case. I hope this is crystal and clear. Now, the second case. What is that? I have got a lens over here. This is the object. I say image made by microscope or simple microscope at distance D. Now, you are placing the object in front of your lens. Now, you want to see this object close to you, and it should be very big. It should be very much magnified. So, that's why we say image made by microscope at D. Now see, this is the object I have placed over here. Now guys, previously I had kept this object at the focus, but right now I'll not keep it this at focus. I'll place it between optical center and focus, somewhere around over here. Now my dear friends, listen to me very carefully. The light ray will leave from this. This is the incident light ray that I'm making. Now this one is the refracted ray. This is the another incident ray. After this, the refracted ray will go straight, something like this only. Now these two light rays are divergent. They are not parallel. They are divergent. Divergent rays. We say divergent rays never meet, but if you do one thing in this particular case, if you extend this light ray, the point where they meet, that will be the image. No doubt this is the virtual image in this particular case, but the point where they meet, that will be the image. And this image is formed at the distance d, that is least distance of distinct vision. And this image will be much magnified, bigger. Okay. And if somebody asks you, what is the magnification of this? Magnification of this will be 1 plus d by f. See, previously it was d by f. Now it is 1 plus d by f. It is more magnified. Tell me in the chats, is this crystalline clear? Simple microscope is done. Let's talk about the compound microscope. Tell me in the chats. I need to see. Let's talk about the compound microscope. Compound microscope is that microscope. I need to see how many, everyone. Those students also who never comment in the chat box, I want those also to write in the chats if this is crystalline clear. Great. I hope you loved the lecture. Huh? Now see, compound microscope. This is that microscope which you would have seen in the schools. Okay, that microscope. Okay, teachers using the microscope in 10th classes, and we used to go in the lab and we used to say, oh, what is this, bro? This is something amazing. Huh? We want to experience this. And that microscope is over here. So that is what we call the compound microscope. Okay. So we say it has got two lenses. This is the first one. It is what we call the objective. And then we have the next one. This is the bigger one. This is what we call eyepiece. So we say in case of compound microscope, we have got two lenses over here. The first one is objective. The second one is, we say, eyepiece. Now see. In front of the objective, I am placing the object. Let's suppose this is the object. What is the goal in this particular case? We are supposed to magnify the object. We are supposed to see the small things bigger. Now see, if we place the object over here, okay? My dear friends, in this particular case, the height of the object is, let's suppose, h. We say incident light ray will leave from the object. This is the incident light ray. This is the another light ray, okay? Now, after refraction, we say they will meet at the point. So we say image will be formed over here. That is h dash. Okay. This is the image formed because of this lens, objective lens that is over here. Now see clearly, this is the object. The image is magnified. It is bigger than the object over here. And my dear friends, the object is placed at a distance of, we say, u0. u0 is the distance at the position at which the object is placed. Now, this object will behave, listen to me very carefully. This object will behave like this is the image. This image will behave like an object for eyepiece. I'll write over here. H dash will behave like an object for eyepiece. Okay. Now tell me in this particular case, if this behaves like an object for this eyepiece, already once magnification has been done by the objective. Now this will do the second magnification. It will make it more bigger. Now see, guys, The light ray will leave from this particular object something like this. This is the first light ray, and then another light ray something like this. These two light rays are parallel, and we say if parallel light rays never meet, they meet at infinity. So we say in this case, image at infinity. Image will be formed at infinity. Image will be formed at infinity. Now, this is the compound microscope. That case in which image is formed at infinity. Image is formed at infinity. So, my dear friends, what I was trying to say, first, this lens will magnify the image, then this lens will magnify the image, but it will make the image at infinity. It will make the image at infinity. And if I say total magnification in case of compound microscope, you say total magnification will be magnification done by the objective lens multiplied by magnification of the eyepiece. Magnification of the eyepiece. Okay, that's why I told you twice magnification takes place over here. That is magnification of objective multiplied by magnification of eyepiece. So MT is, what is the magnification of the objective? Tell me, guys. Sir, magnification of the objective, will directly remember that is V0 divided by U0. What is V0? I told you V0 is the position of the object. U0 is the position of the object. V0 is the position of the image, this image, the first image over here. Okay. Multiplied by ME, magnification by eyepiece, that is D by F. Why did I write D by F? Because eyepiece is simply this, you can consider as eyepiece over there. So because of the eyepiece, if image is made at infinity, magnification is D by F. Same is the case here. Image is made at infinity. So because of this magnification, I am writing D by F. So directly you will be remembering. If in case of compound microscope, somebody asks you to find the magnification, you say V0 by U0, D divided by F. This will be the magnification when image is made at infinity. And in this case, somebody asks you to find the tube length also. What is tube length? Tube length means this distance between the two lenses. That is V0 plus Fe. This is the focal length of this, and this is the V0. V0 plus Fe is the tube length. V0 plus Fe. Next, case 2. If we want to magnify the final image at distance D, we want to magnify the image, but the image should be made at distance D, not at infinity. Image should be made at distance D, not at infinity. Let me show you how. Let's suppose we have got the objective over here. This is the objective we have got over here. This is the eyepiece we have got over here. This is the object. This is the object. Listen to me very carefully. Guys, previously, listen to me very carefully. We say, sir, this is the object. Incident rays will leave. After refraction, they will meet here. The image will be formed. Remember, this image was formed at focus of eyepiece. If I say image does not form at focus, if image is formed at focus at eyepiece, then only light rays become parallel. This H dash is at focus of eyepiece. Okay, I'll write over here. H dash is at focus of eyepiece. Now come over here. In this particular case, this is the object. Light ray will leave from this object. Light ray will leave from this particular object. After refraction, they meet at this point. After refraction, they meet at this point. But right now, the focus of this is not over here. That is exactly at this particular point. Okay, so this image is not made at focus. If the image is not made at focus, we say the light ray will leave from this image something like this. Another light ray will go something like this. Okay. Another light ray will go something like this. Okay. Now, if you extend these two, see, these are the divergent. They can't meet from this side. If you extend these two, they will meet at this particular point. Now, this will be the final image. This is the first image made by objective. This is the second image made by this. Now see how much bigger this is than the object. H double dash is the final image. Final image. H double dash is the final image. H double dash is the final image. Okay, and it is magnified over here by a large amount, So we say in this particular case, remember my dear, what you have to learn in this case, what I'll tell you. When magnification is done in case of compound microscope, but the image is made at D, in that case, magnification will be simply this much. This will be the magnification. That is magnification of objective into magnification of eyepiece, that is V0 by U0 into 1 plus D by F. Why do I write 1 plus D by F? Because if you come over here, when the image was made at D distance, what was the magnification of this lens? 1 plus D by F. That's the reason I have put up over here, magnification of eyepiece as 1 plus D by F. Simply, you guys remember, when image is made at distance D, in case of compound microscope, this will be the magnification. Directly. Like you have got this particular question over here. Can you solve this particular question? Can you solve this? A compound microscope has an eyepiece of focal length as, see, into FE. This is focal length of eyepiece. A compound microscope has an eyepiece of focal length 10 centimeter. FE in this case is given as 10 centimeters. Okay. And objective of focal length 4 centimeter. Focal length of objective is 4 centimeter. Okay. Calculate the magnification if the object is placed at distance 5 centimeter from the objective. So U in this case is given as 5 centimeter. So that the final image is made at the least distance of distinct vision at D is equal to 20 centimeter. So we are supposed to find the magnification in this particular case. What is the formula for magnification in case of compound microscope? If the image is made at distance D, we say, sir, the formula is simply M is equal to, see, we recently studied V0 by U0 into 1 plus D by F. That is V0 divided by U0 into 1 plus D divided by F. FE. Guys, tell me one thing. D is given over here. FE is given over here. U is also given 5. You are supposed to find V. How do you find the value of V in this particular case? We say, sir, in this particular case, as if we have to find V, we say 1 by V minus 1 by U is equal to 1 by F. In case of length, we use formula like this. Okay. Now tell me in this particular case, can I say, sir, 1 by V is equal to 1 by F minus 1 by U? Now tell me, sir, directly if we cross multiply over here, this will be U into F upon, this will be U minus F upon, I'll say something like this. See, this is 1 upon V is equal, this is U minus F upon U into F. Now do the reciprocal. V is equal to U into F upon U minus F. If you take it over there, it will become plus, plus, plus. Okay. This is how you are supposed to do it. Okay. How you are supposed to do it. You know the value of U. You know the focal length in this particular case. Just put the values, get the value of V, put in this particular equation and get the magnification. Is this crystalline clear? Tell me everybody in the chats. Magnification in this case has to be 12. V has to be 20 in this particular case. V should be 20 in this particular. Yes, magnification should be 12. Is this clear? Tell me. Tell me everybody. Okay. So V in this case will come out to be, we say, sir, 20. Then if you put the value V, U and everything over here, magnification will come out to be how much? How much? You check this one. This will be 12. 12. Telescope. Let's talk about the telescope. Let's talk about the telescope. Sir, what does telescope mean actually? We say, sir, when it comes to the telescope is that device which is used to see those objects which are placed at very large distance. Used to see those objects. Used to see those objects placed at very large distance. Very large distance. Used to see those objects which are placed at very large distance. Okay. Now, in this particular case, we have got objective, but in this case, objective is bigger and eyepiece is smaller. Eyepiece is smaller. Now, see, we say, sir, if you have to look at the object in this case is at very large distance, means at infinity. You are seeing an object, you are seeing Mars, you are seeing any other planet. Okay. Okay. So they are placed at very large distance. So if the object is placed at infinity, very large distance, so the light rays come from that object are parallel. Yes, sir. And why do we make this objective bigger? So that it can catch more and more rays from that particular object. Okay. If it catches more rays, it will make the image which is brighter and clear. It will make the image which is clear and bright. Okay. It will make the image clear and bright. Okay. Okay. Now, my dear friends, if the light rays are something like this, now these light rays, when basically enter this objective, after refraction, they all meet at this particular point. This is the focus of this objective. It has bigger focus because its size is bigger. Okay, so they all meet at this particular point. So this will be the image formed at this particular point. Now, my dear friends, we say if the image is formed at the focus of the eyepiece. Now the light rays, this image will behave like an object for this eyepiece. Light ray will leave from this image, something like this. They will go parallel. So we say, sir, in this case, final image is made at infinity. Here also, final image is made at infinity. Final image is made at infinity. Here also, final image is made at infinity. See, guys, if you are looking at the star, let's suppose you are looking at some planet. Does it look like in microscope it is in front of you bigger? No. It still looks like the image is made at very far a distance. It still looks like image is very far. Okay. Okay. So that's why we say, why does in this case image looks very far? Because the light rays after the second refraction become the parallel. So these are the light rays. They meet over here. They will make the image which is very small. Then these light rays enter the eyepiece. Then they become parallel. So final image is made at infinity. Okay. Okay. Now, my dear friends, if we say image is made at infinity in this particular case, what is the value of magnification? Directly you will remember. Sir, if the image is made at infinity, directly you say, sir, it is minus f naught upon fe. This will be the value of magnification. It is the magnification of image done at infinity. Okay, done at infinity. If the magnification is done at distance d, let's suppose, if you are seeing the final image at distance d, in that case, you will have to remember the magnification, this one, FO minus FO by FE, focal length of objective upon focal length of eyepiece. Then 1 plus FE divided by D, 1 plus FE divided by D, 1 plus FE divided by D. This will be the magnification in that case. Guys, what you guys are supposed to remember in this case is, see, when we talk about the compound microscope, what will be the question? Sir, in case of compound microscope, if we say final image is made at infinity, tell me what will be the magnification. You will say, sir, if final image is made at infinity in case of compound microscope, this will be the magnification. V naught by U naught into D by F. Sir, in case of compound microscope, if final image is made at distance D, what will be the magnification? How big this image will be? Sir, this will be the magnification. And in case of telescope, if we say, sir, final image is made at infinity, what will be the magnification? This will be the magnification. Minus FO by FE. FO is the focal length of objective, FE is the focal length of eyepiece. If in case of telescope, final image is made at distance D, what will be the magnification? Sir, F minus FO by FE, 1 plus FE divided by D. This will be the final magnification. Is this crystalline clear? Is this crystalline clear? Tell me in the chats, my dear friends. Tell me in the chats. Tell me in the chats, my dear friends. वो 20 कैसे आया? See, here, focal length, guys, in case of compound microscope, this is the objective and this is the eyepiece, okay? This is the objective, this is the eyepiece. And we say focal length of, let's suppose I have placed the object somewhere around over here. Okay. Focal length of object is given as 4. And focal length of eyepiece is given as 10. If I'm asking you, where will be the first image made? Let's suppose first image is made at this point. So we are supposed to find the value of this V. How will you find? Sir, U, we know. U in this case is, how much is given? U in this case is, we say, sir, 5. U in this case is, let's take this separately. U in this case is, we say, sir, 5 centimeter. Focal length is 4 centimeter. Okay. Now, this is the direction of incident rays. Incident rays in this case will be considered as positive. Okay. And this is the direction of incident rays. This side will be, sir, positive side. This side will be, sir, negative side. Use the sign conventions. Then use this formula. This one. V is equal to U into F upon U plus F. U is how much? Minus 5 in this case, because this is object is from minus side. Minus 5 into 4, that is 20. And divided by U plus F, final will be 20. Is this clear? Is this clear? Do it later. Okay, this is your homework. This is your homework. Now let's take a break. Next chapter, we will be starting the wave optics. Right over here. We'll be starting the wave optics at 2:10 p.m. Huh? We'll teach EM waves also. Don't worry, okay? We'll teach that in the next marathon. Or if we get the time in the today's marathon, then I'll teach that also. Chill.
So, guys, we are back. We are back to business. Let the people join and we will start the next chapter. That is, we say wave optics. Okay. That is, we say wave optics. Okay. So, guys, listen to me very, very, very carefully. Listen to me very, very, very carefully. No, I said 210. I said 210. The break was till 210. See, it is mentioned over here 210, not 215. So let's talk about this wave optics. Okay, listen to me very carefully. Back in time, there was actually a battle between different number of physicists. Okay, some used to say the question was, is light a particle or a wave? Is light a particle or a wave? This was actually the question. Okay, some used to say this light is a particle, and some used to say this light is a wave. Okay, so the different number of physicists, listen to me very carefully. The first one was basically the Newton. He gave this corpuscle theory. Okay, so it was Newton. He gave this corpuscle theory. In this corpuscle theory, what did he actually say? What did he actually say? He said basically light is made up of small particles, okay, known as corpuscles. So at that point of time, Newton came up with a theory. He said this light is basically made up of, we say small particles, tiny particles. Those particles are called corpuscles. Okay. And then came basically the Huygens. Huygens actually said this light is a wave. Huygens said light is a wave. Okay. He gave some proofs. Newton also gave some proofs. So people were actually basically in between the two. Shall we consider this as a particle or a wave? Then finally, Young's double slit experiment, YDSE. We said this experiment clearly proved light as a wave. Okay. So there was no second thought afterwards. The light is not a wave. We say this experiment clearly proved that light is a wave. And after some time came the photoelectric effect. This clearly proved light is a particle. This clearly proved light is a particle. Young's double slit experiment clearly proved that light is a wave. This clearly proved that light is a particle. We'll have to study Young's double slit experiment also today. We'll have to study photoelectric effect also in the today's class only. Okay. So my dear friends, so these were basically the things that used to happen before. First Newton came, he said light is a particle, okay? So he gave a corpuscle theory. Then Huygens principle, okay, Huygens wave theory. Then YDSE, this experiment was performed here. Clearly it was proved that light is a wave. Then photoelectric effect was performed. This clearly proved that light is a particle. But in this particular case, here in case of this particular chapter, wave optics, we consider light as a wave. Here we consider light as a wave. In this chapter, we consider light as a wave. In this chapter, we consider light as a wave. Now listen to me very, very, very carefully. Let me make you understand the first concept, that is we say Huygens principle. This is we need to understand. Let's suppose we have a bucket over here. We have a bucket over here. In this bucket, this drop is falling. This drop is falling into the bucket of water over here. Don't you think that, sir, when this drop falls into the water, sir, these waves will basically move something like this? When water drop falls into the bucket, so kind of waves are being produced in this case. Yes. So this wave is being produced which moves forward over here. This is the side view. This is the side view. If you look at the top view, when this drop falls, we say, sir, it looks something like this. These waves are basically traveling in the forward direction. These waves are basically traveling in the forward direction. So this is what we call, we say wave fronts. Wave fronts. This is what we call wave fronts. Okay. This is what we call wave fronts. Okay. So these are the wave fronts which are being pushed in the forward direction. These are the wave fronts which are being pushed in the forward direction. Okay. Now, my dear friends, this is the example of the water. If the water drop falls into the water, then we say those wave fronts are moving forward. Okay. Now we say same is the case in case of a light source. If we say we have got a light source over here, okay, so it will also produce the same wave fronts over here, and those wave fronts are basically moving forward. This is the example of water. You will get the complete clear feel with this particular example. But in case of a light source, if you have got a bulb over here, light over here, that also produce the wave fronts, those bumps, these bumps, okay, and these bumps move forward. Okay, in case of the light source. Now, my dear friends, let's suppose I am taking a light source over here, or this is that water droplet, first droplet, or either you say light source, okay. My dear friends, this first drop, we say, this is what we call the source particle. This is what we call the source particle. The source particle disturbs the neighboring particles. Don't you think that when this drop falls into the water, it disturbs the neighboring particles? Okay, it disturbs the neighboring particles. So they will now start oscillating. That's the reason this wave travels in the forward direction. Okay, same I am telling you over here. This is the source particle. So this source particle disturbs the neighboring particles. These are the neighboring particles over here. And these neighboring particles are we called secondary wavelets. Okay. Now, my dear friends, when this transfers the energy to the neighboring particles, okay, we say now these will start oscillating. Now, if we join these particles with a tangent, with a line, with a tangent, so this tangent is what we call the wave front. This tangent is what we call the wave front. So what actually is the case? We say, sir, this is the source particle. This source particle disturbs the neighboring particles. Like this is the neighboring particle over here. This is the neighboring particle over here. One more neighboring particle, one more neighboring particle. So it disturbs these neighboring particles. And if we join these neighboring particles by a line, by a tangent, this tangent is what we call the wave front. This tangent is what we call the wave front. Okay, so for us, it looks like this is the wave front moving forward. This is the wave front moving forward. Okay, now, my dear friends, similarly, we say if we join this with a common tangent, it is called the wave front. Okay, now, my dear friends, we say these particles, these secondary wavelets, they will further displace, they will further disturb their neighboring particles. They will further disturb their neighboring particles. And then if we join those neighboring particles, this is what we call the secondary wave front. This is what we call the secondary wave front. Okay, okay, okay. These secondary wavelengths, these secondary wave, this is what we call the wavelet, and this whole tangent is what we call the wave front. This secondary wavelet will further disturb their neighboring particles and produce waves and produce waves and produce waves. Okay, and produce waves. Okay. Okay, so this is basically the Huygens principle. Huygens principle says that if there is a source particle, this source particle disturbs the neighboring particles which are called secondary wavelets. And if we join those particles, it will form the wave front. And those particles now acts as a source of disturbance for their neighboring particles. And if we join these neighboring particles, they form one more wave front over here. One more wave front. Similarly, these particles will disturb their neighboring particles. If we join those, they will form the next wave front over here. Okay. 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 Cool. Now, let's talk about a concept. That's what we call the path difference. What does path difference actually mean? What does path difference actually mean? See. Let's suppose there is a wave. This is a wave. This wave is leaving from the point A. This wave is leaving from the point A. There is one more wave which is leaving from the point B, which is leaving from the point B. I am simply asking you one question. If let's suppose this wave has traveled from A point to this point 5 kilometers, and this another wave has traveled from point B to this point 10 kilometers. Okay. I am saying that, could you please tell me what is the path difference between the two? You'll say, sir, how much this has traveled? How much this has traveled? Path difference will be 10 minus 5. Path difference in their path. Which one has traveled more? So we say, sir, delta x will be 10 minus 5. That is 5 kilometer. This 10, this 5, 10 minus 5 is 5 kilometer. This is the simple concept, path difference. How much is the difference in their path? Okay. Now comes basically the phase difference. I'll make you understand the phase difference. Phase difference. See. I say, let's suppose we have got one wave. This is a sinusoidal wave. Okay, sinusoidal wave. Okay. Let's suppose we have got a wave something like this. This is a wave. Okay. Like you might have studied the wave equation. The wave, this is the wave, the sinusoidal wave. Okay. The wave travels something like this. Okay. Let's suppose we have got this blue color wave and we have got this yellow color wave. We say both are starting from this zero origin. Okay. Both are starting from this zero. Now goes, this blue color goes and reaches maximum. It reaches maximum at some time. Let's suppose that time is, let's suppose I say over here, this time is, we say, sir, t by 4. This time is t by 4. Can I say in this particular case, yellow wave also reached the maximum at the same time t by 4? Yes, sir. Now, when afterwards, when blue wave becomes 0, when it becomes minimum, we say yellow wave also becomes minimum. Then we say when yellow wave becomes maximum once again from the lower side, okay, we say blue wave also becomes maximum from the lower side at the same time. So we say in this case, the two waves are in the phase. Here, the two waves are in phase. The two waves are in phase. In this case, we say the two waves are in phase. Okay. They don't have any phase difference. In this case, we say, sir, phase difference in this case is, we say, 0. Phase difference in this case. Because when this is minimum, when yellow is minimum, blue is minimum. When yellow is maximum, blue is maximum. Now, let's suppose we have got the two waves over here in this particular case. Sir, this blue wave starts from 0. At that time, yellow wave starts from maximum. It is already at maximum. Now, when yellow wave becomes 0, blue wave becomes maximum. When yellow wave becomes maximum from the lower side, blue wave becomes 0. In this particular case, we say they have a phase difference of pi by 2. In this case, they have a phase difference of pi by 2. They have a phase difference of, we say, sir, pi divided by 2. They have a phase difference of pi divided by 2. Okay.
because when blue is at 0, this is at maximum. Now, similarly, if we talk about this particular wave, we say both the waves are traveling something like this is the yellow wave, okay? And this is the blue wave moving from the lower side, okay? So in this particular case, we say phase difference is 180 degrees. Phase difference is 180 degrees. When this is the maximum from the upper side, this is the maximum from the lower side. We say phase difference is pi by 2. Just a second, guys. Okay, we say in this case phase differences, we say 180. When is the phase difference 0? When both are at maximum at the same time. No doubt, this upper wave has got more amplitude, this has got less amplitude, but they are at maximum at the same time. Okay, okay. Now guys, let's talk about the constructive interference and destructive interference. What does constructive interference actually mean? Let me give you the real life feel. Let's suppose there is a wave coming from this side. This is a wave coming from this side, something like this, okay? And there is a wave coming from this side, something like this. These two waves are actually coming towards each other and they are meeting. So when they meet, let's suppose they meet over here. This has the amplitude A. This also has the amplitude A. When they meet, okay, we say in this particular case, they will form a bigger wave which has got the amplitude 2A, So when the two waves meet and they form the amplitude, we say bigger amplitude, we say, sir, amplitude is bigger in this case. And this is what we call the constructive interference. And this happens when there is zero phase difference. Why? See, because when this wave is maximum, when this wave is at maximum, this wave is also at maximum. So the two maximum waves are meeting. So that's why amplitude is becoming twice. It is becoming bigger. So it happens, we say, sir, when phase or difference is 0. And in this case, we say, sir, net amplitude is, we say 2A. Net amplitude becomes 2A. Or you can understand it something like this. When the crust of two waves, this is what we call the crust. See, let's suppose if we have got a wave, this upper one is what we call crust, this is what we call trough. When crust and crust of two waves meet, the amplitude becomes large. The constructive interference happen. And if we talk about the destructive interference, and in case of the waves, see, these two waves are having the zero phase difference. When this is 0, this is 0. When this is maximum, this is maximum. When this is maximum from the lower side, this is maximum from the lower side. Okay, so we say in this case, constructive interference will take place and resultant amplitude will increase. Sir, what is destructive interference? We say when crust of one wave meets with the trough of another wave, this is the crust and this is the trough. When they actually meet, so it becomes flat, line becomes flat over here. So we say this is what we call the destructive interference. And in this case, see, net amplitude over here is 0. So we say when crust, this is the crust, and trough of a wave meet with the another wave, then we say amplitude becomes 0. And this is what we call the destructive interference. Okay. In this case, we say, sir, resultant amplitude is 0. So this is the destructive interference. Okay. Now see. Now listen to me very carefully. Everybody of you must be familiar with the two things. What is this? Let's suppose we have got a wave. Let's suppose if I say I'll make a wave over here. Let's suppose this is the wave. Okay. And this wave has got the equation A1 sine of omega t. A means amplitude. Of the wave. A1 sine of omega t. Okay. And Y2 is the A2 sine of omega t plus phi.
This is the equation of one wave and this is the equation of another wave. These are the two waves, let's suppose we have got. We say this is omega t plus phi. Directly remember, whatever I say in this particular case, you keep on remembering that. This is the equation of one wave. This is the equation of another wave. My dear friends, what is the difference between the two? Here you have phi, here you have no phi. Means the phi is the phase difference in this case. Guys, listen to me very carefully. I have told you in case of phasor diagrams in AC, over there, we can represent these two with the help of phasor diagrams. Like. This wave has got amplitude A1. I'll represent this amplitude with a line with the arrow over here. Let's suppose this is the amplitude of the wave 1. This is the amplitude of the wave 1. Similarly, this is the amplitude of the wave 2. Okay, why did I make it at this angle? Because phase difference between the two is phi. This is phi. This equation leads this equation by phi. So that's why this is the angle phi over here. Okay. And if you have to find the resultant amplitude, if you have one vector, if you have another vector, sir, angle between the two vectors is phi. How to find the resultant amplitude? A net square is equal to A1 square plus A2 square plus twice A1 A2 cos of phi. This is how do we find the resultant. This is how do we find the resultant. Okay, simply what I'm saying is that let's suppose we have got two waves like this, we have got two waves, or two waves like this. Okay, so let's suppose we have got two waves. Okay, amplitude of one wave is 1. Amplitude means this, how high it is. Amplitude of another wave is A2. So angle between the two is, let's suppose, phi. We say phase difference is phi. That's why I'm making phi. So net amplitude, if you have to find in this case, this will be the formula for net amplitude. Remember this one. Now listen to me very carefully. We said, sir, for constructive interference, we say phi is equal to 0. When you have got phase difference 0, then only constructive interference will take place. I have told you this. Sir, when phi is 0, can we say cos of 0 is 1? In that case, cos phi is 1. Can we find what is the net amplitude in case of constructive interference? We say A net square is A1 square plus we say, sir, A2 square plus twice A1 A2 cos of phi. We recently calculated this formula. If you have two vectors, you can find the resultant vector. Now, I can write over here, sir, A net square will be. What is the value of A1? Let's keep this as A1. We have got A1 square plus A2 square plus twice. We say A1, A2 cos of phi. Phi in this case is 0. So cos 0 is 1. So twice A1, A2. Now, A square plus B square plus 2AB. Can we write it something like this? A plus B, that is A1 plus A2 whole square. Now, if I say, my dear friends, if I say A1 is equal to A2 is equal to A. If I say A1 is equal to A2 is equal to A, and if we place it over here, we say, sir, A net will be, that is A net square will be, that is A plus A whole square. A plus A whole square. So can I write in that case, sir, A net square will be, sir, this is 2A whole square. Square goes. So in this case, A net will be, we say, sir, 2A. That's what I was trying to explain. In case of constructive interference, if the two waves meet and they are having the phase difference 0, in that case, if somebody asks you, tell me what will be the net amplitude, you'll simply say, sir, that will be 2A. And in case of destructive interference, we say, sir, phi is equal to 180 degree. If you use the same formula and solve, you will get, sir, net amplitude in this case will come out to be 0. Net amplitude in this case will come out to be 0. So in case of destructive interference, remember, if two waves are interfering, okay, if phi is 180 degrees, so then destructive interference will take place. So net amplitude in that case will be 0. Remember, we'll get minima. Okay? Now, let's talk about intensity. Sir, what does intensity actually mean? See,
Intensity is simply power divided by area. What is power? Power is energy upon time. Energy upon time. Okay. Listen to me very carefully. I'll make you understand. Let's suppose we have got a bulb over here. We have got a bulb over here. We have got a bulb over here. Okay. This is the bulb. So we say, sir, from this bulb, we say energy is coming out, light is coming out, light is coming out. Okay. Light is coming out. If I ask you, what is the intensity of this light? You'll say, sir, intensity in this case will be how much energy it is sending every second. That is energy per second, energy upon time, multiplied by area per unit area. Every second, let's suppose if I say I'll take a sheet over here. If I take a unit area on the sheet, how much energy is falling on this unit area every second? If more energy is falling on this unit area every second, more will be the energy, more will be the intensity. If less energy is falling on this unit area every second, less will be the intensity. Simply remember, simply forget about this. Sir, if somebody asks you what is intensity, energy per second. If some light source is sending more energy per second, means it is having the great intensity. We say, hey, this is giving you good brightness. It is having more intensity. Energy per second per unit area. Energy upon time, or you say power upon area, because power is we say, sir, energy upon time. Power is energy upon time. Okay. So my dear friends, one more important point you remember over here. Intensity is directly proportional to the amplitude square. Intensity is directly proportional to the amplitude. Intensity is directly proportional to the amplitude square. You remember this particular concept directly in your mind. Okay. Intensity is directly proportional to the amplitude square. A square. Okay. Now, if intensity is directly proportional to the A square, can I say as we recently studied, sir, A net square is equal to A1 square plus we say, sir, A2 square plus twice A1, A2, we say cos of phi. Now, my dear friends, A net, what does net amplitude actually mean? We say A net means instead of A net. See, we replace A with I because intensity is proportional to the amplitude square. So we can say this is I net is equal to, sir, this is I1. Then we say plus, this is I2. Then we say plus twice. See, if I is proportional to A, so A will be root of I. So it will be under root I1, under root I2. Then we say cos of phi. This will be the formula which will help us to find the net intensity. Okay, net intensity. As simple as that. Now, guys, let's suppose. See. If I say I have got a light source over here, this light source is sending the light waves. This light source is sending the light. Okay. So means it is sending energy, light waves, whatever you say. Now this light source has intensity, means these light waves have intensity. Okay. Now if we say the two waves for constructive interference, what will be the net intensity? Let's suppose we have got this. We have got two waves, they are meeting. This has, let's suppose, intensity I. This has intensity I. We say, sir, they are meeting. What will be the net intensity in case of constructive interference? We say when it comes to the constructive interference, net intensity will be simply 4 times of I naught. Simply, I don't have to prove it. Even you can prove it by using this particular formula. You will get the same result like this. In case of constructive interference, we say net intensity will be 4 times of I naught. If one wave is having some intensity, another wave has some intensity, and they are meeting constructively, constructive interference is happening. Okay, amplitude is becoming bigger. Sir, what will happen to the intensity? Intensity will become 4 times. And in case of destructive interference, what is the net intensity? We say, sir, net intensity of the two waves will be zero. So that's why I have mentioned over here, this is the net intensity in case of constructive and destructive interference. I hope you got it. If we have got one wave, if we have got another wave, this has some intensity, this has some intensity. If they are meeting, we say they will have some intensity, they will have net intensity. If the constructive interference happen, this will be the net intensity. This will be the net intensity in case of destructive interference. Okay, let's see where does the constructive interference happen. See. Guys, as of now, I told you, if we have got, sir, one wave, another wave, okay? If we have got one wave, another wave. And in this case, we say, sir, phase difference is 0. So what will happen? Constructive interference will take place, okay? Yes. Guys, that's what is mentioned exactly over here. In case of constructive interference, we say, sir, phase difference has to be 0. If phase difference is 0 between the two waves, then we say constructive interference will take place. Constructive interference will take place. Okay. Constructive interference will take place. Constructive interference will take place. Okay. Now guys, we say, listen to me very carefully. When phi is 0, we say cos phi will be 1. We say in that case, constructive interference will take place. Can I say this is a particular value of phi? Sir, in general, will only there be constructive interference when phi is equal to 0? We say no. Let me just tell you. We say in general, we say when phi is equal to 2n pi. Phi is equal to 2n pi. Whenever the value of phi is equal to 2n pi, in that case, constructive interference will take place. In that case, constructive interference will. And the value of n is 0, 1, 2, 3. Now, let me just tell you. Let's suppose we say phi is equal to n pi. If we put the value of n is equal to 0, we say phi in that case will be 0. If we put the value of n is equal to 1, phi in that case will be 2 pi. If we put the value of phi is equal to 2, then we say 2 into 2 is 4 pi. We say 4 pi. So my dear friends, at theta phi is equal to 0, constructive interference will take place. That we know. Now, one more point, at theta is equal to 2 pi also constructive interference will take place. 4 pi also constructive interference will take place. So general formula for constructive interference is what? We say theta is equal to n pi. Theta is equal to n pi, where n is equal to 0, 1, 2. And on all of these values, we say, sir, constructive interference will take place. Similarly, in case of destructive interference, we say, sir, for destructive interference, we say cos phi should be -1. In this case, we said phi is equal to 180 degrees. Whenever phi is equal to 180 degrees between the two waves, destructive interference will take place. Now, my dear friends, we say, in general, if we talk about, in general, we say phi is equal to 2n minus 1 into pi. Phi is equal to 2n minus 1 into pi. If the value of phi is this, then we say what? Destructive interference will take place. Okay. So value of n is 1, 2, 3, 4. Now guys, if you put the value of n is equal to 1, let me show you what will be the answer in that case. We say, sir, phi in that case will be. So we say, sir, this is 2 into, what is the value of n? That is 1. 2 into 1 minus 1 into pi. So 2 into 1 is, we say 2. 2 minus 1 is 1, so it will be pi. So at value pi, we say, sir, constructive interference will take place. So if you have got the two waves, listen to me very carefully, my dear friends. If you have got the two waves, okay. If you have got the two waves, okay, like this one and this one, between these two, if phi is equal to pi, then we say destructive interference will take place. If phi is equal to 3 pi, destructive interference will take place. If phi is equal to 5 pi, destructive interference will take place. So this was all about constructive and destructive interference. Okay. One more important point I just want to mention over here. What is that? Path difference in case of constructive and destructive interference. What will be the value of path difference in case of constructive and destructive interference? What was this? What was the value of phase difference In case of constructive interference, this one. Value of phase difference in case of constructive interference is this one. Value of phase difference in case of constructive interference is destructive interference is this one. Value of path difference in case of constructive interference is this one. Whenever you see, sir, the value of path difference delta x is equal to n lambda, then simply say, sir, constructive interference would have taken place. Okay. I hope this is clear. I hope this is clear. Okay. So we get constructive interference or maxima at delta x is equal to 0, pi, 2 lambda, 0 lambda, 2 lambda, 3 lambda, this one. Okay. Okay. So guys, if you put the value of n is equal to 0, so we say delta x will be in that case 0. If you put the value of n as 1, so delta x will be lambda. If you put the value of n as 2, so it will be 2 lambda. If you put the value of n as 3, so it will be 3 lambda. Okay. So we say at these values, we say constructive interference will take place. So means whenever the path difference between the two waves is 0, lambda, 2 lambda, 3 lambda, 4 lambda, then say constructive interference would have taken place. And in case of destructive interference, what is the value of path difference? We say, sir, 2n minus 1 into lambda by 2. 2n minus 1 into lambda by 2. 2n minus 1 into lambda by 2. So if n is equal to 1, we say, sir, put the value of n is equal to 1. So 2 minus 1 into lambda by 2. So what is that? Is 2 minus 1 is 1. So that will be lambda by 2. So means at lambda by 2, destructive interference will take place. At 3 lambda by 2, destructive interference will take place. At 5 lambda by 2, destructive interference will take place. So these are the values of path difference at which destructive interference take place. Let me know in the chats, guys. Is this clear? Is this clear? Is this clear to each and everyone? I want all the people to tell me in the chats. I want all the people to tell me in the chats if this is clear. Everyone means everyone. Everyone means everyone, guys. Okay. Two beams of light having intensity I and 4I. We have got two beams of light, intensity I and 4I. Interfere to produce a fringe pattern on a screen. The phase difference is okay. Let's suppose we have got the two beams of light. This is the first beam. This is the second beam of light. They meet at point A. We say, sir, point A. They are meeting at the point A. They are meeting at the point A. Okay. The two beams are meeting at the point A. Okay. This has intensity I. This has intensity 4I. Okay. And when they are meeting over here, the phase difference between the beam is pi by 2. So they are having the phase difference of, we say, sir, pi by 2 over here. Okay. At point A. Similarly, when the two waves, basically beams actually meet at, we say, sir, point B, they have got a phase difference of, we say, sir, pi. At point B, they have got a phase difference of pi. Okay. Then the difference between their resultant intensities will be, Tell me, what will be the difference between the resultant intensity? See, guys, first we'll find the resultant intensity, in this case, net intensity. What is the formula for net intensity? We say, sir, I1 plus, we say, sir, I2. Let's suppose this is having I1, this is having I2 plus 2 times of under root I1, under root I2, cos of, what is the angle over here? That is pi divided by 2. Cos 90 is 0. Whole term will be 0. So I1 in this case is how much? That is I, plus I2 in this case is how much? That is 4I. So it will come out to be 5I. Let's find the net intensity in this particular case. We say, sir, net intensity in this particular case, we'll use the same formula. I net is equal. We say value of I1 in this case. This is I, this is 4I. So we say, sir, I plus 4I plus 2 times of, we say, under root I1, under root I2. Then we say cos of
pi, cos 180, cos of pi. Cos 180 is -1. Okay. This is -1, so it will come over here. So this will be I plus, we say, sir, 4i plus, and instead of I1, I need to write over here. Let me write more specifically. This is under root of I, and then we say under root of 4i. Under root of I and under root of 4i. And this is -1. Cos pi is -1. So it will be minus 2 times of, this is I into I becomes I square, 2 into 2, and it becomes 4. It becomes how much? That is minus 4i. And overall, in this particular case, it will come out to be I. It will come out to be 4i. It will come out to be 4i. Okay? It will come out to be 4i. Now, tell me, what is the difference in this particular case, everybody out there? What is the difference in this particular case? Everybody? Sorry. It will come out to be I. Okay? What is the difference in this particular case? Yes. And tell me, sir, if we talk about the IA minus, we say, sir, IB in this case, that will be 5i minus I, so that will be 4i. So difference means this minus this, it will be 4i. Is this clear? Is this crystalline clear to each and everyone? Let me know in the chats. Is this crystalline clear? Let me know in the chats, guys. Okay. Okay. Great. Two sinusoidal waves of intensity. Solve this particular question. Two sinusoidal waves of intensity I having the same frequency and same amplitude interfere constructively at a point. When two waves interfere constructively at a point, in case of constructive interference, tell me, guys, see. In case of constructive interference, what is the net amplitude of the two waves? We say, sir, sorry, what is the net intensity? That is 4 times of I. So if the two waves, see, in this case, it is saying the two sinusoidal waves of intensity I meet constructively. Let's suppose this is a wave, this is a wave. They are meeting. Sir, we said both are having, sir, I. What will be the net intensity in this case? We know, sir, it will be 4 times of I. The resultant intensity at a point will be 4i. Will be 4i. Will be 4i. You can use this formula also. I is equal to, we say, sir, I net is equal to I1 plus I2 plus 2 times of under root of I1 under root of I2. We say cos of phi. And in this case, you say, sir, phi is 0 degrees. Because we know at theta is equal to 0 degrees, constructive interference take place. Okay. Let's move on to the Young's double slit experiment. Let's move on to the Young's double slit experiment. Let's move on to the Young's double slit experiment. What does Young's double slit experiment say actually? Listen to me very carefully. See, this was the experiment which clearly proved the wave nature of light. It clearly proved the wave nature of light. Let me show you how. Let's suppose you have got a source over here. You have got a source over here, or we say light source. Okay. So from the light source, we say, sir, light is coming out. This is the light coming out. So we have got a slit, narrow slit over here. So the light ray will pass from this particular slit. Okay. It will pass from this particular slit. Then you have got over here 2 slits, this one and this one. Okay. 2 narrow slits over here. That's why we call it Young's double slit experiment. This slit and this slit. So when the 2 light rays will pass from the 2 slits, okay. So all over here we have placed a screen. This is basically the screen. These are the slits. And this is, we say, sir, screen. This is the screen. And clearly on the screen, you can see, sir,
these fringes are being made, fringe patterns are being made. See, this is a bright fringe with orange color and this is a dark fringe. This is a bright fringe. Bright fringe. And this one is a dark fringe. Okay, this is a bright fringe, this is a dark fringe. My dear friends, listen to me very carefully. Listen to me very carefully. What I am trying to say in this particular case is, if we consider light as a particle, imagine we are considering light as a particle. So we say particles will leave, listen to me very carefully, particles will leave from this slit, and it will fall onto this point, okay? Because particles travel along this straight line and they will fall at this particular point. So only brightness will be here on the screen and another particles will fall at this point, only brightness will be at this point. So in between over here, there should be no brightness. So here should be no brightness. But you see, sir, brightness, darkness, brightness, darkness, brightness, darkness. Fringe patterns are being made. If we consider light as a particle, then we have to say light will fall at this point and this point only. Over here only at these two spots, bright fringes will be made. But there are, we say, sir, bright, dark everywhere. This bright, dark pattern is only because light is not particle here, light is a wave here. So when we consider light as a particle, then only these fringe patterns are being made. I'll write over here. When light is considered as a wave, then only fringe patterns are being made. Then only fringe patterns are being made. If you do not consider light as a wave, then we say we cannot get the fringe patterns at this particular screen. I hope you are getting this. And this one is what we call central maxima. Maxima means this bright fringe means maxima. Dark fringe, this means minima. Or you can also say constructive interference have taken place over here. That's the reason you got the maxima. In case of maxima, let's suppose the two waves are falling. The two waves are falling at this particular spot. So when two waves are falling at this particular spot, when constructive interference is happening, amplitude is getting bigger, intensity is getting bigger, so brightness is getting bigger. So we say maxima is being made, bright fringe is being made. Okay, we say because of constructive interference. Because of constructive interference. Okay. And this dark fringe is because of destructive interference. Maybe the two waves are falling at this point, they would be doing the destructive interference. That's the reason we get this, because of destructive interference. Okay. Okay. Now listen to me very carefully. Let's make this setup over here. We have got the slit S1. We have got the slit S2. Distance between the slits is D. And distance between the slits and the screen is, let's suppose, capital D. This is capital D and this is small d. And we say, my dear friends, listen to me very carefully. Let's suppose the light wave is basically falling at this point. Another wave is falling at this point. So this is what we call the central maxima. At central maxima, we say what is happening? Constructive interference. We say maxima is being made. Bright fringe is being made over here. And let me just tell you, sir, in case of maxima, listen to me very carefully. In case of maxima, what is the path difference? Let's come over here. In case of maxima or constructive interference, In case of constructive interference, what is the value of path difference? N lambda. Put n is equal to 0. We say, sir, path difference will be 0. Put n is equal to 1. We say path difference will be lambda. So I can clearly say now in case of this, at central maxima, path difference is 0. So that's why we say it is central maxima. And that's why we say constructive interference is taking place over here. Okay. And then we say after this, see, this is the central maxima. Then we have the first minima. This is what we call the first minima. See, first minima is being made at lambda by 2. Come over here. I'll show you the proof which we have discussed already. Sir, in case of destructive interference or minima, we say, sir, path difference is this when you put n is equal to 1. So at lambda by 2, we say, sir, destructive interference will take place. Minima will be made. So we say, sir, at lambda by 2, first minima is being made. And at then afterwards we have got, this is central maxima, first minima, first maxima. So first maxima is being made at delta x is equal to lambda. Second minima is being made at delta is equal to 3 lambda by 2. All of this I have already discussed. Now it is like a butter, smooth butter. Okay. Similarly, now listen to me very carefully. What is the question they might ask you from this particular topic? Distance at which maxima and minimas are formed. Let's suppose, I know, sir, at central maxima is formed. Let's suppose one more maxima is formed at this particular position. Okay, let's suppose 7th maxima. There might be many maximas. This is central maxima, first maxima, second maxima, third, fourth, fifth, sixth, seventh, something like that. Now the question is, if I say this is the maxima over here, okay, what is the distance from the central maxima to this particular maxima? That is what we call y. Distance at which maxima is formed, from the central maxima, okay, this y. How to find the value of this y? Y is equal to delta x, that is path difference. D is the distance between the two screen and slits, and small d, distance between these slits. I'll show you the question on this one. Don't worry about that. Let me show you the question. The question says, find the distance of fifth minima from the central maxima. It says that, let's suppose fifth minima is made over here. What is the value of y? Matlab distance from central maxima to this fifth minima. We use this formula. As we say, as y is equal to delta x, we say d divided by d. Now tell me one thing. In case we are supposed to find the fifth minima. In case of minima, what is the value of path difference in case of minima? What is the value of path difference? We say, sir, path difference we recently studied. In case of minima, what is the value of path difference? See, in case of minima, what is the value of path difference? 2n minus 1 lambda by 2. 2n minus 1 lambda by 2. 2n minus 1 lambda by 2. Delta x is equal to 2n minus 1 lambda by 2. So can I say, sir, this delta x will be 2 into. What is the value of n? It is saying fifth minima. So it is 2 into 5 minus 1 lambda by 2. 2 into 5 is 10 minus 1 is 9 lambda by 2. So 9 lambda by 2. So path difference came out to be 9 lambda by 2. Now can we find the value of y? So we say y in this case will be simply, that is, instead of delta x we write 9 lambda d divided by 2d. This will be the distance y from the central maxima. Similarly, you can find the distance of seventh maxima. So we say in this particular case, y is equal to delta x d divided by d. In case of maxima, what is the value of delta x? That is n lambda. See, Delta x is equal to n lambda in case of maxima, in case of constructive interference or maxima. What is the value of delta x? That is n lambda. Okay. And if we are talking about over here, we are talking about 7th maxima. So n is equal to 7. So delta x is equal to 7 lambda. Put it over here. Y in this case will be 7 lambda d divided by d. And this is the answer. Okay. One more concept you guys need to understand in this one. What is that? What is that? That is fringe width. That is fringe width. Let's suppose you have got over here two slits. This is S1, this is S2. Okay. And guys, let me show you this. Okay. Can I say, sir, this is the fringe. This much will be its width. This much. How wider the fringe is, that's what we call the fringe width. That's what we call the fringe width. Okay. If we have to talk about the fringe width, simply, let's suppose this much is the fringe. So this will be the fringe width. Okay. How to find this fringe width will be simply lambda d by d. D is the distance between the two, and this small d is the distance between the two slits. Lambda d by d will be the fringe width. Lambda d by d will be the fringe width. Okay. Angular fringe width. Somebody may ask you what is the angle. Let's suppose this is the first fringe. Okay. This is the bright fringe. Okay. Over here. Now take a line from this point and join over here. Take a line from this point, join over here. How much angle it is making? This will be angular fringe width. And this angular fringe width will be simply lambda by d. Tan of theta is equal to lambda by d. Lambda by d. Angularly, how wider it is. Angularly, how wider it is. Previous one was the linear fringe width. Guys, like the session if you have not liked the session yet. That's compulsory. Okay. In a Young's double slit experiment, if the separation between the slits is halved and the distance between the slits and the screen is doubled, the fringe width compared to the original fringe width is. What is the formula for fringe width? That is lambda d by d. This is the fringe width. See, it says that, let's suppose, as we know, sir, fringe width is simply, beta is simply lambda d divided by d. Okay. Lambda d by d. Lambda d by d. Okay. It is saying that if the separation between the slits is halved, if the separation between the slits is halved, so d dash becomes d by 2. Okay, okay. Separation between the slits. Okay, okay. D dash, this d dash becomes d by 2. And distance between the slit and the screen, that is this d dash, capital D, becomes doubled, that is 2d. What will happen to the fringe width? Put it over here. B is equal to B dash will be, instead of lambda, we'll put lambda only. D dash will be, sir, 2 times of d because it is doubled, divided by this d, separation between the slits is halved. So this is d by 2. 2 into 2 becomes 4 lambda d divided by d. So lambda d by d is b. So beta dash will be, sir, 4 times of beta. So it is increased by 4 times. 4 times of beta. In a Young's double slit experiment, blue-green light of wavelength, you use it. 2 slits 1.2 meter apart. Okay, okay. You guys are supposed to directly find the fringe width in this particular case. Okay, this I'll give you as homework. Direct formula-based question. Apply the formula and get the value of fringe width. Non-standard YDSE. Non-standard YDSE. What does non-standard YDSE actually mean? See, let's suppose you have got a Young's double slit experiment over here. Okay. You have got the 2 slits from which the light leaves. Distance between the 2 slits is d. This separation is capital D. And this is the screen over here. Okay. And you are basically dissolving this particular setup in a medium. Previously, let's suppose it was in the air.
Now you are basically putting this in a medium, okay, of refractive index mu. Medium has got refractive index mu, okay. In this particular case, you guys remember one thing. Wavelength of medium is equal to wavelength of air, wavelength of light in air divided by, we say, sir, mu. Remember this, remember this. Wavelength in medium is equal to wavelength in air or vacuum divided by refractive index of that medium. Okay. Now, my dear friends, if I say you are dissolving this in a setup of refractive index mu, what will be the position of maxima and minima? See, without dissolving the setup, if we take a look, without dissolving the setup, what was the position of maxima and minima? This one, delta x d by d. But when you dissolve this Young's double slit experiment in a setup, what will be the position of maxima and minima? See, you write, sir, y max is equal to, maxima is equal to n lambda. Sir, what is this lambda? Lambda is the wavelength over here in the medium, okay? D by d, okay? This capital D by small d. And wavelength in the medium is wavelength in the vacuum divided by refractive index. So you say lambda by mu. All these values will be given. You will have to find the answer. And lambda d by d. Similarly, you can find the position of the minima. Where will be the position of the minima from the central maxima? Where it will be located? In that case, you will simply say, sir, 2n minus 1 into lambda, because part difference in this case is 2n minus 1 into lambda d by d. What is this actually? See, guys, what is this actually? This I can write over here. This is n lambda. This is delta x d divided by d. Okay. But instead of maxima, instead of this delta x, part difference for constructive interference is n lambda. Part difference for destructive interference is 2n minus 1 lambda. That's why I'm putting this values directly over here. Okay. So it will be, instead of lambda medium, it will be lambda by mu. Finally, it will be, answer will be this. This will be the position of the maxima, and this will be the position of the minima. And fringe width in this case will be this one. That is lambda d upon mu d. Lambda d upon mu d. Lambda d upon mu d. Refractive index into d. Lambda d upon mu d. Is this clear? Let me know in the chats, guys. Let me know in the chats, everybody. Is this crystalline clear? Is this crystalline clear? And like the session if you have not liked the session yet. You just have to replace lambda with lambda medium. Somebody is saying, please check no voice. Okay, so this will be basically the fringe width in this particular case. Okay, one more point in this case, shift of central maxima. Sir, will there be shift in the central maxima? Let's suppose we were saying, sir, central maxima is at this point. Now, will the central maxima shift from its point? We say, sir, yes. So we say that will be, how to find the shift in the central maxima? We say, sir, d
mu minus 1. Mu is the refractive index of this one. Okay, let's suppose previously central maxima was over here. Now, will the central maxima shift? Let's suppose it will shift, it will reach over here. How to find this shift? How to find this shift? We say, sir, d into mu minus 1 into t, okay, divided by d, divided by d. Okay, 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 okay. Okay, sorry. This is the next case. This is the next case. Sorry. Not the central maxima in this case will remain same. Sorry, this is this case. Okay. Now see. I'll tell you over here. Slab in front of the slit. Slab in front of the slit. Now, let's suppose we have got this is basically the Young's double slit experiment. In this particular case, I am placing a slit over here. I'm placing the slit over here. Okay. Now, when the light rays will, let's suppose this light ray will pass through the slit and this light ray will basically, let's suppose it goes something like this. This is the central maxima. We say in this particular case, here central maxima will not shift. Here central maxima will not shift. It will remain as it is over here. But in this particular case, if you place a slit over here, and if you place a slit over here, we say central maxima will shift in the direction in which the slab is placed. If the slab is placed in this direction from the upper side, we say central maxima will shift to the upper side. And how to find the shift? Shift will be this. This is d into mu minus 1. Mu is the refractive index. T. What is T? T is the width of the slab. T is the width of the slab upon d. D is the distance between the two slits. Small d is the distance between the two slits. Remember, my dear friends, if you have got a Young's double slit experiment and you place a slit over here, and because of this slit, listen to me very carefully, we say central maxima will shift from its position. Okay, how to find the shift in the central maxima? Where will it go? D into mu minus 1 into t upon d. D is the distance of separation and the slits. Mu is the refractive index. T is the width of the slit. And this d is the separation between the two slits. And number of fringes you can calculate by this one. How many number of fringes in this case will be made? So this will be the number of fringes. Okay. And fringe width in this case will remain same. Okay. The width of the fringes will remain same. Okay. Let's talk about the diffraction. Let's talk about the diffraction. See, when it comes to the diffraction, listen to me very carefully. Let's suppose, my dear friends, you might have seen this. Have you ever experienced this one? Okay. This is what we call the diffraction. Okay. You have the door. Okay. Light is coming from the door and these fringes are being made over here. This is, we say, sir, diffraction. So what is diffraction? As the light is coming from a source and goes into the narrow opening. Light is coming from this source. There is a one small narrow opening. Okay. One small narrow opening. Okay. It should directly fall on the screen. Like this light should directly fall on the screen. But no, it bends and reaches the shadow region also. And fringes are being made in this case also. This is what we call the diffraction. What does diffraction mean? You have got a light source over here. Light is coming out of the light source. It should directly fall on this screen here. Bright spot should be made. No, but it falls on the shadow regions. It goes over here. Bright, dark fringes are being made in this case also. This phenomena is what we call diffraction. Okay. Like this, my dear friends. This light should directly pass and fall over here, but it is going here also. So diffraction patterns are being made. Okay. Like this is what we call the single slit diffraction. Okay, like the light is basically passing through this narrow slit. Okay, and then we say this is a screen here. In this case also fringe patterns are being made. This one is what we call the central maxima. It is bigger.
central maxima in this case is wider and bigger. And then this is, we say, sir, minima over here. Then we say this is first maxima, second maxima, third maxima. Okay. And this is the intensity of the fringes. See, intensity of this is bigger. Then we say it has got less and less, 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 less. And similarly, it happens over here. So this is what we call the diffraction, single slit diffraction, single slit diffraction. Light passes from the narrow slit and fringes are being made over here. Here, central maxima is bigger, wider, brighter. Intensity is having large, okay? Here, central maxima is more wider with large intensity. Okay, linear width of central maxima. If somebody asks you to find the width of this central maxima, we say, sir, that will be 2 lambda d by A. What is D? D is this distance, distance from the slit and screen. And what is, sir, A? A is, we say, sir, size of opening. What is the size of this opening? A is the size of this opening. And lambda is the wavelength. Lambda is the wavelength. And what is, sir, 2? 2 is which comes after 1. Which comes after 1, that is 2. Is this clear to each and everyone? Let me know in the chats. Let me know in the chats, everybody out there. Let me know, everybody. Two is 2. 2 is which comes before 3. 2 is which comes after 1. That is 2. Okay. And if somebody asks you what is the angular width, okay, so that will be 2 lambda by A, 2 lambda by A, okay, angular width, okay, so that will be 2 lambda by A. Like over there we calculated angular width, over here it is 2 lambda by A. Location of maxima in diffraction. Like where is the location of maxima? Where is the maxima in case of this one? So we say over here, maxima here will be 2n minus 1 lambda d divided by 2a. This you can find, by this formula you can find the location of the maxima. You can find the location of the maxima. What is this actually? 2n minus 1. So we say, sir, this is delta x, okay, and this is lambda d divided by 2a. Directly you can say, sir, this in this case will be, sir, location of the maxima, okay. And we say, sir, path difference between the two waves, that is delta x is equal to 2n minus 1 into lambda by 2, 2n minus 1 into lambda by 2, 2n minus 1 into lambda by 2, okay. And similarly, if you have to find the location of the minima in case of diffraction, where the minima is actually, okay, what is the location? Like I'll tell you over here. See, what is the location of this minima from the central maxima? Central maxima is here. What is the location of this maxima? This distance. What is this distance? Y. Okay. So that is what we are talking about over here. Location of maxima and minima. Sir, how to find the location of maxima? We say, sir, by using this formula. Okay. If I say, sir, what is the location of fifth maxima? Put n is equal to 5 in that case. What is the location of sixth maxima? N is equal to 6 in that case. You can find the path difference also. Delta x is 2n minus 1 lambda by 2. 2n minus 1 lambda by 2. Okay, this is basically the path difference, and path difference is placed over here. Okay. My dear friends, we say in this particular case, location of minima, how to find the location of minima? We say, sir, location of minima will be simply that is delta x d divided by a. Instead of delta x, we'll put n lambda. So that will be n lambda d divided by a. This is the location of the minima, where the minima is actually. Here, this we can write, this is delta x. Instead of 2n minus 1 into lambda by 2, this is delta x. And then we say d divided by a. Okay. It is exactly, you can compare this. You can compare this, my dear friends. You can compare this. See, location. See, you can compare location over here. Find the distance of fifth minima. We use this particular formula. We use this particular formula. In this case, delta x is what? We say, sir, 2n minus 1 lambda by 2. And over here, you compare it. Exactly, it is similar. Exactly, it is similar. Now, solve this particular question. See, a plane wave front of wavelength 6000 angstrom. Okay, we say wavelength in this case is given as 6000 angstrom. Okay, and a silt of 0.2 mm. So D in this case is given as 0.2 mm. Okay, which enables this diffraction pattern to be obtained on the screen 2 meters away. D in this case is given as 2 meters. Find the width of the central maxima in that case. So what is the formula for the central maxima? This is the formula for the central maxima. 2 lambda D divided by A. 2 lambda D divided by A. And instead of this, we write this A. A is the width of. So this will be width. Width of the central maxima is 2 lambda D divided by A. Put the values over here and solve the particular question. So we say this is 2 into lambda in this case is 6000 angstrom, multiply 10 raised power minus 10 if you convert this in meters, then multiplied by D. D is given as 2 meters upon we say A. What is the value of A? 0.2 into 10 raised power minus 3. Solve this, it will come out to be 12 mm. 12 mm. Yes, answer is 12 mm. Okay. Next we have polarization of light. Next we have polarization of light. Next we have polarization of light. Listen to me very carefully. Listen to me very carefully. My dear friends, what does polarization of light actually mean? Let's suppose we have got a light over here. Okay, this is a light and we say this is unpolarized light. What does unpolarized light actually mean? What does unpolarized light actually mean? Unpolarized light means, listen to me very carefully. Unpolarized light means, see, you all must be knowing that if we talk about the light, we say light is made up of electric and magnetic fields. Okay, it is made up of, we say, vibration, in which electric field oscillate, in which magnetic field oscillate. And see, light is an electromagnetic wave. Okay, electromagnetic wave in which electric fields oscillate, in which magnetic fields oscillate. Both. Now, my dear friends, listen to me very carefully. Remember it directly. Let's say I have got the unpolarized light. And let's suppose electric field is vibrating in different directions, like this. Okay. And if you use a device over here, which is what we call the polarizer. Okay. This is polarizer. And when the light passes through the polarizer, see, after this, you see only light is, this electric field is vibrating in one direction only. Okay, this component, it cancelled this particular component. Okay. So we say after this is what we call the polarized light.
if over here it is vibrating in multiple directions, after the polarization it will basically vibrate in only one direction. Okay, like you have got unpolarized light, okay, vibrating in different directions. It has got the intensity of I naught. It has got the intensity of I naught. So when we place the polarizer over here, see all the other, if the electric field is vibrating in different directions, all those will be cancelled. It will only allow this electric field, this electric field, which is vibrating something like this. So this is the electric field. And remember, in this particular case, what you are supposed to do is, if the light passes through the polarizer, listen to me very carefully, its intensity becomes I naught by 2. If it was I naught initially, it becomes I naught by 2. And then we have another polarizer, that's what we call the analyzer. After this analyzer is basically placed at some angle, let's suppose it is placed at phi. So when it is passed through this polarizer, another polarizer, its intensity becomes I naught by 2 cos square of phi. I naught by 2 cos square of this phi or theta. Remember, my dear friends, what I'm trying to say is that if you have got an unpolarized light over here, what does unpolarized light mean? Which is basically having which is vibrating in multiple directions. Electric field in this case is vibrating in multiple directions. When it passes through the polarizer, it will allow only this electric field, which is vibrating something like this. Okay, its intensity becomes I naught by 2. When it again passes through analyzer, its intensity becomes I naught by 2 cos square of phi. Okay. This is what we call the Malus law. It says that when light enters the polarizer, its intensity becomes I naught by 2. What does this law say? When light enters the polarizer, its intensity becomes I naught by 2. See, its intensity becomes I naught by 2. Okay. And then further, when it passes through another polarizer called analyzer, its intensity becomes I naught by 2 cos square of theta. Okay. Now, my dear friends, if I say analyzer is placed at 60 degrees, can I say what will be the intensity in that case? You say, sir, I naught divided by 2 cos square of 60 degrees. That is 1 by 2. So can I say this will be I naught divided by 2, and this will be 1 cos, this is 1 by 2 whole square, that's 1 by 4, 4 and 2 is 8. So in that case, this is I naught by 8. And if I say this analyzer is placed at 90 degrees, what will be the net intensity, resultant intensity? We say, sir, I naught by 2 cos square of 90. Cos 90 is 0. Okay, so this will be 0. In that case, intensity will be 0. No light will in that case come out. Means if you turn this analyzer completely something like this so that angle becomes 90 degree, we say then no light is basically allowed through this particular polarizer. Is this clear? There aren't much topics in this particular chapter. Tell me, is this clear? Tell me in the chats. This is the theta. See, this is the theta in this case. If you take this axis over here, this is the axis of this polarizer. And if you rotate this analyzer over here at some angle, so we say this is the theta in this case. This is the theta over here. Okay. Tell me, is this crystalline clear till over here, everybody?
Is this crystalline clear? All the people out there. Okay. Brevester's law is nothing, yeah. That's a small concept. There is no question which is asked on that. What does that say? If the light passes from one medium to another medium, some of it gets reflected and some of it gets refracted. That's it. That's the concept. Okay. And you guys have to remember, in that case, reflected gets completely polarized and refracted gets partially polarized. That's it. That's it. Okay. That's why I didn't put up over here that particular topic. You won't get any sort of question in that. What does Brevester's law actually say? Let's suppose this is a medium over here. This is a light travels from this medium. Light travels from this medium. Okay. This is medium 1 and this is medium 2. In this case, let's suppose this is the light which is vibrating something like this. And I'll show you it is vibrating also something like this with dots. Okay. And I'll show you something like this over here. So this one, this one, this one. Okay. And with the help of the dots also, I'm showing you over here. With the help of the dots also, I'm showing you over here. Okay. Now, this particular light gets reflected. This particular light gets reflected and refracted. Make sure you like this particular session, guys. Okay. We say, sir, some part of the light gets reflected, some gets refracted over here. Okay. Okay. And we say the one which gets reflected, that is this one. Okay. This is that light. Okay. And this is that dot one. This is that dot one. And this gets completely polarized. This gets partially polarized. Okay. Let's move on to the next one. That's dual nature of matter and radiations. We'll have to complete this chapter in a very small amount of time. Okay. This is the chapter that we need to finish now. Dual nature of matter and radiations. Okay. The first thing in this particular case is we need to understand, see. In the previous chapter, we considered light as a wave. We say here, we consider light as a particle. Here we consider light as a particle. Okay. Let's suppose if I say, I have got a light source over here. From this light source, if I say light is coming out, so I'll assume that these are the particles which are actually coming out. And more specifically, I call these particles as photons. Okay. These are the photons which are coming out of the light source. And these photons have got energy. So we say, my dear friends, if I say from now onwards the light is coming out, means these are particles coming out. Those particles are called photons. Those photons have got energy. Okay. In previous chapter, wave optics, we considered light as a wave. Okay. Now, my dear friends, tell me over here, if light is made up of photons, those photons have got energy. Can you tell me what is the energy of a photon?
You say, sir, energy of a photon is simply h into f. Sir, what is h? H is Planck's constant. And what is f? F is what we call frequency. F is what we call frequency. H is Planck's constant. F is what we call frequency. F is what we call frequency. Okay. Whenever you multiply Planck's constant with frequency, you will get energy of photon. Sir, is there any other formula? Yes. We say, sir, this frequency is also called, this frequency, F is, we say, equal to C divided by lambda. Sir, what is C? C is speed of light. Lambda is wavelength. So put this C by lambda over here, you'll get this formula, hc divided by lambda. Sir, is there any other formula? Yes. This is also the energy of photon. This is also the energy of photon. That is 2 into 10 raised power minus 25 divided by lambda in joules. So this is the energy of photon in joules. If somebody asks you, hey bro, tell me the energy of photon, calculate the energy of photon in joules, which formula you will be using? You will be using this formula. This will help you to find the energy of a photon in joules. This will help you to find the energy of photon in joules. Okay. This will help you to find the energy of photon in joules. Okay. Now, is there any other formula? Yes. We say, sir, energy of photon. You say, sir, energy of photon in electron volts. Guys, this is the energy of photon in joules. If you want to find the energy of photon in electron volts, like if I say I have got 1 kg mass, okay, I have got 1000 grams mass, both is one and the same thing. This is one unit and this is another unit. Okay. Similarly over here, this is the energy of photon in joules. Okay. And we say here lambda is in nanometers. This is the energy of photon in electron volts, where lambda is in nanometers. This is the energy of photon in electron volts, 12400, where lambda is in angstrom. I'll give you the complete feel. Let me show you on this slide. If I say, let's suppose I have got a photon. Okay. This is a photon. Wavelength of this photon is, let's suppose we say, sir, 4000 angstrom. Wavelength of the photon is 4000 angstrom. I am asking you to tell me the energy of photon in this case. What will you say? Sir, in order to find the energy of a photon, which formula I will be using over here? I have tons and tons of formula. Guys, if wavelength is given in angstrom, you will be using this formula, because here wavelength is in angstrom. You'll simply say over here, use E is equal to 12400 divided by lambda. Then you will be using this formula to find the energy of photon. If I say, listen to me very carefully. If I say I have got a photon over here, energy of this photon, energy of wavelength of this photon is, let's suppose, 310 nanometer. And I ask you to tell me what is the energy of a photon. You'll say, sir, which formula you will be using over here? We'll use this formula. Because when lambda is given in nanometer, to find the energy of photon in electron volts, we'll be using this formula. That is, we say, sir, 1240 divided by lambda. This will give you in electron volts. This will also give in electron volts. But if lambda is in angstrom, we'll use this 12400. If lambda is in nanometer, we'll use this formula. And if you have to find the energy in joules, then which formula you will be using? You will be using this formula. Let's solve a question. Can you tell me what is the energy in 1 joule? Sorry, what is the energy in joule associated with a photon of lambda is equal to 4000 angstrom? We have got a photon over here, okay? And the wavelength of this photon is, we say, sir, 4000 angstrom, okay? We have to find the energy of photon in joules. Sir, what is the formula to find the energy of photon in joules? Let me just tell you, when it comes to the energy of photon in joules, we have got this formula. So let me use this formula only. That is, we say energy is equal to, we say
2 into 2 into 10 raised power minus 25 divided by lambda in joules. But here lambda we take in meters. Lambda we take in meters. So this is given in angstrom. So what do we do? Sir, 2 into 10 raised power minus 25 divided by lambda. This is 4000 multiplied by 10 raised power minus 10. It will be converted into meters. Okay. Solve this and you will get the answer in this case. Similarly, if I ask you one more question over here, listen to me very carefully. If I say to find the energy of photon in electron volts also, to find the energy of photon in electron volts also, what will you say? Sir, I say energy of photon will be 12400 divided by lambda in angstrom. So this will give me the energy of photon in electron volts. Why? Because lambda is given in angstroms. So energy will be 12400 divided by lambda is given as 4000. So this will come out to be 3.1 electrons. Hey, is this clear? Tell me in the chats, everybody. Is this clear? Tell me in the chats, everybody. All the people out there. Everyone means everyone. Okay. Energy of light. Let's talk about the energy of light. See. If we talk about the energy of light, what does energy of light mean? Guys, if we say when it comes to the light, let's suppose we have got a light source over here. Okay. From this light source, we say, sir, light is coming out. Is this one particle, one photon coming out, or many photons coming out? Many photons. For one photon, energy of one photon is hc by lambda. Energy of so many photons, n photons, is nhc by lambda. That will be the energy of light. Okay. If I ask you what is the power of light, what is the power of light? Okay. Power of light is simply, you'll remember, sir, power means energy divided by time. Energy divided by time. If I say I have got a light source over here, how much energy it is giving every second? Sir, this light in front of me is giving me more energy every second. So we say power in this case is more. Power in this case is more. So we say energy is how much? nhc by lambda. nhc by lambda. Time is t. Time is t. This is the formula for power. Okay. Similarly, okay, this is the question that we have exactly over here. Let NR and NB respectively be the number of photons of red bulb and blue bulb. Let's suppose we have got a red bulb over here. Okay, this is a red bulb. This is red bulb. And we say we have got a blue bulb over here. Okay. We say it is saying that power in both is given the same. Oh, okay. Power of red is given equal to power of blue. What is the formula for power? NHF divided by T. So this will be NHF divided by T. But in this case, it is red bulb. So number of photons of red, frequency of red, number of photons of blue, frequency of blue. HT will get cancelled. So number of photons of red into frequency of red is equal to number of photons of blue into frequency of blue. Now tell me, sir, we know in this case, we say, see, frequency of red is less than frequency of blue. Remember this. When it comes to the frequency of red, it is less than frequency of blue. If this quantity is less and this quantity is more, but overall they are equal, so we can say this quantity NB has to be less, this quantity has to be more. So I can say number of photons of red
has to be greater than number of photons of blue. Number of photons of red has to be greater than number of photons of blue. Okay. Guys, like this session if you have not liked. Similarly, there is one more concept, that's what we call the intensity. Intensity is simply energy divided by time, okay, into area. Already discussed over there in wave optics what is intensity. So we say it is power upon area. What is power? What is the formula for power? We recently studied the formula for power is NHC divided by A into T, NHC divided by A into T, NHC divided by A into T, okay, NHC divided by lambda into T. And then we say area over here, this is area over here, this is area. This is the intensity. Intensity is simply how much energy is falling per unit time, per unit area. Photoelectric effect. What does photoelectric effect actually mean? What does photoelectric effect actually say? We say when it comes to the photoelectric effect, let's suppose we are taking a metal plate over here. We are taking a metal plate over here, metallic plate. Okay. Light is falling onto this metallic plate. Light is falling onto this metallic plate. Okay. This is a light source. This is a light source. And this is a metallic plate over here. We say light is falling onto this photosensitive metallic plate. We are doing this experiment. We observed that electrons are being ejected from this surface. Electrons are being ejected from this surface. When light falls onto the photosensitive metallic plate, or we say metal surface, we observed that electrons are being ejected from this metal surface. This process of ejecting the electrons from the metal surface, when light falls onto the metal surface, this is what we call photoelectric effect. When light falls on a photosensitive metallic surface, electrons are being ejected from the surface. Like I have got a surface over here. I have got a surface over here. Okay. Light falls onto the surface. And we observed that electrons are being ejected from the surface. Electrons are being ejected from the surface. Okay. So we say this process is what we call the photoelectric effect. This process is what we call the photoelectric effect. Okay. Okay. Now, my dear friends, there is a concept that is what we call the work function. Sir, what does work function mean? It is minimum energy required to pull the electrons from the metal surface. To pull the electrons from the metal surface. What is the minimum energy required to pull out the electrons from the metal surface? Like in this particular case, let's suppose I have got a material A. This is a material A, metal A. I say its work function is 2 electron volt. What does that mean? That means if you have to pull out the electron from this metal surface, you will have to send a photon of 2 electron volts. If you send a photon less than work function, then we say that cannot pull the electron from this metal surface. Why? Because this is the minimum energy required to pull the electron from the metal surface. Same is the case over here. Let's suppose this is material B. It has got work function 5 electron volt. When photon of 5 electron falls onto this one, then only we say electron gets ejected. If you send a photon of 2 electron volts, then that cannot eject the electron from this metal surface. Why? Because it is work function is 5. Minimum energy required to pull the electron from the metal surface. Experimental setup of photoelectric effect. Experimental setup of photoelectric effect. Okay. Experimental setup of photoelectric effect. Is this clear to each and everyone? Let me know in the chats.
If this is clear to each and everyone, let me know in the chats, guys. No, we'll take the break after. Let's finish this chapter, okay? Yes, no break for now. Hit the like button if you have not liked this session. Everybody out there, if you have not liked the session yet, hit the like button. Okay, let's discuss the photoelectric effect. See, let's discuss the photoelectric effect. Guys, what is general statement of photoelectric effect? When light falls onto the metal surface, electrons are being ejected from the metal surface. That's what we call the photoelectric effect. Okay. Now, let's suppose we have the experimental setup. How do we basically do this particular experiment? Okay. See, we take a tube-like structure over here. Okay. In this tube-like structure, we take a metal surface. This is what we call cathode. And then we take one more metal plate from this side. That is what we call anode. Okay. Then we connect a battery. This is a switch, and we connect a battery somewhere around over here. This is the battery, and this is ammeter. This is the battery. Okay. Yes, sir. My dear friends, listen to me very carefully. We say, this is a light source. When light comes out of the light source and it falls onto this metal surface, these are the electrons which come out of the metal surface. We know whenever light falls onto the metal surface, electrons are coming out from the metal surface. Okay. Now, listen to me very carefully. Let's suppose you are sending the electron of 8 electron. You are sending a photon of how much energy? 8 electron volts. Okay. And if I say work function of this metal is 2 electron volts, work function is 2 electron volts. What does that mean? Minimum energy required to pull the electron from the surface, that is given as 2. Okay. So how much is the energy you are giving? 8. 8 is the energy of photon. Sir, 8 minus 2 is equal to 6. Where will the 6 volt electron volt energy go? Sir, let's suppose, sir, this electron is taking 8 electron volts. 2 electron volts it is using in order to come out of the metal surface. Rest of the 6 electron volts it is using to travel forward in kinetic energy. Okay. So we say, my dear friends, energy of photon is used in work function, in pulling out the electron from the metal surface, and rest of the portion will be used as kinetic energy. This is what we call the Einstein's photoelectric equation. Okay. Energy of photon is equal to work function plus kinetic energy maximum. This is called Einstein's photoelectric equation. Okay. Because of this equation, Einstein got the Nobel Prize. Because of this particular equation, he got the Nobel Prize. Energy of photon is equal to work function plus kinetic energy maximum. Okay. Now, my dear friends, listen to me very carefully. Something I just need to tell you. What is that? If I say 10 electrons are coming out of cathode and only 4 are reaching anode, let me make this over here. Let's suppose this is we say sir cathode. Okay.
photons fall on the cathode, we say, sir, electrons are coming out of the cathode. Okay, electrons are coming out of the cathode. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. How many are moving forward? Only 1, 2, 3, 4. Only 4 electrons are moving forward. And this is, we say over here, this is, we say over here, anode. This is, we say, anode. Only 4 electrons are able to move forward. Okay. Okay. It is mentioned over here. Okay. Now, see what is mentioned. Now, only 4 are reaching anode. Okay. If only 4 are reaching anode, listen to me very carefully. Listen to me very carefully. If I make the graph between photocurrent versus EMF, what does that mean? Listen to me very carefully. Can I say over here, if 4 electrons are moving forward, whenever the electrons move forward, photocurrent is produced? Current is produced? Yes. Photocurrent is produced? Yes. Photocurrent is produced. Because whenever electrons flow, so these are the photoelectrons, we say photocurrent will be produced. Now listen to me very carefully. Sir, what I will do is that in this particular case, I will basically connect a battery. I will basically connect a battery to this. Positive terminal will be connected to anode. What does that mean? If positive terminal is connected to anode, it will send the positive charge to this anode. Okay. Negative terminal is over here. So means that if positive charge is occupied onto this anode, don't you think that this positive charge will attract more electrons from the cathode towards itself? Yes, it will catch more electrons from the cathode towards itself. Yes. So if it catches more electrons towards itself, okay, listen to me very, very, very carefully. Connect the switch so that battery develops the positive charge on the anode. Electrons will be attracted towards anode. This is what I explained. So current will flow, and after some time, listen to me very carefully, my dear friends. Initially 4 electrons were moving. How many are there? 6. So as we keep on increasing the positive charge, 7th electron started flowing, 8th electron started flowing, 9th electron started flowing, 10th electron started flowing. Okay. So when all the electrons started flowing, and then current becomes constant, because 10 are the only, we have only 10 here. So if we make the graph between photocurrent and EMF, okay, EMF means how much positive charge you have developed on the anode. See, listen to me very carefully. If I just write over here, we say 0 volt, at 0 volt. Can I say 4 electrons were moving? Let's suppose at 10 volts, 5 electrons are moving. At 20 volts, we say 6 electrons are moving. At 70 volts, we say, sir, 10 electrons are moving. At 80 volts, how many electrons are moving? 10 electrons only. Why? Because we have got 10 only. So now see, at 0 volts, this is EMF. At 0 volts means here. Okay. This is 10 volts, 20 volts, 30 volts, 70 volts. Okay. At 0 volts, sir, how many electrons were moving? 4, means photocurrent was there. So graph will start from here. As we keep on increasing the potential EMF, we say photocurrent is also increasing, because see, photocurrent is also increasing. And we say at 80 volt, photocurrent becomes constant. That is, photocurrent becomes constant. This is what we call the saturation current, when photocurrent becomes constant. Okay. Now, I hope you got the feel of this particular portion of the graph. I'll make you understand this one. Now, what I will say in this particular case, if we do one thing, can we just reverse the polarity? Negative terminal will be connected here, positive terminal will be connected here. This is negative and this is positive. If negative terminal is connected to this, so it will send the negative charge to this. It will send the negative charge to this anode. Okay. Don't you think that this negative charge will now repel these electrons? Initially, 4 were moving. Now, if it is repelling, now no electron will be able to reach this cathode. So, photocurrent keeps on decreasing. If we keep on increasing the potential in opposite polarity, see, this is the positive potential, this is the negative potential. We say photocurrent decreases. Photocurrent decreases. At certain value, photocurrent becomes 0. So the potential at which photocurrent becomes 0 is what we call the stopping potential. The potential, the value of negative potential, we say the value of negative potential at which photocurrent becomes 0 is called stopping potential. Okay, that's what we call the stopping. Just a second, guys. Okay, so done with the photoelectric effect. Okay, and remember one more thing, at stopping potential, we say kinetic energy of the electron is EV naught. Remember this directly. Don't ask me where does this come from. It will take time. At stopping potential, we say, sir, kinetic energy of the electrons is how much? That is EV naught. Okay, E is the charge on an electron, V naught is the stopping potential. I hope you got it. Simply, what I said is that if we occupy positive charge on it, we say electrons will be attracted. So current will increase, graph will increase. If we occupy negative charge on it, electrons will be repelled. So current will decrease. At certain value of negative potential, no current flows. That potential is what we call the stopping potential. Done. There is nothing more in the photoelectric effect. For a certain metal, okay, we have got a question important over here. See, in this particular case, for a certain metal, frequency nu is 5 times mu naught. Matlab frequency is 5 times mu naught. We have got a photon which is falling onto this metal. The frequency of this is 5 times of V naught. Frequency of this is 5 times F naught. Okay, 5 times F naught. What is F naught? F naught is the threshold frequency. Like you have got phi. Phi is the work function, minimum energy required to pull the electrons from metal surface. What is F naught? F naught is the minimum frequency required so that electron will come out, so that photoelectric effect will take place. Threshold frequency. Remember it. Minimum frequency required so that photoelectric effect can take place. Okay. We say, sir, this is the photon which falls on the metal surface. Because of this photon, an electron comes out. And the velocity of that electron, it is saying that is V1. V1 is giving as 8 into 10 raised power 6 meter per second. And then the questioner says that one more photon falls onto the same metal surface. But this photon has a frequency of 2 times of F naught. Because of this also electron comes out. So the speed of this electron is V2, which we have to calculate. Speed of this is given, speed of V2 is we are supposed to find out. Let's talk about the case 1. Case 1. We say, sir, energy of photon is equal to
Energy of photon is equal to work function plus kinetic energy maximum. Work function plus kinetic energy maximum. What is the energy of photon? What is the energy of photon? Guys, we know, sir, energy of photon we can write H into F. Okay. So I'll write over here, this is H into F. This is H into F. Okay. Okay. Is equal to work function. What is the work function of this one? Guys, if you can write energy of photon as H into F, work function also you can write as H into F naught. Why? Because see, combination of Planck's constant and frequency is energy. This is also energy. So combination of Planck's constant and threshold frequency is also energy. So you can write this as H into F naught plus kinetic energy is 1 by 2 mv1 square. So what is the frequency in the first case? Frequency of photon 5 times F naught. So it will be 5 times HF naught minus this HF naught is equal to 1 by 2 m is equal to 1 by 2 mv1 square. So this will be 4HF naught is equal to 1 by 2 mv1 square. Let's call this as equation first. Okay. Now in case of case 2, we'll use the same formula. So we say, sir, here frequency is 2 times. So I can write 2 times of HF naught minus is equal to, this is the energy of photon, work function. Work function will be HF naught plus 1 by 2 mv2 square. So the photon, the electron which this is pulling out has got what velocity? v2. And this will be 2 HF naught minus HF naught. This will be HF naught is equal to 1 by 2 mv2 square. This is called second equation. This is first and this is second. Now, my dear friends, divide first by second. So I can write over here, divide first by second. So what is that? That is 4HF naught divided by HF naught is equal to 1 by 2 mv1 square upon 1 by 2 mv2 square. 1 by 2 mv2 square. Now see, this 1 by 2m will get cancelled out over here. So this and this will get cancelled out. V1 divided by V2 in this case will be simply under root of 4, that is 2. So V2 we are supposed to find out, that is V1 divided by 2. Okay, so V2 will be, what is the value of V1? Value of V1 is 8 into 10 raised power 6. So that will be 8 divided by 2 into 10 raised power 6 meter per second. That is 4 into 10 raised power 6 meter per second. Is this clear? Is this clear? This question is on the same concept. I want you guys to do it. This is your homework. This question is on the same concept. This question is on the same concept. Okay, now let's move on to this particular concept, that is de Broglie waves, or we say matter waves. De Broglie waves or matter waves. Okay, what does de Broglie actually say? He said everything in this universe has a wave nature. Okay, and a wave is associated with it, that is called a matter wave. Okay, let's suppose, my dear friends, if I say
I have got a particle over here. I have got a particle over here. Okay, I have this pen. This pen is a particle. This has got particle nature. It has got particle nature. Okay, we can see it, we can feel it, we can touch it. De Broglie said, if this particle is moving with some velocity v, we say, sir, it will have the wave nature also. Wave nature also. It will have the wave nature also. And if something is a wave, we say it has wavelength. So this will also be having the wavelength. That wavelength is h divided by p. That wave is h divided by p. Or we say that wavelength is h divided by mv. Okay. So this wave, if it has wavelength, this wavelength is what we call the de Broglie wavelength. De Broglie wavelength. Or we say matter wavelength. Matter wavelength. Okay. So de Broglie said, if you have got a particle, okay, you can feel its particle nature, okay. We say, if this is moving with some velocity, it will also have the wave nature. It will also have the wave nature, okay. Okay. It will also have the wave nature. And this, if this has the wave nature, it should have the wavelength. What is the value of that wavelength? Lambda is equal to h by mv. Lambda is equal to h by mv. That's what de Broglie said. Everything in this universe has a wave nature. Everything in this universe has a wave nature. Everything in this universe is a wave. And a wave is associated with it, okay? Called matter wave or de Broglie wave. And that de Broglie wave is h divided by mv, h divided by mv. Or you say that is h divided by p, where h is Planck's constant, m is momentum, okay. Now my dear friends, if I say different forms of de Broglie wavelength in terms of kinetic energy, guys, this was the de Broglie wavelength in terms of momentum. But right now we have to see de Broglie wavelength in terms of kinetic energy. That formula of de Broglie wavelength in which kinetic energy is present, we say that is h divided by under root of 2mke. H divided by under root of 2mke. Okay. Then we say one more thing. De Broglie wavelength for a relativistic particle. De Broglie wavelength for a relativistic particle. De Broglie wavelength for a relativistic particle. Okay. Okay. Sir, what is a relativistic particle? That particle whose velocity is comparable to the speed of light, which is traveling with a very great velocity. That velocity which is traveling with a very great velocity. This is the de Broglie wavelength of that relativistic particle. H is Planck's constant, under root of 1 minus v square by c square. Okay, v is the velocity of that particle, c is the speed of light, m naught is the mass of that particle, rest mass, v is the speed of that particle. Directly you will have to remember this. Similarly, charge accelerated under potential difference delta v. If you have got a charge which is accelerated under potential difference delta v, okay, which is accelerated under potential difference delta v. Sir, what does this mean? Let's suppose you have got the plates over here. You have got the plates over here, 2 plates, okay, and you have connected a battery to this. So battery creates the electric field over here. If let's suppose there is a charge over here, on this charge we say, sir, force will be created because of this electric field. So force is there, so acceleration is there. So this is accelerated because of this potential difference delta v. Because of the battery potential difference, electric field is set up. Because of electric field, force acts. Because of force, acceleration will be there. So we say for this particle, de Broglie wavelength is simply h upon under root of 2mq delta v. H upon under root of 2mq delta v. Charge at rest in an electric field. If you have placed a charge in an electric field, okay, this one. So what will be the de Broglie? Let's suppose force acts on it, it started moving. What is the de Broglie wavelength of this charged particle? Lambda is equal to h by QET. Sir, Q is the charge, E is the electric field, T is the time, T is the time, T is the time. Okay. Next, charged particle placed in a magnetic field. Let's suppose you have got a magnetic field over here. Okay. And in this charged particle, in this magnetic field B, you have placed a charged particle Q. Okay. Okay. Now, when you place the charged particle inside the magnetic field, it started moving in the circle. It will move in a circle. Okay. This circle will be having the radius R. This circle has the radius R. Whenever you place a charged particle perpendicularly in magnetic field, it will have the radius R. Okay. So this will have the de Broglie wavelength of what? Lambda is equal to h upon QBR. What is Q? Q is the charge, B is the magnetic field, R is the radius, R is the radius, R is the radius. Okay, for a gaseous molecule at temperature T, if you have got a gaseous molecule at temperature T, its de Broglie wavelength is h upon under root of, we say 3m kBt. What is this kB? This is Boltzmann's constant. T is the temperature. M is the mass of that charged particle. So if you have got a charged particle if you have got a gaseous molecule, okay, at temperature T, we say de Broglie wavelength of that particle will be h upon under root of 3m kBt. Okay, for an electron moving in nth orbit of an atom, this we'll study after some time. Let's suppose this is the center, this is the nucleus, this is the nucleus, this is the nucleus, this is the nucleus. Okay, around the nucleus you have got the electron. Around the nucleus you have got the electron which is revolving around the nucleus. Okay, let's suppose you have an electron in nth orbit. Sir, nth orbit means n can be 1, 2, 3, 4, some anything. Okay, so here this electron would be revolving. Okay, so if this electron is moving, it will have the de Broglie wavelength. That de Broglie wavelength is lambda is equal to nh. N means nth orbit, number of orbits. H is Planck's constant. Under root of 2m, mass is mass of electron, into 13.6 into 13.6. Okay. There is a question over here. Find the ratio of velocity of proton and alpha particle if the de Broglie wavelength of both of the particle is same. Okay, listen to me very carefully. We are given an alpha particle over here. We are given a proton over here. When it comes to the alpha particle, we say this alpha particle is made up of 2 neutrons plus 2 protons. When 2 protons and 2 neutrons meet, they form the alpha particle. And if somebody asks you, what is the mass of the alpha particle? We say, sir, mass of alpha particle is simply 4 times mass of proton, because mass of neutron is equal to the mass of proton. So 2 neutrons have got mass 2 mp, 2 neutrons have got mass 2 mp, 2 plus 2 is 4 mp. And mass of proton is simply, we say, mp. Now it says that if the de Broglie wavelength of both is same, it says that de Broglie wavelength of alpha particle is equal to de Broglie wavelength of proton. Now, what is the value of de Broglie wavelength? We say, sir, h divided by m into v is equal to h divided by m into v. What is the mass of alpha particle? We read m alpha, v alpha. Mass of proton, velocity of proton. So I can further write it somewhere around over here. This is h upon mass of proton. Mass of alpha particle is 4 times mass of proton into velocity of alpha particle is equal to, this will be h upon mass of proton into velocity of proton. So mass of proton, this and this will cancel. So velocity of proton divided by velocity of alpha particle will be
4 is to 1. So ratio is 4 is to 1. The problem solving session is on 9th because tomorrow we are traveling to Bangalore. That's why. Next chapter. Next chapter. Fourth chapter. Guys, let me know. Did you like this session, everybody out there? Did you like this session? All the people out there. Is this clear to each and everyone? Let me know in the chats. We'll take the break at 5 o'clock, okay? Then we'll take the next break at 7 o'clock. Then we'll take the next break at 7 o'clock. So, till 5 o'clock, let's finish this particular chapter. Till 5 o'clock, we need to finish this particular chapter. That is atoms. That is atoms. See, the first topic in this case is, we say, sir, Thomson's model of atom. That is Thomson's model of atom. What does, see, in this atoms chapter, we have to study different models of atom. We have to study different models of atom. Okay. There were different people who came and they gave the different models of the atom. Okay. The first model we need to study is, we say, sir, Thomson's model of atom. So Thomson said atom is like a watermelon. Thomson said atom is like a watermelon. Okay. So if you take a look at this watermelon, if you cut it, inside this watermelon, you have got this red portion. Okay. This red portion we eat. Okay. And then you have got these seeds over here. This red he said this red portion represent positive charge. And these seeds represent electrons. These seeds represent electrons. Okay. Red portion represent positive charge and seeds represent electrons. Seeds represent, he said atom is exactly like this. In an atom, like over here you have positive charge. Over here you have got this red portion. In atom you have got positive charge. Over here you have got electrons. In atom you have got electrons. Okay. Red portion represent the positive charge. And he also said atom is electrically neutral. Atom is electrically neutral. What does that mean? Number of positive charge is equal to the number of negative charge. Number of positive charge is equal to the number of negative charge. Okay. He said number of positive charge is equal to the number of negative charge. Okay. And also it is not like, sir, more positive charge will be over here, less negative charge. No, equal. In an atom, the positive charge and mass of the sphere is uniformly distributed. The positive charge and mass of the sphere is uniformly distributed. What does this mean? It means if you have got this atom over here, it is not like, let's suppose I say, if we have got an atom over here, okay? It is not like, sir, more positive charge will be present at this point, less will be at this point. No, it is equally distributed. Okay. Similar positive charge at every point, uniformly distributed. Uniformly distributed. Okay. And mass of the sphere is in an atom, positive charge and mass of the sphere is uniformly distributed. Mass is also uniformly distributed. Okay. An atom is having the radius of 10 raised power minus 10 meters. 10 raised power minus 10 meters. This was the Thomson's model. Then came the Rutherford. What does Rutherford actually say? He said, I will not give you the theoretical model, but I will perform an experiment. With the help of that experiment, I will prove what is the actual model of an atom. I will prove what is the actual model of an atom with the help of that experiment. That experiment was basically alpha particle scattering experiment. What does that mean? He took an alpha particle source. Alpha particle source means which provides alpha particles. If I say I have got the light source over here, light source means which provides light, which gives light. Okay? Which gives light. Now see, if this is the alpha particle source, so we say this is what we call the beam of alpha particles. So many alpha particles were coming out of this alpha particle source. Okay, beam of alpha particles, okay. Now this beam of alpha particles, listen to me very carefully, this beam of alpha particles, over here he took a gold foil, so what was the experiment he performed? Alpha particle scattering experiment. He took an alpha particle source and the beam of alpha particles was coming out of this alpha particle source. And then he placed a gold foil over here. And this was the screen. Okay. Now listen to me very carefully. He observed that. It is mentioned over here. 99.86% alpha particles were falling directly on screen. If these alpha particles are coming, okay, they are directly crossing and falling onto the screen. Listen to me very carefully. We say this alpha particle has got positive charge because alpha particle is made up of protons and neutrons. So protons have got positive charge. So alpha particle has got positive charge. So what did he observe? 99.86% alpha particles were directly crossing and falling on the screen. Okay. 0.14% were deviating. Only 0.14% were deviating. That is, only one alpha particle in 8,000 alpha particles were reflected back or deviated. 1 in 8,000 alpha particles were reflected back. 1 in 8,000 alpha particles were reflected back. Okay. Now listen to me very carefully. What does it actually mean? I'll give you the feel. What does Thomson said? Thomson said, if you have an atom, in this atom, we say, sir, positive charge is distributed uniformly everywhere. He said, if this is true, then if I am sending the alpha particles over here, why are they crossing directly and falling onto the screen? Because alpha particle also have got positive charge. If this is having the positive charge in the entire sphere, then this positive charge should repel this positive charge. It should get deviate something like this. This positive charge should also deviate something like this. So these should also deviate something like this. These should also deviate something like this. At least there should be 20-30% deviation, but there is no deviation, only 0.14% deviation. So means he said that it clearly implies that, sir, the alpha, this positive charge is not present in the entire sphere. It is present at a unique position. Why? Because if positive charge was present in the entire sphere, then these alpha particles would have been deviated, would have repelled. But no, only one is being repelled in 8,000 alpha particles. So he said, what did he say? Positive charge is concentrated at a unique position called nucleus. Means if you have got this an atom, positive charge is at center. So if you are sending different alpha particles, over here,
if you are sending different alpha particles over here, okay, if you are sending, so this will be crossed, this will be crossed, this will be crossed, this will be crossed, but the one which strikes this one will be reflected back. Okay, and he also said electrons revolve around the nucleus but are not randomly distributed. Electrons revolve around the nucleus. If this is a nucleus, electrons revolve around the nucleus. These are the electrons which revolve around the nucleus. And this was the graph between, we say, number of electrons repelled, okay, and theta and theta and theta. Guys, we say clearly, you see, sir, at theta is equal to z, see, theta is equal to 0 degree, 10 degree, 40 degree. We say, sir, guys, see, in this particular case, all the particles are crossing directly, okay. So maximum number of crossing particles are crossing at 0 degree angle. They are crossing at 0 degree angle, okay. So when we say the number of particles which are crossing, we say they are large. We say the graph is, it is starting somewhere around over here. This is the graph. So at theta is equal to 0 degree, maximum number of particles are directly crossing. But when theta is equal to 180 degree, 180 degree means which is reflected back. So only one electron. So at theta 180 is over here. At theta is equal to 180 degree, approximately 0 particles or 1 particle is reflected back. So you have to remember this graph. Okay. There was a drawback of Rutherford's atomic model. What was that? It could not explain the stability of an atom. What does that mean? See, Rutherford said if we have an atom, nucleus is present at the center. Nucleus is present at the center. Okay. Around the nucleus, electrons are revolving. Around the nucleus, electrons are revolving. Okay. Around the nucleus, electrons are revolving. Okay. Around the nucleus, electrons are revolving. Okay. He said, if electron is revolving around the nucleus, people asked him this particular question. That's why it became the drawback. If electron is revolving around the nucleus, means charge is revolving around the nucleus. Means charge is revolving around the nucleus. So charge is revolving means charge is performing the circular motion. Circular motion is an accelerated motion. Okay, because whenever a particle moves in circle, it has centripetal acceleration. So it is an accelerated motion. And whenever charge accelerates, remember this, my dear friends, we say electromagnetic wave is produced. Sir, what is the source of electromagnetic wave? We say accelerating charge. Whenever charge accelerates, we say electromagnetic wave is produced. Electromagnetic wave is produced whenever charge accelerates. Okay. So my dear friends, if listen to me very carefully, electromagnetic wave means energy is radiated, energy is released. What is electromagnetic wave? Release of energy, radiation of energy. Okay. So if it means that when electron is revolving around the nucleus, it is producing electromagnetic wave, means it is losing the energy. So if it is losing the energy, after some time, this positive charge will keep on attracting it. It will fall into the nucleus. It will collapse into the nucleus. Hence, it means if it collapses into the nucleus, atom is unstable. But we know electron does not collapse into the nucleus. Atom is a stable system. So these are the points which were asked to him. He couldn't answer the question. So then finally came the Bohr's model of atom. So Bohr's model of atom was given in 3 postulates in 3 different parts. The first one is, we say, Bohr's first postulate. Bohr's first postulate answered this question, which became the drawback for Rutherford's model. Okay. What does Bohr's postulate say? Bohr said that, I know, I will tell you, electron is revolving around the nucleus, that's for sure. And this is an accelerated motion, that is also for sure. I do not disagree with that. This is an accelerated motion. I do not disagree with that. Okay. And he also said this charge is accelerating, okay? Means wave is formed, yes, forms the wave is produced, but the wave which is produced is what we call the stationary wave. It is not electromagnetic wave. And stationary wave is that wave which does not radiate the energy. Hence, if an electron is revolving around the nucleus, it is forming the stationary wave that is something like this. This is what we call the stationary wave. Okay? And if it does not release the energy, means it will keep on rotating in the same path. It will not collapse into the nucleus. So this was the Bohr's first postulate and answer to the Rutherford. Second is Bohr's second postulate. What does it say? Bohr's second postulate defines the stable orbits. Bohr's second postulate defines the stable orbit. What does it mean? An electron can revolve only in that new atom. See, I will tell you. Let me change the background of this. Now see. Listen to me very carefully. What does Bohr actually say? He said, if let's suppose you have got an atom over here. He said, if let's suppose you have got an atom over here. Okay, this is a nucleus. Around the nucleus, we say electron is revolving. Around the nucleus, we say electron is revolving. Okay. He said, this electron can revolve only in that orbit. It can revolve only in that orbit. In which its angular momentum is nh divided by 2 pi. In which its angular momentum is nh divided by 2 pi. In which its angular momentum is nh by 2 pi. Guys, it is not like, sir, this electron can revolve in any orbit. No, it can revolve only in that orbit in which its angular momentum is nh by 2 pi. Like n can be, let's suppose if we put n is equal to 1, we say, sir, it will be h by 2 pi. Sir, an electron which is revolving in this orbit will have the angular momentum h by 2 pi. Is it possible? Yes. We say if n is equal to 2, it will be 2h divided by 2 pi. If n is 3, we say 3h divided by 2 pi. And then we say 4h divided by 2 pi. So an electron can revolve in these orbits only in which it can, if it has h by 2 pi angular momentum, 2h by 2 pi, 3h by 2 pi, then it is possible. That's what he said. That's what is mentioned over here. An electron around a nucleus only revolves in those orbits for which its angular momentum is some integral multiple of h by 2 pi, that is nh by 2 pi. Okay. Third postulate, Bohr's third postulate. Bohr's third postulate says that, listen to me very carefully. If you have got a nucleus over here, this is the first orbit. First orbit means in which is just outside the nucleus. This is the second orbit, okay? This is the third orbit. This is the third orbit. Okay, first orbit, second orbit, third orbit. Okay. Now, my dear friends, in this particular case, we say, if an electron makes the transition from higher orbit to lower orbit, if it moves from higher orbit to lower orbit, if an electron makes the transition from higher orbit to lower orbit, then energy would be released from it. Then we say in that case, energy is released in this process, means a photon is released, because photon itself is an energy. Photon is released. Okay. And my dear friends, if it has to make a transition from lower orbit to higher orbit, if the electron wants to make the transition from lower orbit to the higher orbit, we say energy has to be supplied to it. We need to supply the energy to it, then only it can make the transition from the lower orbit to higher orbit. Means we need to send an electron to this one. It will basically take that energy of that electron, then it will move to the higher orbit. So these are the two statements of Bohr's third postulate. Mathematical analysis of Bohr's model.
Okay. Mathematical analysis of Bohr's model. Is this crystalline clear? Let me know in the chats, everybody out there. Is this crystalline? Guys, if you have not liked the session yet, like it as soon as possible. Make the like count 1.3. Make the like count 1.3K. Everybody out there, is this crystalline clear? Hey, Nandalal Yadav, what are you doing in the chats? Huh? I'll get you blocked, huh, if you do this. Okay, great, 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 great. Okay. Now see, mathematical analysis of Bohr's model. What does this actually mean? It says, if it says, let's suppose we have got an electron over here. Let's suppose we have got this is a nucleus. Around the nucleus, we say electron is revolving. Okay. We say this electron will have some velocity if it is in the nth orbit. Let's suppose if it is in the nth orbit. Okay. Like it is mentioned over here. It is mentioned over here. We have got, listen to me very carefully. We have got a nucleus. The charge on the nucleus is Z. At r distance, you have kept an electron which is E. Okay. And this electron is revolving around the nucleus, something like this. We know, sir, if this electron is in the nth orbit. Which orbit? We say, sir, nth orbit. Okay. So here, it will have some velocity. It will have some velocity, that is V. So that's what we need to discuss. Velocity of an electron in nth orbit. Velocity of an electron in nth orbit. So what is that? That is 2.2 into 10 raised power 6 Z by N. Z is what? Z is the atomic number. Z is the atomic number. Like for hydrogen, atomic number Z is equal to 1. For helium, we say, sir, Z is equal to 2. Okay. Let's suppose we say if this is a hydrogen atom over here. In case of hydrogen atom, if an electron is revolving in nth orbit, what will be its speed? You say, sir, 2.2 into 10 raised power 6 Z by N. Z is in that case 1. Or you can also write it V naught Z by N. So this is the velocity of an electron in nth orbit. In nth orbit. Okay. Similarly, we have got over here. Let's suppose we have got the same electron, which is revolving in the nth orbit. N can be 1, 2, 3, 4, anything. Okay. Now, my dear friends, from this center to this radius is, we say, sir, R.
And if somebody asks you, what is the radius of the electron in nth orbit? In this nth orbit, what is the radius of electron? You say, sir, radius of electron in nth orbit is 0.53 angstrom n square divided by z. N is what? Which orbit you are talking about? If you are talking about third orbit, so n is 3. Z is atomic number. If you are talking about hydrogen, atomic number of hydrogen is 1. So you can also write it R is equal to n square by z. This is the radius. This is the radius of an electron in nth orbit. Now, time period of revolution of an electron in nth orbit. If I say an electron is revolving in nth orbit of the hydrogen atom, okay, of an atom, I am asking you, sir, how much time it will take in completing the one cycle? How much time it will take in completing the one cycle? So if it is starting from this point and it is moving and it reached the same point once again. So we say how much time it will take in completing the one cycle. We say this will be the time. Okay. Time is equal to 1.51 into 10 raised power minus 16 n cube by z square. N is the number of orbits, its cube, and Z is the atomic number. Z is the atomic number. Okay. How much time an electron takes to complete one cycle is what we call the time period. Next. We say total energy of an electron in nth orbit. Guys, listen to me very carefully. This one is important. If I say this is an atom over here, this is the nucleus at center. It is having the charge Ze. Okay. Remember, the charge of the nucleus is, we say, sir, Z. Z is the atomic number. E is the charge over here. Okay. Listen to me very carefully. If I say this electron is revolving around the nucleus, if this is revolving around the nucleus, it has mass m, it has velocity v. We know whenever there is a particle which has mass m, which is moving with the velocity v, it has got kinetic energy, that is 1 by 2 mv square. Okay. But here, it has got mass m, velocity v. In this particular case, this will have the kinetic energy of, Ze square upon 8 pi epsilon naught r. Z square upon 8 pi epsilon naught r. Z is the atomic number. If this is the hydrogen, atomic number is 1. Okay. E is the charge on an electron divided by 8 pi epsilon naught r. R is the radius. Okay. And if somebody asks you what is the potential energy, whenever there are two charges, let's suppose if we have got a charge Q1 over here, at r distance you have got another charge Q2, they will have potential energy K, Q1, Q2 divided by r. So here we have got electron and proton. They will have the potential energy between the two. So that potential energy in this case will be this one, minus Ze square upon 4 pi epsilon naught r. Now this is kinetic energy, potential energy. Sir, what about total energy? This will be the total energy in that case. This will be the total energy in that case. That is minus Ze square upon 8 pi epsilon naught r. Clearly you see over here, kinetic energy is inversely proportional to r. But the value of kinetic energy in this case is positive. It is positive. Okay. Potential energy is also inversely proportional to r. It is negative. It is negative. Total energy is also inversely proportional to r. It is also negative. So if we make the graph between energy versus r, E versus r, you can clearly see in this particular case, my dear friends, listen to me very carefully. Sir, kinetic energy is positive. So positive energy will make from the upper side, negative energy we make from the lower side. And kinetic energy is inversely proportional to r, so the graph would be rectangular hyperbola. So potential energy is negative. So this would be the potential energy. Total energy is negative. This would be the total energy. This would be the total energy. That's why I made it from the negative side, and they are also inversely proportional to r. They're also inversely proportional to r. Okay. Okay. And one more thing you can see over here. Total energy is exactly like potential energy. But here total energy is positive. Kinetic energy is negative.
Sorry, kinetic energy is positive, total energy is negative. Okay? Okay. Now. I can write over here. Total energy is, we say, negative of kinetic energy. One more thing I just want to tell over here. What is that? See. If I say total energy, guys, there is a derivation for this. You say, sir, total energy is this one, Z minus ZE square upon 8 pi epsilon naught R. I'll write over here. As we say total energy is minus ZE square upon 8 pi epsilon naught R. Okay. What I suggest you to do is, if you put the value of R over here, what is the value of R? R is equal to R naught n square by Z, radius of an electron in nth orbit. Then put the values and solve. Finally, after solving, you will reach on to this particular equation. I hope you are getting me what I'm trying to say. If you take the total energy, put the value of as R is equal to R naught n square by Z. Put the value over here. Then put the value of 8 pi epsilon naught, value of E, R naught, everything. And then if you solve, you will land on to this particular equation. So I would recommend you to directly remember this equation. That is total energy of an electron in nth orbit is minus 13.6 Z square by n square. Now, if total energy is positive, can I say kinetic energy is, if total energy is negative, can I say kinetic energy is positive of total energy? Yes. So we say that will be minus 13.6. We say, sir, Z square by n square. So from this, I can write kinetic energy is plus 13.6 Z square divided by n square. Okay. Now, if I talk about more specifically for a hydrogen atom, Z is equal to 1. For a hydrogen atom, Z is equal to 1. So put the value of Z is equal to 1. So I'll get, sir, total energy of an electron in hydrogen atom is minus 13.6 by n square. And kinetic energy will be 13.6 by n square. 13.6 by n square. Okay. Let's move on to this one. The total energy of an electron in an orbit. See, guys, one more important thing I just want to tell. Yeah, you can see this particular chart also. See, we know, sir, total energy is equal to, simply, that is minus 13.6 divided by n square. For a hydrogen atom, we say if Z is equal to 1. Okay. Now, if we say, sir, n means orbit. If we talk about the first orbit, for first orbit, n is equal to 1. So we say energy will be minus 13.6 divided by 1. That is minus 13.6 electron volts. Okay. If we say, sir, n is equal to 2 for second orbit. So we say for n is equal to 2. So we say this will be 2 square minus 13.6 divided by 2 square. So it will be minus 3.4. It will be minus 3.4. It will be minus 3.4. Similarly, total energy of an electron in the third orbit of hydrogen atom, minus 1.51. And then in the fourth orbit, minus 0.85. See, this was the question which was asked in NEET 2019. Total energy of an electron is minus 3.4. Total energy is minus 3.4 electron volts. Okay. We are supposed to find its kinetic energy. We know, sir, kinetic energy is positive of total energy. That is 3.4 electron volts. And then we are supposed to find potential energy. We say, sir, potential energy. Guys, can I say one thing? What is that? We know, sir, total energy is equal to potential energy plus kinetic energy. Total energy is equal to kinetic energy plus potential energy. Okay. So I'll write total energy in this case is minus 3.4 is equal potential energy plus, we say kinetic is how much? That is 3.4 electron.
Take it over there, minus, so this will be minus 3.4 because this is also minus, is equal to potential energy. So we say potential energy in this case will be minus 6.8 electron volt. Minus 6.8 electron volts. So I can say kinetic energy is 3.4 electron volts and that is minus 6.8 electron volts. One more question we have over here. The electron in a hydrogen atom jumps from n is equal to 3 to n is equal to 1. We have got, let's suppose this is the nucleus. This is the first orbit of the nucleus. This is the second orbit of the nucleus. This is the third orbit of the nucleus. Okay. Okay. Now, an electron jumps from n is equal to 3 to n is equal to 1. Okay. Okay. An electron jumps from n is equal to 3 to n is equal to 1. Now, guys, listen to me very carefully. What is the energy of an electron in third orbit? That is minus 1.51. What is the energy of an electron in first orbit? Minus 13.6. So we say here energy of an electron is minus 1.51 eV. Here energy of an electron is minus 13.6 eV. If an electron makes the transition from higher orbit to lower orbit, we say in that case energy will be released. How much? Energy gap, this energy gap, this energy gap. That is 13.6 minus 5.1. That is 12.1 electron volts. 12.1 electron volts will be the energy gap in this particular. 12.1 volt will be the energy gap and this will be the energy of photon. Because in this case, photon is released and that photon has got how much energy? That is 12.1. That is 12.1. Okay. That is 12.1. Now, my dear friends, it says that this photon which is released from this, it falls on the photosensitive metallic surface. It falls onto the photosensitive metallic surface. So we say when it falls onto the photosensitive metallic surface of work function 5.1 electron volts. Of work function 5.1 electron volts. We say, sir, photoelectric effect will take place. Electron will come out from the surface. And we are supposed to find the stopping potential. Guys, listen to me very carefully. When it comes to the stopping potential, we say, first of all, you tell me one thing. In this particular case, can we say as energy of photon is equal to work function plus kinetic energy maximum. This is Einstein's equation. When an electron makes the transition from higher orbit to lower orbit, photon is released. That photon has energy of 12.1 electron volt, which falls on the photosensitive material. Photosensitive material. Okay. Which falls on the photosensitive material. So we say photoelectric effect will take place. It will have the stopping potential. So let's find that stopping potential. See, energy of photon is 12.1 electron volt is equal. Work function is 5.1 electron volt. Then we say plus kinetic energy, we can write EV naught because I have already told you the value of kinetic energy is EV naught. Okay. In terms of stopping potential, 12 minus 5, that is 7 electron volt is EV naught. V naught is the stopping potential. E and E will cancel. Stopping potential will come out to be 7 volts. Answer in this case is 7 volts. Is this clear? Is this clear to each and everyone? This I will give you as homework. Consider the third orbit of helium. For helium, we say, sir, atomic number is 2. Using non-relativistic approach, the speed of an electron in this orbit will be third orbit. Okay. N is equal to 3. It is saying that we have got helium. In the third orbit of helium, what is the speed of an electron? As speed of an electron, V is equal to V naught Z by N. Okay. Like
I have told you over here, speed of an electron, that is V naught Z by N, 2.2 into 10 raised power 6 Z by N. So I can say it will be simply V is equal 2.2 into 10 raised power 6 into Z by N. Z is 2 divided by 3. This will be the speed of that electron. Is this clear? Is this clear? Is this clear, guys? Tell me in the chats, everyone. Let's take a break of, we say 15 minutes, okay? 15 minutes. 15. What is the time right now? Not 15 minutes. We'll have to take, because we'll have to do the iftar, okay? We'll have to break the fast we'll have to break the fast at 7 o'clock. I'll have to give, that is the compulsory, at 7 o'clock. So right now we'll be back at 5, 5, 5, 10 minutes back. The break is till 10 minutes only, okay? So we'll have to break the fast. That's why I'll have to give one more break at 7 o'clock. That's the compulsory break. Fumble, guys. Now see. Let's move on to the next chapter, that is nuclei. That is nuclei. Join back quickly, join back quickly. Now see, my dear friends. What is a nucleus? What is a nucleus? First of all, let me tell you over here, sir, what this nucleus is. As we have studied the complete atom, in case of the complete atom, we say at the center is what we call the nucleus. And around the nucleus, we say, sir, electron is revolving. This is the electron which is revolving around the nucleus. This is the electron which is revolving around the nucleus. And this is the nucleus at the center. Now we'll have to do the study of this particular nucleus. We'll have to study about this nucleus. Okay. Now see, my dear friends, when it comes to this nucleus, we say the particles inside the nucleus. Listen to me very carefully. The particles inside the nucleus are protons and neutrons. Inside the nucleus, what are the particles? Protons and neutrons. Outside the particle, what is revolving? We say, sir, electron. So listen to me very carefully. We say the particles which are present inside the nucleus are called nucleons, or we say hydrons, or we say baryons. Simply we call them nucleons. Nucleons are those particles which lie inside the nucleus. Means protons and neutrons are what we call the nucleons. Okay. And if we talk about the radius of an atom, it is 10 raised power minus 10 meters. And if we talk about the radius of nucleus, it is 10 raised power minus 15 meters. Keep this thing in your mind. Radius of nucleus is 10 raised power minus 15 meters. Okay. Cool. Now the point is a representation of a nucleus. How do we represent the nucleus? Okay. Let's suppose if we have got a nucleus over here. This is the nucleus we have got over here. Okay. And the name of the nucleus is, we say, sir, X. The name of the nucleus is, we say, sir, X. Okay. And in this nucleus, let me make it bigger. Let's suppose we have got this nucleus over here. In this nucleus, we have got proton. Okay. Proton, 4 protons. We say, sir, 4 neutrons. Okay. So this nucleus contains 4 protons, 4 neutrons. Now, so the name of this nucleus is, we represent, say, X. Then we say at the top, this is, we say, A. What does this A mean? A means the mass number. What does that mean? That is number of protons plus number of neutrons. In this case, number of protons is 1, 2, 3, 4. Number of neutrons is 1, 2, 3, 4. So total number, mass number in this case is how much? We say, sir, 4 plus 4 is 8. In this case, A is, we say, sir, 8. Okay. And then we say Z. Z means atomic number. Atomic number means number of protons. Can you tell me how to find the value of Z? You say, sir, value of Z will be how much? See, in this particular case, number of protons in this case is 1, 2, 3, 4. Simply. So in this case, Z is 4. We say Z is 4. So if I have to represent this nucleus over here, see, how do I represent? We say, sir, X. Then we say total number of protons, A, that is 8. Total number of, total number of nucleons, that is 8, mass number. Atomic number Z is, we say, sir, 4. 4x8 will be the name of this nucleus. Okay. This is how do we represent this nucleus. Then comes the next concept. That's what we call the rest mass energy. What does rest mass energy actually mean? Let's suppose we have got a mass over here. Okay. Or we say, let's suppose we have got an object over here. This object is moving with a velocity v, its mass is m, its mass is m, its mass is m. Okay, we know, sir, due to the motion of the object, it has got an energy in it, that is kinetic energy. And this kinetic energy is equal to 1 by 2 mv square. Remember this. The kinetic energy of an object is 1 by 2 mv square. It is due to the motion of the object. Whenever somebody moves, we say it gains kinetic energy, that's 1 by 2 mv square. Now, in this particular case, we say we have got mass m over here. This is the mass m, okay? Due to the mass of an object, it has energy associated with it. That is called rest mass energy. Due to the mass of an object, it has energy in it. That is what we call the rest mass energy. Like I say, sir, I have got mass over here. Because of its mass, does it have energy stored in it? We say yes. Sir, this is moving. This is the motion. This is in motion. We say, sir, because of its motion, it has kinetic energy. If we place an object at certain height, we say, sir, because of this height, it has potential energy, mgh. So because of mass, this has energy in it. That's what we call rest mass energy. That's what we call rest mass energy. And how to find that rest mass energy? mc square, E is equal to mc square. Let's suppose if we have got an object of 10 kg, if we have got an object of 10 kg, if we have to find the energy stored in this, how can we find? E is equal to mc square. Mass is how much? 10. C is the speed of light, that is 3 into 10 raised power 8, its square. Okay. So I'll write over here, this is 10. Okay, 3 into 3 is 9. So 9 into 10 raised power, this is 8, 16. Okay, that will be 90 into 10 raised power 16 joules. This much amount of energy can burn the entire universe. It can burn the entire universe. It can take this whole world upside down. This is the amount of energy which can burn the entire universe, all the galaxies, everything. Guys, do you understand what that means? How much is this energy? Huh? Do you understand how much is this energy? Okay. Like if I say, what is your mass? What is your mass? You say, sir, my mass is how much? Sir, 60 kgs. How much energy do you have stored in you? How much energy is there stored in you? Immense amount of energy. Okay. So this is 10 kg. 10 kg has this much. And do you know when it was that atomic bomb was basically, when it was that Hiroshima and Nagasaki incident? Have you heard about that? Okay. So in that case, we say 0.2 grams of mass was converted to energy. Only 0.2 grams of uranium was converted to the energy, and whole 2 cities were destroyed completely. Just 0.2 grams. Just 0.2 grams. Okay. Now you see how much energy do you have stored in you. The energy equivalent, this was asked in NEET 2020, the energy equivalent to 0.5 grams of substance is. Can you tell me how much is the energy in this case? Okay. So we say, sir, E is equal to mc square. So we say E is equal to mass in this case is 0.5. Okay. Okay. Into, you can also write it something like this, 0.5 grams. You can write it 5 into 10 raised power minus 4 into 3 into 10 raised power 8 its square. Okay. Is that clear? Is that clear? Is that clear? Is that clear? Just E is equal to mc square. That's it. E is equal to mc square. That's it. Okay. 4.5 into 10 raised power 13 joules. Huh? Clear? So this is how you can, whatever the mass I'll give you over here, let's suppose mass is, we say, sir, 100 kgs. If I say how much is the energy stored in this, E is equal to mc square. So we say mass in this case is 100 into 3 into 10 raised power 8, it's square over here. Okay. Is that clear? Is that clear? Let's move on to the next one. Let's move on to the next one. Let's move on to the next one. See, nuclear size, size of nucleus, nuclear size of nucleus, nuclear size of nucleus. Okay, listen to me very carefully. My dear friends, when it comes to size of the nucleus, we say experimentally it has been verified volume of nucleus is directly proportional to the mass number. What does that mean? Let's suppose we have got this nucleus over here, its mass number is 10. What does that mean? What does that mean? It has got how many number of nucleons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nucleons. This has got mass number 5. Now you can clearly see, size of this nucleus is small. Size of this nucleus is big. Size of this nucleus is small. Because volume of, size means volume, because mass number is more the number of nucleons, we say more is the volume. Okay, that's what is mentioned. Volume is proportional to mass number. This has got less mass number, it is volume is less. So can I say in this case, sir, 4 by 3 pi r cube, okay, is proportional to, we say, sir, mass number, because this is volume is proportional to mass number. 4 by 3 pi is constant, r cube is proportional to mass number. We say r is proportional to, I can write over here, r is proportional to a raised power 1 by 3. And then finally we got this, r is equal to r naught a raised power 1 by 3. R naught a raised power 1 by 3. Is that clear? Is that clear? R is proportional to a raised power 1 by 3. Okay. So, what is this R? R is the radius of nucleus, where R is radius, where R is the radius of nucleus, where R is the radius of nucleus. Okay. Okay. Where R is the radius of nucleus. Okay. As simple as that. So volume of nucleus is directly proportional to the mass number. More is the mass number, more will be the radius of the nucleus. Okay. Let's move on to the next one. Let's talk about the nuclear density. Let's talk about the nuclear density. See, if we talk about the nuclear density, what does the density of nucleus, rho? We say simply, sir, density is mass by volume. We say, sir, it is, okay, one more thing I just want to tell you over here. If somebody asks you to plot the graph between R versus A, that is radius versus mass number, how will you make it? R versus A. You make it something like this. Because this is having the, because R is proportional to A raised power 1 by 3. So graph will be this. Okay. Now, we say, sir, density of nucleus is what? Nuclear density or density of nucleus. It is mass of nucleus divided by, we say, volume of nucleus. Okay. Now, my dear friends, listen to me very carefully. Let's suppose we have got a nucleus over here. And inside this nucleus, you have got 1 proton, neutron, proton, neutron, proton, neutron, 6 number of nucleons. Mass of 1 nucleon is, let's suppose, mp. Because mass of neutron is same as the mass of proton. So we say mass of nucleon is over here mp. Mass of nucleon is mp. Listen to me very carefully. If mass of nucleon is mp, so we say 1, 2, 3, 4, 5, 6. What will be the mass of whole nucleus? We say, sir, mass of whole nucleus will be 6 times mass of proton. Because mass of 1 nucleon is mp. Mass of 6 nucleons is 6 times mp. Okay. Okay. And if we talk about the volume, sir, volume of nucleus is, we say, proportional to V naught. Volume of nucleus is proportional to the mass number. Volume of nucleus is proportional to, we say, mass number. We recently studied. Volume of nucleus is proportional to the mass number. We say, sir, V is equal to, replace this with a constant, V is equal to V naught into A. As bigger is the mass number, if mass number is large, we say volume of the nucleus will be large. So mass of nucleons, listen to me very carefully. For 6 nucleons, mass is 6 times mp. If I say A number of nucleons are present in this one, if I say mass number is A, can I say in this case, sir, mass of nucleus will be, sir, A into mp, 110%. Just put it over here. Rho is equal to mass of nucleus will be A into mp upon volume of nucleus will be V naught into A. V naught into A. A and A will get cancelled. This rho will be mass of proton divided by volume this V naught. And overall, this value is coming out to be constant. That is 10 raised power 17 kg per meter cube. So it is mentioned over here. Density of nucleus is constant for all the nucleus. That is 10 raised power 17 kg per meter cube. It is constant for all the nucleus. Simply, sir, what is nuclear density? Density of nucleus. This question over here. Take a look. We say radius of 2He4 nucleus is 3 fermi-meter. We are given a nucleus over here. That is 2He4. That is helium nucleus. Its radius of helium nucleus is given as 3 fermi-meter. Okay. The radius of 16s32. We say, sir, 16s32. We are supposed to find the radius of this one. Okay. Now tell me one thing. We have recently studied, sir, as radius is proportional to the mass number raised power 1 by 3. Can I say, sir, radius of this S sulfur divided by radius of this He is equal to A divided by this A whole raised power 1 by 3. Mass number of this S, mass number of this He whole raised power 1 by 3. So I can write it further over here. Sir, Rs divided by Rhe will be equal to, sir, A. Mass number of this helium is, mass number of this S is 32. This is mass number, that is 32. Mass number of helium is 4. Because this is mass number, this is atomic number. That is 4. Okay, whole raised power 1 by 3. So I can write it something like this, 4, 8. So 8, 1 by 3. Okay. So cube root of 8, that is 2. So Rs divided by Rhe. What is the value of Rhe? That is 3 is equal to, we say, sir, 2. 3 into 2 is 6. Radius of S is, we say, sir, 6 fermi-meter. Yes, a lot of people have given me the correct answer. That's great. Absolutely great. Nice. Binding energy. Let's talk about this concept. Binding energy mass defect. Let me make you understand this particular concept over here. See, let's suppose we have got a nucleus over here. Okay. Inside this nucleus, you have got 1, 2, 3, 4 nucleons. Mass of each is, we say, sir, 5 kg, 5 kg, 5 kg, 5 kg. And if I ask you in this particular case, what is that net mass, or we say, sir, collective mass. Mass collective. That is 5 plus 5 plus 5. That is, we say, sir, 20 kgs. Okay. What I'm doing in this particular case is that I'm breaking this particular nucleus. I want to break this particular nucleus. Okay. So I want to break this particular nucleus and take these nucleons out of the nucleus. So I'll have to use energy. I'll have to supply energy in breaking the nucleus. Then these nucleons will be taken out. When I placed this first nucleon over here, the second nucleon over here, third nucleon over here, fourth nucleon over here, then I calculated the mass of all the four, okay, individually. And then I added them. We say, sir, individual mass came out to be, we say, sir, 22 kg. 22 kg. What was the mass of all these inside the nucleus? We say, sir, 20 kg. What is the mass finally? That is 22 kg. Can I say mass defect has occurred over here? Yes. We say, sir, mass defect has occurred. And if somebody asks you how to find this mass defect, you say, sir, this will be simply, that is 22 kgs. 22 kgs minus, we say, sir, 20 kgs. Okay. You simply say, sir, that is 2 kg is the mass defect. Now the question is, how does this mass defect actually come from? Where does this mass defect actually come from? Why this mass has been increased? Okay. Let me answer this question over here. Same concept I am taking over here. I have got a nucleus in this case. Okay. This nucleus has got a number of nucleons. A is the mass number. And Z is the atomic number of protons. My dear friends, if I say the collective mass of all these nucleons is capital M. Now I want to break this nucleus. Okay. So for that, I'll have to supply the energy. When I break the nucleus, I took the protons out. Let's suppose mass of proton is MP. How many number of protons are over here? Z. So Z protons have got Z MP mass. Okay. Now, how many neutrons are over here? Sir, if protons are Z, total is A. Neutrons will be A minus Z. So A minus Z will be the number of neutrons. And if mass of one neutron is Mn, so A minus Z neutrons has mass A minus Z into Mn. Now, this is the individual mass. This individual mass came out to be greater than collective mass. Like in the previous question, the individual mass came out to be greater than collective mass. Okay. Okay. Now, I will say the energy which is used in breaking the nucleus is stored in the form of the energy which is used in breaking the nucleus is stored in the form of mass. It is mass over here. Is mass over here. Is stored in the form of mass. Okay, it was correct. In the form of mass in nucleons. So the energy we basically gave over here in order to break the nucleus, that is not wasted. That is stored in these nucleons. That's why their mass increased. Okay. Mass can be converted into energy. Here energy is converted into mass. That will be stored as mass. That's why their mass is increased. So this energy is what we call binding energy. This energy which is what we call binding energy. The energy which is used to break the nucleus is called the binding energy, and that binding energy is stored as mass defect. And due to that energy only mass defect occurred. Due to that energy only mass defect occurred. Due to this energy only mass defect occurred. And if somebody asks you how to find the mass defect, simple logic. What is the final mass? This is the final mass individually. ZMP plus A minus ZMN minus collective mass, that is M. Like over there, 22 kg minus 20 kg. Okay. So this much is the mass defect. And if somebody asks you, Find the binding energy. Sir, mass, this mass is because of that binding energy only, this mass defect. Now guys, if you have to check how much is the binding energy stored in this mass, you say simply binding energy is m in B is equal to m into c square. It is E is equal to mc square. So in this much of mass, how much is the energy stored? Delta m into c square. Instead of delta m, you put this value, zmp plus a minus zmn minus m into c square. Okay, this will be the binding energy formula in that case. Simply guys, you remember, binding energy is that energy which is used to break the nucleus, and that energy will be stored as the mass in nucleons, and due to which mass defect occurs. As simple as that. An important statement I would like to mention over here, that is binding energy per nucleon is proportional to the stability. Binding energy per nucleon is proportional to the stability. This one. What does this mean? What does this mean? I will show you with the questions. Binding energy per nucleon. First of all, let me tell you what is binding energy per nucleon. We say, what is binding energy per nucleon? This is binding energy per nucleon. This is what we call, it is the amount of energy amount of energy used in taking out one nucleon. Amount of energy used in taking out one nucleon from the nucleus. From the nucleus. This will be the binding energy. This will be the binding energy per nucleon. How much amount of energy you have to use so that you can take one nucleon from the nucleus, okay, per nucleon. See, we are given over here two nuclei, 4x6 and 6y12. Binding energy of x and y are 24 electron volt and 36 electron volt. Binding energy for this, if we have got the nucleus over here x, this is 4x6, okay. It has got binding energy of how much? 24 electron volts. We have got one more nucleus, that is 6y12. It has got binding energy of how much? We say, sir, 36 electron volts. Which one is more stable? As it looks, sir, the amount of energy required to break the nucleus. Here we need more energy to break the nucleus, so it looks y is stable than x. But no. Stability. If we talk about the stability, we say as binding energy per nucleon is proportional to stability. Okay. And in this particular case, if we have to find the binding energy per nucleon, what is the value of binding energy? That is 24 divided by mass number per nucleon. Mass number is 6, 24 by 6. 6 4s are, that is 4 electron volt. So, in order to take out every single nucleon from X nucleus, you would require 4 electron volt energy. You would require 4 electron volt energy. Okay. And in this case, if we find binding energy per nucleon, so that will be binding energy is 36 divided by, we say mass number is 6. 6 are 36. Okay. No. Mass number is 12. Okay. Sorry. We say, sir, this is 36 divided by 12. So this will come out to be 3 electron volts. So we say, if you have to take out one nucleon from Y nucleus, you have to use 3 electron volt energy, less energy. Here you have to use 4 electron volt energy. So we say X is more stable than Y. X is more stable than Y. Is that clear? Let me know in the chats, guys, if this is crystalline clear to each and everyone. Okay. Graph between binding energy per nucleon versus mass number. Graph between binding energy per nucleon versus mass number. This is an important graph. This is binding energy per nucleon. You can also call it the stability also. Binding energy per nucleon, or you call it the stability. It is one and the same thing. Okay. Now, if I make the graph between binding energy per nucleon and stability, the graph would be something like this. The graph would be something like this. Okay, this would be the graph. This would be the graph. Okay. Now, my dear friends, listen to me very carefully. This is the experimentally verified graph. We say, this is step binding energy per nucleon versus mass number. Let's suppose if there is a nucleus, it is having mass number 10. So that is having the binding energy, how much? This much. Let's suppose there is a nucleus, it is having the mass number 20. So this 20 has this much of binding energy. Similarly, the mass number, which is the nucleus, which has 30 binding energy, 30 mass number, it has got binding energy this much. And the nucleus, which has got mass number 170, it has got this much binding energy. Now see, listen to me very carefully. My dear, binding energy per nucleon. More the binding energy per nucleon, more is stability. Sir, this nucleus which lie over here, it has got less binding energy per nucleon, so it is less stable. So this binding nucleus, it has also got less binding energy per nucleon, it is also unstable. So we say in this particular case, all those nuclei which lie between A is equal to 30 to A is equal to 70. Let's suppose you have got different nuclei over here. So from A is equal to 30 to A is equal to 170. These nuclei are, we say, stable nuclei. These nuclei are stable nuclei. Let me write over here. Those nuclei with mass number less than 30, if there is a nucleus, it has got 20 mass number, 15 mass number, 14 mass number, are called lighter nuclei. Those are called lighter nuclei and are unstable. Those are unstable. Why? Because they have got less binding energy per nucleon. Then we say those nuclei with mass number greater than 170, are called heavy nuclei and are unstable Those are also unstable. These heavy nuclei are also unstable, Now, here two nuclei will combine together to form a bigger nuclei. See. In this case, what we say is that, let's suppose you have got the two nuclei over here. We say one is 15, another one is, let's suppose, 16. This has mass number 15, 16. If they combine together, they form a bigger nuclei of how much? That is 31 mass number. 31 is stable. So that's what is mentioned over here. Two nuclei combine together to form a bigger nuclei in order to attain stability, so that they become stable. And this process is what we call fusion. When two nuclei fuse together to form a bigger nuclei, this process is what we call fusion. Okay? And energy is released in this process. Remember, my dear friends, energy is released in this process. Okay? Next. Also, a bigger nuclei with mass number greater than 170, breaks into two smaller nuclei to gain stability. Let's suppose you have got a nucleus of over here. This has got mass number 200. 200 is unstable. So if it breaks in two nuclei, 1 and 2, this is having 100, this is having 100. 100 is stable. So it forms 2. See, this breaks into two nuclei. This process is what we call fission. Okay, this is fission. Fusion means combining two nuclei to become stable. Fission means breaking into two nuclei to become stable. Okay. Like over here. So we say a bigger nuclei with mass number, this breaks into two smaller nuclei to gain stability, and this process is called fission. Energy is released in this process. So whenever you see something is moving towards the stability, something has attained the stability, we say energy is released in that process. Energy is released in that process. Let's move on to this one. Is the fission and fusion clear? Tell me in the chats. Is the fission and fusion clear? Tell me in the chats. Everyone means everyone, ladies and gentlemen, boys and girls out there. And if you have not liked the session, guys, like the session as soon as possible. Okay. Now we'll have to study the Q value of the reaction. Q value of the reaction. Okay, now let's move on to this particular topic, that's Q value of the reaction. See, when it comes to the Q value of the reaction, let's suppose this is how much energy is released or absorbed. What does that mean? Let's suppose you have got a nucleus A, okay, and you have got nucleus B. Now these two nucleus are combining together, okay. They form the nucleus C and nucleus D. Okay, this looks like some sort of reaction of the nuclei. In this reaction, we say, sir, plus Q over here. What does this plus Q mean? This Q means Q value of the reaction. That is energy absorbed or released during the reaction. So, my dear friends, A plus B, these are what we call the reactant nuclei. So they are converted into product nuclei. And then we say, sir, Q. Q means energy absorbed or released. So this is what we call the Q value of the reaction. Q value of the reaction. Okay. And if somebody asks you, sir, how to find this Q value of the reaction? Directly, I'll tell you over here, sir, this you can find mass of reactants. Sir, this is mass of reactants minus mass of products multiplied by c square. C is the speed of light. Okay. So what is mass of reactants? Mass of A plus mass of B. Mass of A nucleus plus mass of B minus mass of C plus mass of D. Mass of C plus mass of D into C square. This is the Q value of the reaction in terms of mass. There is one more important formula. Okay. One thing I just want to tell you over here. If mass of A plus mass of B is greater than mass of C plus mass of D. Guys, it says that if this quantity,
mass of reactants is greater than mass of products. In that case, let's suppose if I say this is 10, this is 5. 10 minus 5 is plus 5. So Q value of the reaction in that case will come out to be positive. Q is coming out to be positive. Positive means energy is released. If this reactant mass is greater than product mass, we say energy is released in that process. Remember it, guys? Okay, so it is an exothermic process. It's an exothermic process. And if mass of A plus mass of B, mass of reactants is less than mass of products, so product mass have increased, we say, sir, Q will be negative in that case. Why? See. If I say mass of reactants is 5, mass of products is 10, 5 minus 10 is minus 5. So Q will come out to be minus 5. So in that case, if Q is minus 5, so energy is absorbed. Energy is absorbed. It is an endothermic reaction. It's an endothermic reaction. Okay. Is this clear? Is this clear, Q value of the reaction? Now see, one more important thing. To write the Q value of the reaction in terms of binding energy. If somebody asks you to write this Q value of reaction in terms of binding energy, how do you write? We say, sir, Q value of the reaction, I'll simply say directly over here, this will be, sir, binding energy of products, okay, minus we say binding energy of reactants. Binding energy of products minus we say binding energy of reactants. This will be the Q value of the reaction in terms of binding energy. That is BC plus BD minus BA plus B. Let's move on to the questions that will help you to solve. This is, we have the reaction over here. See. I'll write the reaction. That is 7Li, 3Li7. We say 3Li7. Then we say plus 1H1. We say it gives 2H4 plus 2He4, okay, plus we say, sir, Q. In this case, we are supposed to find the Q value of the reaction. Okay, guys, and it is mentioning that the binding energy per nucleon for 3Li7 and 2He4 is 5.60 and 7.06. Okay, it says that, see, if we have got 3Li7, it says that binding energy per nucleon for 3Li7 is how much? 5.60. Means binding energy of every nucleon of 3Li7 is 5.60. So binding energy of 7 nucleons is how much? 7 into 5.60. Bro, for 1 nucleon it is 5.60. For 7 nucleons, see, 3Li7, mass number is 7. So for 7 nucleons, it is 7.60. And it is saying, sir, binding energy of 2He4. For this, binding energy per nucleon is given as 7.06. How many nucleons are there in 2He4? You say, sir, 4 nucleons. This is one helium. It has got 4 nucleons. Another helium. It has got 4 nucleons. So 4 plus 4 is 8. So 8 nucleons has got how much binding energy? 7.06 into 8. Question done. Now see, I'll show you over here. In order to find the Q value of the reaction, I write binding energy of products minus binding energy of the reactants. Okay, this is the formula. So I say this Q value of the reaction will be simply. This will be simply. What is binding energy of products? Binding energy of products. You say, sir, binding energy of products will be how many? Okay, products are these. Okay. How many products are there? Okay, you say, sir, 2He4, 2He4. How many nucleons are in the products? 4 plus 4 is 8. One nucleon of products has how much binding energy? 7.06. 8 has got how much? 8 into 7.06. So 8 into 7.06. Then minus binding energy of reactants. In case of reactants, how many nucleons are there? 7. Don't say this 1. It is only 1H1. 1H1 is proton, okay? Hydrogen. So this is only 1. So it has got 0 binding energy, 1H1. Now see, it is 3Li7. So we say in this case, one nucleon of this has got how much binding energy? 5.60. 7 has got how much? 7 into 5.60. 7 into 5.60. Tell me in the chats, is this clear? Tell me in the chats, is this clear? Everybody out there, is this clear? Is this clear? Okay. And this will be, we say, sir, 17.3 MeV, mega electron volt. Is this clear? Binding energy for 1 is this much, for 7 is 7 into this much. That's it. Everybody. Okay, next question on the same concept. Tell me the answer of this question. All the people out there. See, the binding energy per nucleon for deuteron and alpha particle are X1 and X2. Okay, the reaction in this case is 1H2 plus 1H2 gives 2He4 plus Q. We are supposed to find the Q value of the reaction. Simply, Q value of the reaction is binding energy of products minus binding energy of reactants. Okay. Now, it is saying that the binding energy per nucleon for deuteron is this 1H2, 1H2. It is X1. See. If we talk about 1H2, it has got binding energy per nucleon as how much? X1. If we talk 2He4, helium, it has got binding energy per nucleon as X2. Okay. So, one nucleon has got binding energy X2. 4 nucleons has got how much binding energy? 4 into X2. One nucleon has got binding energy X1. Two nucleons have got how much binding energy? 4 into X, 2 into X2. But here you have got 2 plus 2 is 4. So we say Q is equal to binding energy of products. So 4 into this, it has got X2. 4 into X2 minus, we say, sir, X1. A lot of people are confused. Let me write one more step over here. See, Q is equal to 4 into X2. This is the binding energy of products minus binding energy of reactants. These are the reactants. How many nucleons are there in the reactants? 2 plus 2 is 4. So 4. For one nucleon of reactants, how much is the binding energy? X1. This is what I was saying. 4 into X2 minus X1. Is this clear? Is this clear to each and everyone?
Is there any Kashmiri in the chat? Is there any Kashmiri learning from this particular session? Raise your hands. Which place? Which place? Okay. Cool, cool, cool. Okay. One more important concept I just want to add over here, then we'll move on to the semiconductors, okay? What is that? That is nuclear force. That is nuclear force. Nuclear force. What does nuclear force actually mean? Let's suppose I have got a nucleus over here. I have got a nucleus over here. Okay. We know inside the nucleus you have got protons, you have got neutrons, you have got protons, neutrons, protons, 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 neutrons, neutrons, protons, protons, neutrons, neutrons, protons. Okay. Okay. Now, my dear friends, if you take a look over here, proton has got positive charge, neutron have got positive, proton have got positive charge, neutron have got no charge. We say, sir, if we talk about between the protons, we say electrostatic force exists. So whenever you have the two charges, they apply the force on each other. And how much is that force? F is equal to K Q1 Q2 divided by R square. Now, this nucleus is a very small congested place. Now, if we have the two protons inside the nucleus, means they are placed at a very small distance. Okay. This R is in the fermimeters. Okay. Even less than 1 fermimeter or 1 fermimeter. Okay. Now, we say, sir, here, R is very small, very small. If this quantity is very small, can I say, sir, this electrostatic force is very large? If electrostatic force is very large between the protons, so let's suppose this proton is being pushed in this direction, this proton is being pushed in this direction. Okay. So this electrostatic force becomes very large. So if this electrostatic force becomes very large, we say it will make the nucleus unstable. It will try to break the nucleus. So, and tries to break the nucleus. Tries to break the nucleus. But we know nucleus is a stable system. It does not break. So we say, here. So between the protons, between the nucleons, another force acts called nuclear force. Okay. So between the nucleons, we say another force acts. That's what we call the nuclear force. If I say, sir, these are the two protons, they are basically pushing each other in the outward direction. But we say it is the nuclear force which is basically keeping them together over here in this particular place. So this is electrostatic force over here. This is electrostatic force. This is nuclear force. And we say this nuclear force is attractive in nature. And remember, my dear friends, this nuclear force exists between nucleons. We say, sir, nuclear force between proton, it will be equal to nuclear force between neutron. it will be equal to nuclear force between proton neutron. Guys, when it comes to the electrostatic force, that exists only between the protons, okay, in the case of nucleus. But when it comes to the nuclear force, it exists between two protons, two neutrons, even proton and neutron also. Okay, okay, and it is a large force. Keep that thing exactly in your mind. Okay, okay. Is this clear? Is this clear? Is this clear to each and everyone? Okay, let me ask you a question on this particular concept. Okay, the question is, if you have got a proton and if you have got a proton, if you have got a proton, if you have got a neutron, if you have got a neutron and if you have got a neutron, okay, we say net force between proton is F1 and between proton neutron is F2 and between neutron is F3. You have to compare which force will be large, okay, or will they be equal in all the three cases? Let me know in the chats, everybody out there. Let me know in the chats. Everybody, let me know in the chats. See. If I would have asked what is the nuclear force between the two protons, between the two neutrons, and between the proton and neutron between the two neutrons, you would have said it is equal. But I'm not talking about the nuclear force. I'm talking about the net force. See, in this case, when it comes to this will be, in this case, nuclear force between the two. This is nuclear force, and this will be electrostatic force in the outward direction. They apply electrostatic force also. But when it comes to the proton and neutron, they apply only nuclear force on each other. Okay, no electrostatic force because neutron does not have charge. When it comes to this one, this will also apply only nuclear force. This will also apply only nuclear force. Okay, my dear friends, you can clearly see that if you check the net force in this case, see on this one, if I say in the outward, this is 10 Newton, this is 5 Newton, net will be 10 minus 5, that is 5. See guys, if this is 10, this is 10, this is 10. In this case, 10 Newton, 10 Newton. What will be? This is 10, this is 5. So net will be how much? That is 5. So if I say force between the proton and proton is F1, so we say F1 is less than force between the proton and neutron, that is F2. And this force will be equal to, we say, sir, F3. Because here you have only nuclear forces. Here you have electrostatic force also. Is this crystalline clear? Is this crystalline clear? Is this crystalline clear? Let's talk about the semiconductors. Let's talk about the semiconductors. Next topic we are starting. Let's talk about the semiconductors. Now guys, what does a semiconductor actually mean? See, before understanding the semiconductor, okay, we need to talk about the conductors. We say, sir, conductors are those materials. Conductors, let's suppose if I am taking a conductor over here, okay. We say, sir, conductor are those materials in which free electrons, large free electrons are present. We say current flows easily. We say conduction is possible. Conduction is possible. Current flows easily. And when it comes to, sir, insulators, we say, sir, no free electron is present. That's why there is no conduction, no current electricity is produced in this case. So in case of conductors, if we talk about, we say clearly, sir, in this case, conduction is possible. Conduction is possible in case of conductors. Why? Because there are large number of free electrons which produce the current over here. Okay. Okay, because of so many free electrons. And then we say insulators. Sir, when it comes to the insulator, we say conduction is not possible. Why? No free electron is present. Okay. Okay. Now guys, if I say, can you convert the insulator into the conductor or conductor into the insulator completely? We say no. We say no. We say, can you, then we have, in between the two, we have got a semiconductor. In between the two, we have got a semiconductor. Sir, this semiconductor, it lies between conductor and insulator. It can behave like a conductor. It can behave like an insulator. That's why this semiconductor is very important in the modern times. The phones you use, the mobile phones you use, the computers you use, okay, televisions, everywhere semiconductors are used. Okay. Okay. So we say this semiconductor, we say it can become a conductor also, it can become an insulator also. That's why we say it is special. It is special. We say it has got dual nature. It has got dual nature. Its conductivity and resistivity can be controlled. If we increase its conductivity, we say it will become conductor. If we decrease its conductivity, it will become an insulator. Okay. Now take a look. If we talk about a conductor, its conductivity lies between 10 raised power 2 to 10 raised power 8 ohm meter inverse. This is the conductivity of a conductor that is lying between 10 raised power 2 to 10 raised power 8 ohm meter inverse. And if we talk about the semiconductor, its conductivity lies between 10 raised power minus 5 to 10 raised power 6 ohm meter inverse. Okay. And if you talk about an insulator, its conductivity is less than 10 raised power minus 9 ohm meter inverse. Guys, if you keep on decreasing the conductivity of an conductor, if you make it 10 raised power minus 5, it will become an insulator. And if you make it to 10 raised power 6, see, conductivity of conductor is from 10 raised power 2 to 10 raised power 8. If you make it 10 raised power 6, it will become a conductor. That's why we say this is special. In case of semiconductor, we say it behaves like a conductor also. It can behave like an insulator also. Now comes the concept of band diagram. Okay. What does this concept of band diagram actually say? Listen to me very carefully. Let's suppose we have got a material over here. Okay. And in this material, we say there are large number of, I'll make you understand what is band diagram. We say if we have got a material over here, we say in a material, there are millions of electrons. Present in a material. Okay. And we say, sir, in this material, if millions of atoms are present inside the material, millions of atoms contain millions of electrons. As simple as that. Now the question is, these electrons are present in the energy levels. Okay. You say, sir, if we have got a material, I have got this material over here. Okay. I have got this material. And I know, sir, in this material is made up of, we say, large number of, we say, atoms. Okay. Infinite number of atoms. Those millions of atoms contain millions of electrons. Okay. Now, if you ask me in a crystal, where does those electrons lie? We say they lie in the energy bands, energy levels. Okay. Like these are what we call the energy levels. Okay. Energy levels. These electrons basically lie in the energy levels, like over here. In every energy level, you have got two electrons. Okay. Sir, you used to say previously in case of Bohr's model, sir, nucleus is at the center and electron is revolving around the nucleus. Now you are saying electron is in the levels energy. This is valid for single electron system. It is not valid over here where millions of electrons are present. So we say in a crystal where millions of electrons are present, electrons lie in the energy bands, energy levels. In every energy level, two electrons are present. So this is what we call the band diagram. Now, let's make the band diagram for semiconductors. Okay. Listen to me very carefully. If we have to make this band diagram for semiconductors, we make this one. This is what we call the conduction band. Okay, we make conduction band. We make the energy levels. This is what we call the conduction band. And this one is what we call the valence band. Let me write over here. This is valence band. And this is conduction band. This is conduction band. Okay. Now, my dear friends, in this case, if you have got these levels over here, and if you have got these levels over, these are the levels of valence band, these are the levels of conduction band. For different materials, this band diagram looks different. For semiconductors, it looks something like this. This is what we call the conduction band, and this is what we call the valence band. Okay, conduction band and valence band. And my dear friends, in between the two, this is what we call energy band gap. Okay, this gap is what we call the energy band gap. And this level is what we call the highest energy level of valence band. Okay, or we say maximum energy level of valence band. Okay. And this energy level is what we call the minimum energy level of conduction band, lowest one. Okay. Minimum energy level of valence band. Okay. So, my dear friends, we write over here, listen to me very carefully. Sir, this energy band gap, delta E, it is always equal to, sir, minimum energy level of conduction band, minus maximum energy level of valence band. Okay, maximum energy level of valence band. Okay, keep that thing in your mind. And some important points I just want to mention over here. Sir, at 0 Kelvin, conduction band is completely empty, valence band is completely filled. Means if let's suppose you have got a semiconductor material over here, you have not increased the temperature of the semiconductor material. Okay, at 0 Kelvin we are saying. We say at 0 Kelvin, this valence band, it is completely filled with electrons. And this is completely empty. Now, if you increase the temperature of this semiconductor, okay, let's suppose you make it 300 Kelvin. We say in that case, these electrons will shift to the conduction band. Some electrons will shift to the conduction band. So these electrons will shift to the conduction band. Remember this, my dear friends. So when these electrons will shift to the conduction band, over here, listen to me very carefully. So now this electron will come over here, this electron will come over here, this will come over here, this will come over here. And a hole is being created over here, hole. Sir, what does hole mean? Hole means the vacant space. So we say electron hole pairs are created. So vacant space is created over here, okay? Deficiency of electron means the hole. Deficiency of electron means the hole. Okay, my dear friends, okay. This is basically the band diagram of semiconductors. Similarly, if we try to make the band diagram of conductors, if we try to make this for, we say band diagram conductors. See. For conductors, we say this is what we call the conduction band. Let's suppose this is we say conduction band and this is we say valence band. Can you tell me what is the difference between the band diagram of semiconductors and band diagram of conductors? We say in this case energy band gap is 0. Energy band gap is 0. And over here in case of conductors we say this conduction band is completely filled. Conduction band is completely filled at 0 Kelvin. Okay. And this valence band is completely filled. Okay. This is also completely filled. This is also completely filled. And remember, my dear friends, these are what we call the bonded electrons. Bonded electrons. And these are what we call the free electrons. Free electrons. So free electrons basically constitute the current electricity. They are responsible for the conduction. They are not responsible for the conduction. So the electrons which are present in the valence band are free electrons. And the electrons which are present in the, the electrons present in the conduction band are free electrons. And the electrons present in the valence band are, we say, bonded electrons. Okay. Sir, what happens to the, if we increase the temperature, will the electron hole pair be created? We say yes. In this case, if you increase the temperature, electron hole pair will be created. Maybe in this case, listen to me very carefully. I'll tell you the secret. We say, sir, this electron will shift to the conduction band. This will also shift to the conduction band. So hole will be created. But this hole will be recombined very soon in a very small amount of time. One more electron will come and that will get occupied over here because there are so many free electrons present. That's why it gets recombined very soon in a very small amount of time. Okay. And if we talk about the insulators, band diagram for insulators. So if I have to make the band diagram for insulators, so that will be something like this. Let's suppose this is the conduction band. This is the valence band. Okay, this is the conduction band. This is the valence band. And in this case, we say, sir, energy band gap is large. Even greater than 3 electron volts, we say. Okay. And here, when it comes to the electrons, this valence band is completely filled. Valence band is completely filled. Okay. Valence band is completely filled. But conduction band is completely empty. Even if you increase the temperature in this case, these electrons would not be able to cross this band gap because it is very large. So no electron in the conduction band. So that's why there is no conduction. We know, sir, conduction is because of these free electrons. Let's talk about the types of semiconductor. Let's talk about the types of semiconductor. So the first category of semiconductors is basically, we call it intrinsic semiconductor. Is this clear till over here? Let me know in the chats, people. Is this clear till over here? If you're not like this session yet, guys, hit the like button. Break will be at 6:50. Okay. Now, see, let's talk about the types of semiconductors. The first category is, we say, sir, intrinsic semiconductor. Okay. We have got the intrinsic semiconductor over here. We also call this as pure semiconductor. Pure semiconductor. Okay. And then we have the next category of semiconductors. That's what we call impure. Impure semiconductor. Okay. Pure semiconductor and impure semiconductor. Okay. We'll discuss both of these. First, let's talk about the pure semiconductor. Listen to me very carefully. Listen to me very carefully. Guys, let's suppose this is a semiconductor crystal. I am saying this is a semiconductor over here. And we know, sir, at room temperature, let's suppose it has got some electrons in it and it has got some holes in it. Sir, what does electron-hole pair mean? I told you, if you increase the temperature in case of semiconductors, we say electrons will shift to the conduction band. So holes will be produced in the valence band. Okay. Okay. Yes. Now, if you have got this semiconductor crystal, okay, we say electrons, holes are already present. Now you connected a battery to this pure semiconductor. Okay. So battery will set up the electric field. This is the electric field because of the battery. Now tell me one thing, sir. This is a normal crystal. We say at molecular level, it looks something like this. See, actual scenario is we are taking the silicon crystal. We are taking the silicon crystal. Okay. Silicon is considered to be the pure semiconductor. Pure semiconductor. Okay. Silicon is considered to be the pure semiconductor. So my dear friends, if we have the pure silicon over here, okay, this pure silicon, this is Si. My dear friends, we are saying that at room temperature, it has got electrons, it has got holes. At room temperature, it has got electrons, it has got holes. Okay. Okay. So if it has got electrons as well as holes, so if you are applying the electric field, sir, we know whenever you place an electron inside the electric field, it experiences the force. We say electrons will be pushed in the backward direction.
We know if this is an electric field, you push an electron, it will be pushed in the backward direction. Electron is pushed in this direction. And my dear friends, this electron gets occupied into this hole. It gets occupied into this hole. Now, it looks like, listen to me very carefully, listen to me very carefully, listen to me very carefully. We say, sir, initially hole was over here. Now, if this electron gets occupied into this hole, now hole will be placed over here. Now, hole will be basically made over here. Can I say it looks like, sir, electron is moving in this direction, hole is moving in this direction, but in actual reality, only electron is moving. Okay. But it looks like hole is also moving. Hole has got the positive charge. Remember it. Hole is having the positive charge. Electron has negative charge. So my dear friends, can I write in this particular case here, I'll say electrons as well as holes are moving. Okay. So in this case, current will be because of we say net current in this case will be because of electrons, plus net current will be because of holes, And in general, if I say, sir, what is the value of net current in this particular case? You simply say, sir, this will be the value of net current in this case. That is Ni, okay, EA delta V divided by L. Okay, L is the length of the semiconductor, delta V is the potential difference applied by the battery, A is the area of cross section of semiconductor, E is the charge on an electron, N is the number of electrons per unit volume. Okay, and then we say mu E plus mu H. Mu E is the mobility of the electrons. Mu E is mobility of electrons, and mu H is mobility of holes. Mobility means if I say which one has got more mobility, the one who is more free to move has got more mobility. The one who is less free to move has got less mobility. Okay. So electron has got less mass. So we say it is free to move. It is having the more mobility as compared to the hole. Hole is positive charge. Positive charge has got more mass. So we say, remember this, mobility of electron is greater than mobility of holes. Okay. I hope this is clear. E is the charge on an electron. A is the area of the cross section of semiconductor. Delta V is the potential difference applied by the battery. L is the length of the semiconductor. Okay. So this is basically what? This is basically, we say pure semiconductor. Now, what is the problem in pure semiconductor? I will tell you. Every time if you have to do the conduction, over here in case of pure semiconductor, we say we have to apply the battery. We have to apply we have to increase the temperature, because the increase in temperature, holes and electrons are created, then only they move. So this is a large process. See, I say this is a pure semiconductor. You have to make the conduction in this pure semiconductor. What will you do? You will first create electron hole pairs. How is that possible? By increasing the temperature. So every single time, if you have to make the current flow in this pure semiconductor, you have to increase the temperature and electron hole pairs are created. That too, if you increase the temperature, not greater electron hole pairs are created, only few electron hole pairs are created. So yes, it is temperature dependent, and conduction is also less. So what we do instead is that we make an extrinsic semiconductor, that is impure semiconductor. Impure. We make an impure semiconductor. Okay. Yes, by adding the impurity, we make this impure semiconductor. Now listen to me very carefully over here. See. We say, my dear friends, if we make an N-type semiconductor over here, if we make an N-type semiconductor over here, sir, extrinsic semiconductor is of two types. We say N-type semiconductor and we say P-type semiconductor. Okay. How to make the N-type semiconductor? Listen to me very carefully. We'll take a pure semiconductor first. Let me take the pure semiconductor first. That is a silicon crystal. This is a silicon crystal that I am taking over here. Okay. Okay. Now, in this case, if this is a silicon, this is silicon, this is silicon, this is silicon, this is silicon. Remember, my dear friends, silicon has got 4 valence electrons. 4 valence electrons. Valence electrons means it is having the 4 electrons, okay, in its surrounding, okay, in which it is making the bond with the other silicon. Okay, that's, we say this is the valence electron. My dear friends, this is a pure silicon. This is a pure semiconductor. We have to make N-type semiconductor from it, or we say impure semiconductor. So we will add the impurity, that is phosphorus impurity. We'll add the phosphorus impurity. We say add phosphorus impurity in this case. Okay, phosphorus impurity. Now this phosphorus has got 5 valence electrons. Okay, this phosphorus has got 5 valence electrons. So in order to fit into this crystal, it should only have how many electrons? We say, sir, 4, because 4 is the requirement over here. It has 5. So what it will do is it will basically donate 1 electron, minus 1 electron. If it donates 1 electron, it becomes phosphorus positive. It becomes positively charged. Also, we call it positive donor ion. Donor ion. Donor ion. It becomes positively charged, so we call it phosphorus positive or positively donor ion. Okay. Now, see. So we say basically, my dear friends, if we have added the phosphorus over here, so this is the phosphorus. Now it is making the 4 valence with the 4 valence, it is making the bond over here. And that 1 electron which it has donated, that is over here. So on adding 1 phosphorus, my dear friends, we say 1 electron is donated. Now, if you are adding the impurity in a semiconductor, will you add 1 phosphorus or millions of phosphorus? A small impurity contains millions of phosphorus. So on adding millions of phosphorus, we say millions of electrons are donated. Now, these electrons are what we call the free electrons. Free electrons. These electrons are what we call free electrons. So if these are the free electrons, so they constitute the electric current. Okay, they will make the electric current. They will make the current electricity over here. So conduction has been increased. So we say some points we need to understand over here. So we say electrons will be in the majority. Electrons will be the majority charge carriers. What does that mean? See, guys, if you are adding the phosphorus over here, on adding phosphorus, lot of electrons are being donated over here. So can I say majority charge carriers in p-type, or we say electrons? Ne will be the majority charge carriers, and holes in this case will be minority. So at room temperature, it was having 4 electrons, 4 holes. On adding impurity, now 50 electrons have added, holes are only 4. So that's why we say these are the minority charge carriers, electrons are the majority charge carriers. So we say current due to electrons is much greater than current due to the holes. I hope this is clear to each and everyone. And number of electrons is equal to the number of donor ions. That's what I was telling. If you are adding 5 phosphorus is a donor ion. We say, sir, 5 electrons are being released, 5 electrons are being donated. That's why number of electrons is equal to the number of donor ions. Is this crystalline clear? Is this crystalline clear? Okay. Is this crystalline clear? Let me know in the chats, guys.
Conductivity of a semiconductor increases on doping. Doping, what does doping mean? When it comes to the doping, doping means adding impurity. Adding the impurity. Okay. It says conductivity of a semiconductor increases on doping. Okay. So we say if we keep on adding the doping, if we keep on if we keep on adding the impurity, we say number of electrons have been added by impurity. So we say if number of electrons increase, we say conductivity increase. So assertion is correct. What is reason? Doping raises the temperature of semiconductor. No. How can doping raise the temperature of a semiconductor? No, this is false. Assertion is correct, reason is false, means option C. A means when assertion is correct, reason is correct, and reason is the correct explanation of assertion. B means assertion is correct, reason is correct, but reason is not the correct explanation of assertion. C means assertion is correct, reason is false. D means both are false. Do you agree with me, guys? Tell me in the chats. Do you agree with me? Yes, yes. Let's talk about p-type semiconductor. Let's talk about p-type semiconductor. See, when it comes to the p-type semiconductor, you take a pure semiconductor over here, okay? Like germanium, okay? Pure crystal of germanium. And in this case, what you are supposed to do is that you add the impurity that is boron, boron impurity. Boron is this is a pentavalent impurity. Pentavalent impurity means which has got 5 valence electrons. This is a pentavalent impurity. And this is, we say boron is, we say trivalent impurity. See, so if you are adding the boron, this is a trivalent impurity. So if you are adding the boron, guys, so in order to fit in the boron over here, how many electrons are required? We say, sir, 1, 2, 3, 4. But it has got only 3. So what it will do is that once we add the boron over here, listen to me very carefully. Once we add the boron over here, we say in this case, this boron will gain 1 electron. This boron will gain 1 electron. And if it gains 1 electron, we say it will become boron negative. It will become boron negative. Okay. It will become boron negative. That is, we say negative acceptor ion, negative acceptor ion. So if we are adding the boron over here, boron has only got 3 valence electrons, but requirement is 4. So it will gain 1 electron. Who is going to donate him the 1 electron? We say germanium. So if we are adding the boron over here, boron negative. So boron was having this one, and this one. So one of the germanium will actually give him the electron and it will take it something like this. Now, over here, hole will be created. So can I say in this particular case, sir, on adding 1 boron, 1 hole is created? Yes. On adding millions of boron, millions of holes are created. We say on adding millions of boron, millions of holes are created. Millions of holes are created. Okay. Millions of holes are created. Now guys, my dear friends, can I say in this particular case, remember my dear friends, hole is the majority charge carriers. Number of holes is the majority charge carriers in this one. Why?
because on adding borons, holes are created. And electron in this case is minority charge carriers. Electron in this case is minority charge carriers. On adding the electrons, we say, sir, on adding the impure, let's suppose at room temperature, it was having some electrons and some holes. Now, if you add impurity, holes increase, electron remains the same. So we say in this case, number of holes is much greater than number of electrons. Number of holes is much greater than number of electrons. And number of, listen to me very carefully, number of acceptor ions is equal to the number of holes. Number of acceptor ions is equal to the number of holes. Okay? Number of acceptor ions is equal to the number of holes. What does number of acceptor ions mean? Acceptor ions means boron. If you add 5 borons, 5 holes will be created. So that is Na is equal to NH. And one more important thing I just want to tell you. Could you please tell me what will be the net charge in this case? As holes have increased, holes have got positive charge. So what will be the net charge in the chats? Net charge in this case will be 0. Okay. In the previous case also, here also we say net charge is 0. Don't say net charge is negative. Why? Because number of positive donor ions is equal to the number of electrons. If you are adding 5 positive charge, 5 electrons are created. So again, net charge remains 0, same. Here also, we say if you are adding 5 acceptor ions, okay, 5 boron, we say 5 holes are created. So 5 negative charge, 5 positive charge, net charge again 0. So let's take a break, my dear friends. Break till we say 7:30. Huh? Break till 7:30 p.m. Let's do the iftari now, okay?
We're back. So we are given over here the question we have on the screen. Okay. Guys, hit the like button if you have not liked the session yet. We are given a question on the screen. For a given applied voltage, conduction current in N-type semiconductor is more than that in P-type semiconductor. See, when we talk about N-type semiconductor, okay, in case of N-type semiconductor, we say majority charge carriers. Majority charge carriers are electrons, okay. Similarly, if we talk about P-type semiconductor, in case of P-type semiconductor, we say majority charge carriers. Majority charge carriers are, we say, holes. Okay. And I have told you before, mobility of electrons is greater than mobility of holes. So if mobility of electrons is greater than mobility of holes, so we say conduction, current due to the electrons is greater than current due to the holes. The one which is free to move will constitute more current as compared to the one which is less free to move. Okay. So we say in this particular question, assertion is correct. Assertion is correct. For a given applied voltage, current in N-type semiconductor is more than that in P-type semiconductor. The reason is mobility of electrons is greater than mobility of holes. This is also correct. So option A. So option A. This was asked in NEET 2019. In this, the question says that which of the following statement is true for P-type semiconductors? Electrons are majority carriers and trivalent atoms are the dopants. In case of the P-type semiconductor, we say, sir, majority charge carriers are holes and trivalent atoms are the dopants. Holes are the majority charge carriers, pentavalent atoms are the dopants. No. Holes are the majority charge carriers and trivalent atoms are the dopants. I guess B is matching. Electrons are majority. No. This one. No, this one. Option B. Option B. Okay. Let's move on to the next question. This was the question which was asked in NEET 2013. In an N-type semiconductor, which of the following statements is true? Holes are majority charge carriers. Holes are majority charge carriers. Trivalent atoms are the dopants. Trivalent atoms are the dopants. Okay. Electrons are majority charge. Holes are majority charge carriers. Wrong. Electrons are majority charge carriers. Trivalent atoms are the dopants. Electrons are minority charge carriers. This is also wrong. Electrons are minority charge carriers. Pentavalent atoms are the dopants. Holes are minority charge carriers. Pentavalent atoms are the dopants. This is correct. Option D is correct. Option D. Yes. Great, great, great. Now let's talk about the PN junction diode. Let's talk about the PN junction diode. See. Guys, if we have got a P-type semiconductor over here, this is the P-type semiconductor we have got. And if we have got an N-type semiconductor over here, if they are joined together, this is what we call PN junction diode. If P-type semiconductor and N-type semiconductor are combined together, joined together, that's what we call the PN junction diode. Okay. Now, my dear friends, listen to me very, very, very carefully in this case. When it comes to the P-type semiconductor, we know, sir, holes are the majority charge carriers. These are the holes which are majority charge carriers. Okay. And when it comes to the N-type semiconductor, we say electrons are the majority charge carriers. These are the electrons. Sir, what is this negative, negative, negative? Guys, remember when we were studying the when we were studying the P and N type semiconductor, let me take you back. See, in case of N type semiconductor, you have added phosphorus positive and electron is added. On adding one phosphorus, one electron is added. On adding two phosphorus, two electrons are added. On adding millions of phosphorus negative, millions of electrons are basically added. Sorry, phosphorus positive. Millions of electrons are added. Similarly, in case of P-type semiconductor, on adding boron negative, we say one hole is created. On adding millions of borons, millions of holes are created. So that is what is mentioned exactly over here. Come on to this one. We say, sir, this is hole and this is, we say, boron negative. This is, we say, hole. This is, we say, boron negative. This is hole. This is, we say, boron negative. Hole, we say, boron negative. These are the fixed ions. These are the fixed ions. Okay. As boron was fixed, that was bonded. That was bonded. Now, in case of N-type semiconductor, we say, sir, this is electron. This is electron. And this is phosphorus positive. This is phosphorus positive. This is electron, phosphorus positive. Electron, phosphorus positive. So we say electrons are majority. Okay. Now, my dear friends, what happens in this particular case is, what happens when you join P and N-type semiconductor, these electrons will see holes. So they will get recombined into the holes. These electrons will get recombined into the holes. So they will get occupied into the holes when they connect, when they are connected with each other. Okay. Now, when these electrons will go over there, okay, when these electrons will go over there, we say now negative charge will come on to this one. This is negative, negative, negative. Now negative charge will come on to this side, and it was electron plus this fixed ion positive charge. Only positive will remain because electron has shifted. Positive charge, positive charge. Now, this is what we call depletion region. This depletion region is formed. Depletion region is formed. And in this depletion region, electric field will be set up from positive charge towards negative charge. Guys, when electrons are shifted towards P side, only what remains from this side? Only positive charge, and positive charge. And from this side, negative charge will be occupied. So electric field will be set up from positive to negative. Depletion region will be created in this case. Okay. Now, my dear friends, listen to me very carefully. Don't you think that in this particular case, when electrons move from N to P, we say, sir, charge is moving, electrons are moving, so current is produced. Yes, sir. Yes, sir. So I say, diffusion, that is diffusion current is produced due to the recombination of electrons and holes. Okay. Due to the recombination of electrons and holes. When holes move from P side to N side. Okay. When holes move from, N side to P side. Yes, P side to N side. Electrons move from N side to P side. Listen to me very carefully. We say diffusion current will be produced. We say because of that. Okay. And drift current is produced. Drift current is produced. Electric field in the depletion region, which makes the minority charge carriers to move. My dear friends, listen to me very carefully. When electrons and holes are recombined, electrons move from this end to this end, holes move from this end to this end. Listen to me very carefully. Remember this point. If the direction of motion of electrons is this, we say current will be opposite. If the direction of positive charge is this, we say direction of current will be also the same. So in this case, when electron-hole recombination take place, we say current is produced because of that. That current is what we call the diffusion current. Okay. So diffusion current is from P side to N side. Okay. Now, when the depletion region is formed, can you tell me in case of P-type semiconductor, what is minority? We say minority are electrons. If you remember, in case of
N-type semiconductor, what is minority? Minority are the holes. Minority are the holes. Now, because of this electric field, we say electric field will basically apply the force on minority charge carriers. So I have mentioned over here, I drift is produced because of the electric field, because electric field will make the minority charge carriers to move. Because of that, drift current will be produced from N to P. Diffusion current is from P to N, but drift current is from N to P. Drift current is from N to P. And this drift current is because of this electric field. Because when these minority carriers move something like this, current will be produced in the opposite direction from N to P. But when it comes to the diffusion current, electrons move something like this, current will be produced from P to N. That's the reason over here. Diffusion current is from P to N, drift current is from N to P, and overall we say net current in this case will be 0. In case of PN junction diode, we say net current in this case will be 0. Net current in this case will be 0. Okay. Now, my dear friends, let's talk about the forward bias. Let's talk about the forward bias. See. If I say I have got a semiconductor over here, this is the semiconductor which I have. This is the P-type P side, and this is, we say, N side over here. Okay. Now, my dear friends, we say this is the PN junction diode. This is the PN junction diode. And we say this is the P side, holes are majority charge carriers. And this is the N side, electrons are the majority charge carriers. Okay. Now, guys, we know, sir, depletion region will be formed in this case. Positive side will be from this, negative will be from this. What we are doing in this case is we are connecting a battery to this particular circuit. We are connecting a battery to this particular PN junction diode. But positive terminal of the battery is connected to P side. Negative terminal of the battery is connected to N side. Okay. My dear friends, if positive terminal is connected to P side, let me just write over here. When positive terminal is connected to P side and negative terminal is connected to N side, when positive terminal is connected to P side and negative terminal is connected to N side, it is called forward bias. It is called forward bias. When positive terminal is connected to P side and negative terminal is connected to N side, this is what we call the forward bias. This is what we call the forward bias. Okay. Now see, my dear friends, this is what we call the forward bias. Now, what happens in this particular case is when depletion region in this particular case, what's gonna happen? See. Sir, when positive terminal is connected to P side, positive terminal will kind of send the positive charge onto this. Negative terminal will send kind of negative charge from this side. Sir, this positive charge will repel the holes because holes also have positive charge. This negative charge will also repel the electrons. Electrons have got negative charge. So, on repelling this, depletion region will decrease. We say, sir, when depletion region decreases, if this depletion region decreases, once again electron-hole recombination will take place. Once again electron-hole recombination will take place. We say the electrons of N side and holes of P side will start recombining. As soon as the depletion region decreases, we say electron-hole recombination takes place once again. Okay. Now the question is, if these electrons will come onto this, where will these electrons then go? Because of the battery, it will catch these electrons and make them flow something like this and will send back to this n side. Once again, these electrons will shift over here. Again, they will travel in a loop, come over here. Once again, they are shifted to this side. Again, they come in a loop. And this is the case. This is the way in which we say current flows in case of forward bias. Okay, this is how current flows in the forward bias. Okay, battery will make the electrons flow to n side once again. Battery will take these electrons and will send it to n side once again, and will send it to n side once again. Okay, this is the procedure of current flow in case of forward bias. This is how current flows in the forward bias. And if somebody wants to make the graph between current versus voltage, the graph will be something like this. The graph will be something like this. See, I'll make you understand this graph. Let's suppose initially you are sending less charge, less potential difference means less charge from this side, less from this side. We say less depletion region will decrease, so less electron hole recombination will take place, so less current will be produced. If less current is produced, so graph will be something like this, less current. As you keep on sending more charge to this, we say current will start increasing, And at certain value, we say, sir, current will be large. This potential is what we call the barrier potential. This potential is what we call barrier potential. This potential is what we call the barrier potential. When you reach the barrier potential value, we say in that case, current will become the large. You have sent enough charge over here. Now current is very large in that particular case. Okay. And if you have, this is the symbol of PN junction diode. This is the symbol of PN junction diode. This is P side, this is N side. Okay. And when it comes to the forward bias, this is, we say, how do we represent this? This is, we say, forward bias. This is, we say, forward bias. Okay. Now let's talk about the reverse bias. What does reverse bias say? Let's suppose we have got a PN junction diode over here. Okay. Reverse bias means when negative terminal is connected to P side and positive terminal is connected to, we say N side. Okay. So we say over here. So let me just draw it. This will be negative side. This is positive side. Okay. When negative terminal is connected to P side and positive terminal is connected to N side, we say this is what we call the reverse bias. In this case, depletion region will increase. Why? Because if you send the positive charge onto this side, okay, positive terminal is connected, it will attract these electrons. And if you send the negative charge onto this side, it will attract these electrons. This negative charge will attract the holes. We said depletion region in this case will increase. Okay. So do you think that current electron hole recombination is possible? No, in this case, electron hole recombination is not possible. If electron hole recombination is not possible, will the current flow? In this case, current will not flow. Okay. Now, my dear friends, listen to me very carefully. If current is not flowing, we say in case of reverse bias, the graph between current will be something like this. See, the graph, this is constant. It is having the very small current, minute current, extremely small. Okay. Now, listen to me very carefully. These electrons, this charge, these are, we say, the bonded, this is the bonded charge over here. Now,
as you keep on increasing the negative charge, as you keep on increasing the, voltage, okay? Like positive charge over here, negative charge over here. Electric field is getting stronger. Electric field is getting stronger. This electric field and this electric field are in the same direction, okay? This electric field and this electric field are in the same direction. We say electric field in the depletion region will again increase, okay? Now, my dear friends, listen to me very carefully. We say, sir, as we keep on increasing, as we keep on increasing the potential difference, as we keep on increasing the potential difference, at certain value of potential difference, we say bonds in the depletion region break. Bonds in the depletion region break and current, bonds in the depletion region break. These electrons will basically start flowing. This negative charge will start flowing and current is produced. Current is produced, but that will be also very small as compared to forward current. That will be very small as compared to the forward current. What I'm trying to say is that, see, because of this reverse bias, depletion region increase. So electron hole recombination is not possible. So current will be zero. Now, what I'm trying to say in this particular case is, we say you keep on increasing the electric field. As electric field gets stronger over here, this negative charge will be attracted towards the left in the opposite direction because of this electric field. So now this charge will start flowing and current will start increasing. And the graph in that case, at that potential at which bonds will break is what we call the breakdown voltage. That potential at which bonds break, that potential at which bonds break is called breakdown voltage. Is called breakdown voltage. Okay. At this breakdown voltage, you can clearly say current has increased in large amounts. And my dear friends, but this current is very small as compared to the forward current. Okay. As compared to the forward current. I hope this is clear. This is basically the reverse bias. If you have got a diode over here, you are connecting this negative terminal to P side. This is the P side and this is N side, positive terminal to N side. This is the reverse bias. Okay, this is the reverse bias. In an unbiased PN junction diode, holes diffuse from P region to N region. If you have got unbiased PN junction diode, in case of PN, okay, so P type has got majority charge carriers as holes, N type has got majority charge carriers as electrons. So we say these electrons, these holes are shifted from P to N, electrons are shifted from N to P. In an unbiased PN junction diode, holes diffuse from P region to N region. This is correct. This is correct. And when it comes to the reason, hole concentration is P region is more as compared to the N region. Region is also correct. The reason is also correct. Reason is also correct. So A is the correct option. Tell me in the chats, is this clear, guys? Is this clear? Everybody out there, let me know as soon as possible. The NEET 2020.
The increase in the width of the depletion region in PN junction diode is due to reverse bias only. Reverse bias only. Reverse bias only. Next, 2017 question. Which of the following represents forward bias diode? Which of the following represents forward bias diode? NEET 2017. See, you have to see if P side is connected to higher potential, N side is connected to lower potential, means that is forward bias. This is 3 volt, this is 5 volt. This is higher potential, this is lower potential. Okay, so we say this is P side, this is N side. N side is connected to higher potential, so this is reverse bias. In this case, this is 0 volt, this is minus 2 volt. So this is higher potential, okay? And this is lower potential. This is forward bias. This is minus 4 volt and this is minus 3 volt. No, this is reverse bias, okay? Minus 3 and this is minus 4. This is minus 2 and this is plus 2. This is also reverse bias. Option B is the correct option. Let's move on to the next one. Can you tell me in this question, in the following circuit, which diode is forward biased? See, this is 0, this is minus 2. So this is forward biased. This is 0, this is 2, this is reverse biased because this is P side, this is N side. If P side is connected to higher potential, that is forward biased. This is minus 5, this is minus 2. So we say this is reverse bias. This is 512, this is also reverse bias. So we say option A. This question, we have got the 2 diodes over here. I hope this is visible. Okay. See, in this particular case, you can clearly see, sir, diode 2 here, D2 is reverse bias. Reverse bias. Okay. So if D2 is reverse bias, no current flows through D2. So current will be 0 through we say, sir, through D2. Through this D2 diode, there will be no current. Why? Because it is reverse bias. In case of reverse bias, current is 0. So current will be through this diode only. So can I say, sir, I is equal to V divided by R. V is how much? That is 5 divided by resistance is how much over here? That is 10. 5 by 10. That is 1 by 2. That is 0.5 ampere. So current in this case is 0.5 ampere. 0.5 ampere. Let's talk about this half wave rectifier. Sir, what does rectifier actually mean? See, when it comes to the rectifier, we say a simple instrument which converts AC into DC. It is a simple instrument which converts alternating current into direct current. What is alternating current? It is a bidirectional current. That current which flows in 2 directions. Okay. Like, can you tell me, sir, how does alternating current actually look like? This is alternating current. It is positive also. It is negative also. Sir, what is direct current? This is direct current. It is positive only. It is positive only. This is also direct current. It is positive. Current is not from the lower side. So we say it is an instrument which converts AC into DC. So means, my dear friends, when it comes to the AC, let's suppose I have got an AC source over here. This AC source sends the current in this direction. It can send the current in this direction also. This cycle you can consider as or negative. This cycle you can consider as positive. Now, but when it comes to the DC source, it sends the positive cycle only. Okay. Now, see in this particular case, sir, we say over here, this is the current which is entering this. This is, we say, half wave rectifier. So over here, you have got a transformer. You have got a diode over here attached to this one. And then you have got resistance. Okay. So the input in this case, you are giving an AC. See, this is positive as well as negative. See, this is positive as well as negative. Now, we say, sir, positive cycle means the current is positive. So we say positive cycle will go from this side, okay? And negative cycle will go from this side.
This cycle can easily flow in the loop, but this negative cycle cannot flow. Why? Because for this current, this is forward bias. This is forward bias. Remember, reverse bias. Remember one thing, guys. Remember, if I say you have got a diode something like this, current can enter the diode from back side and it can leave from front side, not a problem. But if I say you have got a diode something like this and current is entering from front side, we say this current cannot flow through the diode. This current cannot flow through the diode. Keep that thing in your mind. Okay? This current cannot flow through the diode. Same is the case over here. We say this current, positive cycle can easily flow. Negative cycle cannot flow through this diode because for this cycle, this is the reverse biased. In reverse bias, current does not flow. Okay. So only positive cycle will be allowed, only positive cycle. Negative cycle, see, this negative cycle is cancelled. Only positive cycle is allowed. So this is a DC, but this is not a good DC because it is getting 0 for some time, again maximum, then 0 for some time. Okay. Then we say full wave rectifier. See, in case of full wave rectifier, we call this as full wave rectifier. We have got this cycle over here. Okay. My dear friends, this full wave rectifier converts the positive cycle also into the negative cycle. Sorry, negative into the positive. Let's suppose we have got an alternating current, something like this. This is positive cycle and this is negative cycle. Now, when the current enters this particular full wave rectifier, we say positive cycle will go from this side and listen to me very carefully. This positive cycle can flow easily through the diode 1 and it wants to go from this path. It would want to go through this part, but no, it cannot go. Why? Because this is N side, current cannot enter through N side. So this current I can go something like this in the load, okay, and flow through like this. Because current always flow in the closed loop, okay. So positive cycle is passed. Positive cycle is passed. Let me make the graph. Let me make the graph over here. Positive cycle is passed. 1. What about the negative cycle? Let's see. Sir, when the negative cycle flow from this side, so it can go pass through this diode, as this diode is forward biased for this current, because current can enter from the back side. Now, it can't go over here. Why? Because current cannot enter from the front side. Current can enter from back side. Now, this current will flow, and it will go something like this. It will go something like this. This will be the path. This will be the path. Which one? I'll show you with another color. This will be the path of current to negative cycle. So negative cycle also flows in the loop. So we say negative cycle also becomes positive over here. Then another positive, then another negative. So this is, we say, sir, DC supply, because this is positive only. Current is flowing in one direction only. Okay. Is that clear? Okay. Now see. So we say full wave rectifier. In case of full wave rectifier, positive cycle is also allowed. Negative cycle is also allowed, but this negative cycle also becomes the positive cycle. In case of half wave rectifier, we say only positive cycle is allowed, negative cycle gets cancelled. Now, my dear friends, this is also not the good supply. Why? Because current is becoming maximum, then 0. Again maximum, then 0. So we need some supply, something like this, constant. So we say what we do is that we use the capacitive filter. Let's use the capacitive filter. We don't go in much detail. After using the capacitive filter, we say the output in this case will be something like this. After using the, in case of full wave rectifier, if we use a capacitor over here, capacitive filter means capacitor over here, we say the supply becomes constant. So after using the full wave rectifier, after using the capacitive filter in full wave rectifier, we say output becomes almost constant. Almost constant. So this will be the graph in that case. Then we have the Xenar diode. Okay. Then we have the Xenar diode. What does Xenar diode actually mean? We said this Xenar diode is simply, it is used as a voltage regulator. What does voltage regulator actually mean? Voltage regulator simply means voltage stabilizer. Like you have the transformer at your home. What is the work of the transformer? See, let's suppose you have got the refrigerator at your home. This is the refrigerator, okay? And you connect the transformer to this refrigerator. So the supply coming from the outside goes into the transformer. Then this transformer sends the supply to the refrigerator. Why? Because if the supply from the outside is low, this will step up that. It will maintain the voltage to this one. If 200 voltage is required to work so that this refrigerator should work properly, this will provide 200 voltage. If large voltage is coming from the outside, it will maintain, it will send only 200 to this one. This is what we call the stabilizer or transformer. Okay. Now, my dear friends, we say this Xenar diode works exactly like voltage stabilizer. See. Let's suppose I say I have got a television, a resistance. This is resistance, but this is actually television. Load, television has resistance. Let's suppose this is a television. I am saying that across this television, voltage should be 200 volts. Voltage should be 200 volts. What will I do? What I will do is that I will connect a Xenar diode. This is, we say, sir, this is Xenar diode. This is the symbol of Xenar diode. I will connect a Xenar diode over here, okay, parallel to this. But this Xenar diode has got the voltage of how much? We say, sir, VZ is 200 volts. In market, if you go to the market over there, you will be able to find different Xenar diodes. Some Xenar diodes will be having, sir, we say voltage of 20 volts. Some may be having 10 volts. Sir, what is the difference? This can maintain 10 volt potential difference. This can maintain 20 volt potential difference. This is the difference. Similarly, if you want to maintain 200 volt potential difference over here, you have to buy that Xenar diode from the market, which has got 200 volts potential difference, which has got 200 volts potential difference. Okay. Then only it can maintain the voltage across this one. That's it. This is the working of Xenar diode. Now listen to me very carefully. Similarly, see, this Xenar diode can maintain 20 volts potential difference across the load. This Xenar diode can maintain 10 volts potential difference across the load. Okay, now let's suppose if I say find the current in Xenar diode. Listen to me very carefully. Find the current in Xenar diode. Okay. Now see. See, I have to find the current in the Xenar diode. Okay. See, we have connected a 20 volt battery. This is 100 volt resistance, and this VZ voltage of this Xenar diode, this is fixed. This is constant. Okay. 15 volts means it can maintain 15 volts potential difference. This Xenar diode can maintain 15 volts potential difference. Okay. Remember this directly. Okay. Now, my dear friends, listen to me very carefully. This is the breakdown voltage of Xenar diode, means it is constant. If you are sending 20 volts,
Sir, 15 volts will be maintained across this one. Why? Because you have used 15 volt Xenar diode. So how much is remaining? 5. So 5 will be given to this one. This is 5 volts. Now guys, if I say I is the current you are sending, the battery is sending I current. IZ will be the current in Xenar diode and IL will be the current in this load. Can I say, my dear friends, what will be the value of current over here? We say, sir, I will be V by R. V in this case is 5, R in this case is 100. Okay. What is the current in the load? We say, sir, listen to me very carefully. If across this voltage is 15 volt, don't you think this is parallel to this one? In case of parallel combination, voltage remains same. In case of parallel combination, voltage remains same. So across this one also voltage will be 15. So we say IL is 15 divided by, we say, sir, 500. So this will be 3 by 100. Okay. I is IL. Now can I say, sir, this current IL gets split into IZ and IL. So this will be IZ plus IL. If we have to find IZ, we can write I minus IL. So this IZ will be simply, what is the value of IL? What is the value of I? That will be 5 divided by 100 minus 3 divided by 100. So this will be 2 by 100 ampere. So current in this Xenar diode will be 2 by 100. An important question which was asked in J Mains 2020. An important question which was asked in J Mains 2020. See, you have got a figure over here. Is this visible, guys? Is this figure visible? Is this figure visible? Tell me in the chats. Or shall I make the new one over here? Is this figure visible? This is, you have got a Xenar diode over here. One more Xenar diode over here. Okay, this is 4 volts. This is 6 volts. This is 100 ohms. And then you have got the load resistance over here. This load is 400 ohms. And then this is the output voltage. This is the output. Okay. Okay. And this is the input. This is the next level question that I have put up over here. This is V input. Now listen to me very carefully. Listen to me very carefully. Let's suppose, my dear friends, I am saying we are supposed to plot the graph between output voltage and time. Output voltage and time. Okay. Now see. If I am saying that you are giving the, see, this Xenar diode has got 6 volts. This is 4 volts. Means this can maintain the voltage of 6 volts. Okay. Sir, what if you give less voltage than 6 volts? We say, sir, in that case, it will behave as open wire. Open wire. No current will flow through this one. Okay. No current will flow through this one. Now, my dear friends, we say, listen to me very carefully. Listen to me very carefully. Listen to me very carefully. We say, if you give input voltage in this case, let's suppose you are supposed to make the graph between V output and time. Let's suppose if you give input voltage over here, 1 volt. Okay, 1 volt. What will be the value of output voltage? Sir, if you are giving 1 volt, output will be directly 1 volt over here. Okay. Because this will maintain the voltage across it when you give 6 volts to it. When you give 6 volts to it. Okay. Okay. So we say V output in this case is 1 volt. Okay. V output is 1 volt. Okay. The graph will be straight line. If you give V input as 2 volts, V output is also 2 volts. So graph will be straight line. If you give V output as input as 3 volts, V output is also, we say, sir, 3 volts. Graph will be straight line. Okay. Okay. Now, if you give 4 volts voltage, once again, we say graph will be the straight line. V output will be also 4 volts. Now, my dear friends, if you give V output as 5 volts, now at 4 volts, this gets activated, this one. It will maintain the potential difference across it as 4 volts, okay? If you give 5 volts, so it will maintain 4 volts across it only. If you are giving input as 5, 4 will be across this, 1 will be across the resistance, 4 plus 1 is 5. So output in general between this point and this point will be between this point and this point, that will be 5 volts. If you give 6 volts over here, we say output will be in this case, output will be in this case. Now see, output, if once you give the 6 volts over here, listen to me very carefully. Sir, now this gets activated, means this will maintain 6 volt potential difference across it. So if across this is 6, across this will be 6 because both are in parallel, across this will be 6, across this will be 6. Let's suppose if you give 7 volts, what will be the output? We say, sir, if you are giving input as 7 volts, this will maintain 6 volts only. So at 6 volts, we say graph will be constant. So this will be 6 volts. So option D is the correct option. I hope this is clear. You don't have to mark this. This is not the correct option. You say, sir, at 4 volts, this gets activated. It will keep on maintaining 4 volts only. No. We say when this is 4, it has got the resistance in series with it. Even if you give 5 volts, 1 will be shared with this one. 5 plus 1 is 6. 4 plus 1 is 5. And when you give 6, it will maintain 6 across each load. It will be 6. Is that clear? Is that clear? Let me know in the chats if this is clear. Let's move on to the Boolean algebra. See, in case of Boolean algebra, what do we have to study? What do we have to learn? Now see, what does this Boolean algebra mean? I'll tell you. You will be given a device. In this one you will be given different devices. In those devices, if you give some input, this device will produce the output. As simple as that. In this Boolean algebra, we have to study about different devices, different instruments, different gates, like we'll see OR gate, AND gate, NOT gate, okay? So you will be given a device, you will have a device, and in that device, if you give some input, it will produce the output. Now the question is, what kind of input will be this? We say that will be digital input or a digital signal, okay? The input that you need to give over here can be either 0 or can be either 1. It will be in the form of 0 or 1. Once again, I am saying, in case of Boolean algebra, we have to study about different devices. In those devices, we give some input, it gives us the output. These inputs and outputs will be in the form of 0 and 1. Okay, 0 means 0 volts, 1 means 5 volts. Okay, 0 means also low, or it also means off. 5 volts means high, or it also means on. You guys need to remember this. Okay, you guys need to remember this. Okay, next. This is, we say, addition of Boolean algebra. In Boolean algebra, multiplication and we say inverse. Like you have studied, we are in the LKG right now. Okay, LKG. You might have studied in your class LKG nursery, 1 plus 1 is 2, 5 plus 4 is 9. Okay, basic mathematics over there. Same is the case. Once again, we have to learn. But this is the Boolean algebra. This is the addition of these digital signals and subtraction of
sorry, multiplication of these digital signals. Okay. Okay. Now see, let's suppose if we give an input signal, let's suppose we have got a device over here. Input signal in that case is 0. This is 0 and this is 0. What will be output? We say, sir, 0 plus 0 is 0. Simple addition. Low plus low is low. Sir, 0 plus 1 is 1. You have to remember all of this. Sir, 1 plus 1 is 1. Sir, A plus 0 is A. Sir, you were saying before some time, this digital signal can be either 0 or 1. What is this A? A is also 0 or 1. Let me show you over here. If I say A plus 0, what is the value of A plus 0? See, if I say if A is equal to 0, keep A 0. So it will be 0 plus 0 is equal to 0. 0 plus 0 is equal to 0. If I say if A is equal to 1, if A is equal to 1, keep A is 1 plus 0. 1 plus 0 is equal to 1. 1 plus 0 is equal to 1. Now see, A is having two values. This quantity is having two values over here. Okay. It is having value 0. It is having value 1. So it can have either value 0. It can have either value 1. So we say overall A plus 0 is, we say A. The value of A can be 0 or the value of A can be 1. That's why I have mentioned A plus 0. A plus 0 is A. Sir, let's talk about A plus 1. See, this is A plus 1. If we place A is equal to 1, let's suppose if A is equal to 1, 1 plus 1 is 1. If we place A is equal to 0, 0 plus 1 is 1. In both the cases, answer is coming out to be 1. That's why we have mentioned A plus 1 is 1. That's why we have mentioned A plus 1 is 1. Now see, if we say, sir, A plus B plus B plus A bar plus B, ultimately, if you do plus 1 at the end, it will be 1. Now, A plus A bar. What is A bar? See, if I say this is 1, 1 bar means a reciprocal of this one. Okay, not the reciprocal, just the inverse of this one. Inverse of this one is 0. And 0 bar will be 1. Okay. Similarly, A bar is the reverse of A. A double bar is A. A plus A bar is 1. Similarly, you have to see this. 0 into 0 is 0. 0 into 1 is 0. 1 into 1 is 1. A into 0 is 0. A into 1 is 1. A into A bar is 0. Okay. Done. Let's move on to the next one. De Morgan's law. De Morgan's law. What does De Morgan's law actually say? De Morgan's law says that if you have a quantity A plus B, if you have a quantity A plus B whole bar, and there is a bar on this particular quantity over here. Okay. Now, if you want to break this particular bar, you can break it. You can write it A bar dot B bar. It says that if you want to break this bar, you can break this bar A bar B bar, but this addition sign will be changed into multiplication. Similarly, like you have over here, A dot B whole bar. You can break this bar, but this addition multiplication sign will be changed into addition. This is the De Morgan's law. Commutative law, it says A plus B is B plus A. Okay. Associative law, it says A plus B plus C. Bracket is over here for B plus C. We can write it A plus B plus C, bracket for these two. Okay. Then we say distributive law. A dot B plus C is A dot B plus A dot C. Let's talk about the gates. Tell me in the chats, is this clear till over here? Everyone means everyone. Is this clear till over here? All the people out there. Is this clear? Guys, if you have not liked the session, like it as soon as possible.
Now we need to learn all those gates. Okay. So gate is a device. We give input that will provide the output. That will provide the output. Now listen to me very, very, very carefully. Let's talk about, we say we have got three fundamental gates. The first one is the second. Okay. It is based on inverse operation. What does that mean? I'll tell you. We say we have got the three fundamental gates over here. Okay. And then we have the universal gates. We say universal gates means NAND gate, and then we say NOR gate. We'll see all one by one. First of all, we'll talk about the NOT gate. Sir, what is the work of the NOT gate? Okay, what is the work of the NOT gate? Let's suppose this gate is basically a device in which we give input, it provides output. Now, what is the work of this? First of all, this is the symbol of NOT gate. This is the symbol of NOT gate. Its work is, if you give the input A, it will do the inverse of A. Okay? It will do the inverse of A. So its Boolean expression is Y is equal to A bar. Its job is to do inverse. I'll just write over here. Its work is to do inverse. Its work is to do inverse. Okay. Okay. So if we talk about the truth table, my dear friends, if you give input A, it will give output as A bar. Means if you give 0 input, it will give 1 as output. Okay. Reverse of 0. If you give 1 input, it will give you 0 as output. Okay. Now, electrical equivalent circuit of NOT gate. Sir, that circuit which exactly works like NOT gate. Let's suppose we have got this circuit over here. See. In this particular case, we say this is switch, that is key, this is switch, and this is bulb. See, I'll tell you. Let's suppose if you switch on, if you close the switch over here, so current will leave from the battery. This bulb has resistance. Current would never want to flow through that path where there is resistance. So that will prefer this path where there is no resistance. Okay, where there is no resistance. So means, my dear friend, if current is leaving, it follows this particular path. So current does not go into the bulb. So means, my dear friends, we say if you switch on the key, on means 1. I told you in that case, digital signals, on means 1. Okay. Off means 0. So we say bulb will remain off, 1, 0. And if I say, if you keep the key on, matlab off, if you keep it off, so we say current will flow through the bulb. In that case, we say bulb will remain on. Now 1, 0, 0, 1. See, 1, 0, 0, 1. This is the truth table of NOT gate. Means this circuit is exactly working like NOT gate. That's why we call it the electrical equivalent circuit of NOT gate. Then we say we have the OR gate. The symbol of OR gate is this one. This is the symbol of OR gate. What is the work of OR gate? If you give the input A, if you give the input B, its work is to do the addition. Y is equal to A plus B. Y is equal to A plus B. Its work is to do the addition. Its work is to do the addition. Okay. Then it comes the truth table. If we make the truth table over here, my dear friends, okay, we say this is A input, this is B input. This is output, Y is equal to A plus B. Let's suppose you give 0. Another input is also 0. 0 plus 0 is 0. Let's suppose you give input 1. Another input is also 1. 1 plus 0 is 1. Let's suppose another input you are giving 0. 0, another input we are giving 1. This is 1. 0 plus 1 is 1. 1 plus 1 is 1. Okay, you can mention it exactly over here. Okay, you can mention it exactly over here. Okay. Is that clear? Is that clear? And you can also mention one point in this case. What is that? We say output is low. See, output is low when both the inputs are low. When both the inputs are low. Okay. And output is high. Output is high when any of the two inputs is high. When any of the two inputs is high. Okay. Next, electrical equivalent circuit of NOT gate, of OR gate. Electrical equivalent circuit of OR gate. Electrical equivalent circuit of OR gate. See, we make a circuit something like this. We make a circuit something like this. This is the key 1, this is key 2, and this is the bulb. Guys, see. I say, if you keep this key off, if you keep this key on, you connect this and you keep off. So current will go, and it will flow through this one and bulb will glow. Okay. So let me make it over here. I'll make it separately over here. This is K1, this is K2, and this is bulb. If I say K1 is, let's suppose, on, K2 is, let's suppose, off, will the bulb glow? Yes. So current will go and will follow this path and enter the bulb. Bulb will glow. It is 1. And if I say this is off, this is on, 0, 1, in that case also bulb will glow. If I say both are on, then in that case also bulb will glow. If I say both are off, this is off, this is off, current cannot flow through this path, so bulb remains off. Now see, this truth table is exactly like this truth table. Means what I can say in this case, this circuit is exactly working like the OR gate. This circuit is exactly working like the OR gate. Okay. Then we say, let's talk about the AND gate. Sir, what is the work of AND gate? Its job is to do the multiplication. Y is equal to A dot B. Okay. Now, if you give the input, let's suppose 0. Another input is 0. So 0 into 0 is 0. Now, 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. So can I write in this case? Output is high when both the inputs are high. Output is high when both the inputs are high. Both the inputs are high. See, when this is 1, then only output is 1. And output is low. Output is low when any of the two inputs is low. When any of the two inputs is low. Okay. Electrical equivalent circuit of AND gate. Okay. Guys, this is the key 1, this is the key 2. And if I have to make the truth table over here, let me make the truth table over here. We say this is, we call K1, this is K2, and this is bulb. Let's suppose if I am keeping K1 on, K2 off, will the bulb glow? No. If this is on, this is off, so current cannot flow further. So no current flows through the bulb, it remains off. Okay. Similarly, if I say, my dear friends, in this particular case, this is off, this is on, still bulb is off. If both are off, bulb is off. If both are on, bulb is on. This truth table is exactly like this truth table. So that's why we say this is the circuit which works like which gate? AND gate. Then we say NOR gate. NOR gate is simply, listen to me very carefully. NOR gate is simply
the combination of OR plus NOT. It is the combination of OR plus NOT. When OR gate is added with NOT gate, it becomes what? NOT gate. It becomes NOT gate. Now let me tell you what is the output. Let's suppose A and B are the inputs. What is the work of OR gate? Its job is to add. It will do A plus B. Then you connect a NOT. What is the work of NOT? To apply the bar inverse. So we say it will be A plus B bar. This is input for this gate and it will be A plus B bar. So finally, its symbol we can write something like this. This one, and then we say this one. And instead of whole NOT, we'll take only this ball and place it over here. So this ball, this will be the symbol of, we say, NOR gate. Okay. And in this case, Boolean expression, final result will be y is equal to A plus B bar. Y is equal to A plus B bar. And if we talk about the truth table, see, if A is 0, B is 0. Y is equal to A plus B is 0 plus 0 is 0. This is OR. And then finally NOR. NOR means Y is equal to A plus B bar. So that is 0 bar is, we say, sir, 1. Then A is 0, B is 1. Now see, 0 plus 1 is, we say, sir, 1. And what is the bar of that? That is 0. 1 plus 0 is 1. So bar of that is 0. 1 plus 1 is 1, bar of that is 0. Okay, you can see it over here. Okay. In this case, you can see, sir, when both the inputs are low, output is high. You can clearly see over here, when both the inputs are low, output is high. When any of the two inputs is high, any of the two inputs is high. See, 1, 1, 1. Output is low. Output is 0, 0, 0. Hey guys, are you able to understand this? This is very simple, extremely simple. Tell me in the chats if this is crystal and clear. Tell me in the chats. Electrical equivalent circuit of NOR gate. This is the electrical equivalent circuit of NOR gate. See, we have got a battery over here, then we apply this key 1, key 2, and then we have got the bulb. Now see, if we make the truth table over here, let me make the truth table here. This is K1, this is K2, this is bulb. Let's suppose the current will leave from this, okay? If K1 is on, K2 is off. Let's keep this K1 on. We say, sir, current will flow through this and it will pass through this. It will not enter the bulb. Why would the current flow through that path in which resistance is present? So if you are saying that I am closing this switch, means I am connecting this switch. So current will flow through this path and will go over. This will be the loop. Okay. So bulb in that case will remain off. Okay. That is 0. Now, if you keep this on, then current can flow through this path. So if this is off, this is on, this will be off. If both are on, bulb is off. If both are off, this is off, then the current has to flow through this path. Then it will be on. This is exactly like the truth table of NOR gate. NAND gate. What is NAND? NAND, we simply say it is basically the combination of AND plus NOT. It is combination of AND plus NOT. If you have got the AND gate over here, if you add it with, we say, sir, NOT gate, it becomes NAND gate, NAND gate. Its symbol is directly this. This is a straight over here. And then put the ball
So it's Boolean expression. Boolean expression is, we say y is equal to AB bar. Y is equal to AB bar. Truth table will be simply 0, 0. 0 into 0 is 0. 0 into 0 is 0. 0 bar is 1. 0 bar is 1. 1, 0 into 1 is 0. 0 bar is 1. 1 into 0 is 0. 0 bar is 1. 1 into 1 is 1. 1 bar is, we say, 0. Okay. And in this case, you can clearly see when both the inputs are high, output is low. When both the inputs are high, output is low. Okay. And when any of the inputs is low, 0, 0, 0, output is high. When any of the two inputs is low, output is high. Output is high. This is the electrical equivalent circuit of NAND gate. Let's make the truth table for this one. This is K1, this is K2, and this is bulb. Let's suppose, my dear friends, if you keep the K1 on, K2 off, we say still current cannot flow through this path. Current has to flow through the bulb. Bulb remains on. If this is off, this is on, still current cannot flow through this branch. Current has to flow through this path, on. If both are off, 0, 0, bulb is on. If both are on, bulb in that case will be off. If this is on, current will flow through this path in this loop. So it will not enter the bulb. Bulb remains off. Okay, okay. Now there are some questions. This was the question which was asked in NEET 2019. I want you guys to answer this particular question. See, you guys have to tell me in this particular case, this is the electrical equivalent circuit of which gate? This is the electrical equivalent circuit of which gate? How do you solve this particular question? Just simply make the truth table. You'll get the answer. That's it. There is no other shortcut. Just make the truth table, you'll get the answer. That's it. See, if I say, sir, this is the higher potential plus 6 volts. Okay. I hope this is visible. This is plus 6 volts. So current will flow from higher potential. If I say this is K1 and this is K2, this is K1, this is K2, and this is bulb. If I keep the K1 on, so here you have the bulb. Bulb has resistance, one more resistance. Why would the current won't flow through this path? Okay. It will flow through the path where there is no resistance. If we keep the K1 on and we keep the K2 off, current will flow. Here it cannot flow because it is off. So current has to flow through the bulb. Bulb remains on. If this is off, bulb is on. What will happen? K2 is off. What will happen to the bulb? Bulb remains on because current cannot flow through this path. If K1 is off, K2 is off, bulb is on. If K1 is on, K2 is on, bulb is off, then current will flow through this path and reaches over here. So this is the truth table of which gate? Tell me, guys. This is the truth table of which gate? Tell me, guys. This is the truth table of which gate? Don't you think this is the truth table of NAND gate? 0, 0, 1. Or you can look at this statement also. When both the inputs are high, output is low. When any of the two inputs is low, output is high. See? When both the inputs are high, output is low. When any of the two inputs is low, output is high. This is NAND. This is the technique by which you can solve this question. Next. This was asked in NEET 2019. Which gate is this? Which gate is this? I hope this is visible. I hope this is visible. This is bulb. This is K1. This is K2. This is resistance. Now this is also resistance. This is plus 6 volts. Current will flow from higher potential. Okay. The answer of this is, we say, sir, NOR. But you have to solve this from your end. You have to solve this from your end. Okay. This is your homework. This is what I'm giving you as the homework. Okay. You have to make the truth table. From the truth table, you'll get to know. Then we have this question. What is the output of this particular question? What is the output? In the combination of the following gates, the output Y can be written in terms of A and B. Okay, okay. What is the output over here we are saying? See, this is A, this is A. This output A will go over here. This output B. This is not gate, so it will be B bar. It will make B to B bar. Okay. Then this A will go directly over here. So this NOT gate will make it A bar. And this B will go directly over here. This will be B. Now, which gate is this? Could you please tell me which gate is this over here? Everybody in the chats. Everybody in the chats. Okay. Okay. What is this symbol? See, I have told you. I have told you over here. I have told you over here. This is AND gate. Symbol of AND gate. What is the job of AND gate? To multiply A dot B. So it will multiply, that is A dot B. Multiply A dot B. Okay. So input is A, input is B bar, A, B bar. Okay. And then you have, this will be A bar, and then this is B. And then which gate is this? Which gate is this? What is the job of this particular gate? Its job is to, we say, add. We say add. So it is OR gate. It is OR gate. Come over here. Come over here. I will show you OR gate. Now see, the job of OR gate is to basically add Y is equal to A plus B. Y is equal to A plus B. So what I will do in this case is, so final output will be, see, this input will go in this. This input will go in this. So it will be A B bar plus A bar A. This will be the final. This is the last question of the session, and this I am giving you as homework. Comment down the answer of this one. Comment down the answer of this one. Thank you so much, people. If you have still not liked this session, like it right now. Okay. And I want you guys to comment down below once I end this session. How was the session? Each and everything. Okay. Let me know. Okay. We keep on reading your comments every single time, and that gives us more energy. Okay. And I would personally reply to your comments this time. That's for sure. Okay. So do comment. Thank you so much. This is done your marathon second part 2 of the complete physics 12th. Okay. Okay. Let's now focus on the 11th portion afterwards. Now it will be 11th part 1. Next marathon will be 11th part 1. Okay. So do comment down below afterwards. I want everybody of you to basically do that because that's mandatory. Okay.
Okay, guys. Okay. Let me know. Let me know in the chats. Hmm? Somebody is saying, please show these questions. Okay. Okay, I will show you. Okay. Just see. If we talk about this particular question over here, see, it is very simple, guys. It is very simple. It is very simple. Let's make the truth table over here. Let's make the truth table over here. If I say, if I say, if I say, I have got K1, I have got K2, and this is bulb over here. This is bulb over here. Okay. Now see. If I say the current is flowing from this point, the current is flowing from this point, plus 6 volts. Okay. So we say, if we keep the K1 on, let's keep the K1 on. Okay. Let's keep the K2 off. What will happen? What will happen? Tell me. Sir, if we keep the K1 on, okay, if we keep the K1 on, so we say in that particular case, we say the current will flow through this path and will reach over here. Because current flows from higher potential to lower potential. This is grounded over here, 0 volts. So this will be the path. In this case, has the current gone through the bulb? No, sir. So we say over here, bulb in this case will remain off. Bulb in this case will remain off. I can simply say this will remain off. Let's keep this on and this off. Let's see what is going to happen in this particular case. We say, sir, if we keep this on and this off, remove this now. If we keep this on and this off. Okay. Now what we are going to do in this particular case is, we will keep this on, open it, and then connect this. We say current will flow through this. Now here it is bulb, so and resistance. Current would not want to flow through this path because you have got 2 resistances. So current will prefer this path and will reach over here. In this case also, I can say bulb will remain off. In this case also, I would say bulb will remain off. Now, next point I must say in this particular case, what is that? What is that? If this current flow, let's suppose, what we are doing next is that, let's keep both off. Okay. If we keep this off and this off, in that case, current has to flow through this path. Current has to flow through this path and reach over here. So we say in this case, bulb remains on. Now, if we keep this on and this on, what will happen? We say, sir, if we keep this on, then once again the current will flow through this path and this path. So it does not enter the bulb. So bulb remains off. So bulb in this case remains off. Okay. Now, can you see in this particular case? See, when both the inputs are low, output is high. When both the inputs are low, output is high. Okay. And when any of the two inputs is high, output is low. Now, which is matching? It is matching with, let's move on to the NAND. Let's move on to the NOR. See, let's move on to the NOR. When both the inputs are low, output is high. Okay. When both the inputs are low, output is high. When any of the two inputs is high, output is low. Or you can compare the truth table directly. We say NOR gate. You'll say simply this is NOR gate. You'll say simply this is NOR gate. Okay. And the last one in this particular case is, so I will write over here. Yeah, this one. What is the answer of this question? The answer of this question is simply, see, what is the output Y in the following circuit when all the 3 inputs A, B, C are first 0 and then 1? Okay. This is a question that we have exactly on the screen. Tell me which option I need to go for over here. Which option? See. This is we say AND gate. We say this is AND. Okay.
And this is we say sir NAND. This is we say sir NAND. This is we say NAND. Let's suppose if we are sending A and B, what is the work of this? It will say A into B. It will say A into B. The work of AND gate is to multiply A dot B. The output of this will be A dot B. And then this is C. What is the output of this NAND? Sir, it will first multiply A dot B dot C and then it will put the bar. This is the common. Simple question. Sir, what is the work of NAND gate? See, come over here. Sir, the work of NAND gate is, sir, it will multiply first, then put the bar. It will multiply first, then put the bar. Okay, it will multiply first, then put the bar. Now, in the question, it is saying that if what is the output Y in the following circuit when all the three ABC are first 0 and then 1? Okay. If we place first ABC as 0, if A, B, C is equal to 0, okay, then what is the output Y? See, output will be, sir, this is bar A, B, C bar. So it will be bar of A is 0, 0, 0. 0 into 0 into 0 is 0. 0 bar, that is 1. Okay, output is 1. And if it says, if all the three inputs are then 1, if all the three inputs are 1, A, B, C is equal to 1, we say output in that case will be bar of A, B, C. So we say this will be bar of 1, 1, 1, 1, 1, 1 into 1 into 1 is 1. So that is 1 bar, that is 0. So we say output in that case will be Y is 1, 0. So that is option D. So if you place A, B, C 0 first, then place 1 afterwards, output will be 1, 0. Option D. Okay. Now it is done and dusted. Happy? Now is it done and dusted? Everything? Okay. Let me save these slides first, okay? Then we'll talk. Okay. So guys, I want everyone to basically, I'm ending the live stream, okay? I want everyone to tell me in the chats how was this session, okay? Do let me know over there, okay? And everything. Full-heartedly comment over there. And most importantly, because we keep on reading those comments every single time, this gives us energy. This gives us more and more josh, okay? So that we can come up with the more sessions like this. This is covered now. Tell me. Okay. So, okay. Tomorrow we are traveling to Bangalore, so I won't be able to take the session tomorrow for this problem solving session, okay? Okay. Cool. Thank you. Why are you not replying to my comment? What comment have you, what have you asked, bro? I'll reply to that. No, that the problem solving session which is scheduled on 9th, that I'll take on 9th only, okay? Yes.
Miss you for next 4 days. Miss you too. And guys, if you have not liked the session yet, do like the session as soon as possible. No, no, no. That XOR and X, leave those. Okay, leave those. Through this session, we can get 100 marks. If you follow both of the sessions like part 1 and part 2, definitely you'll get a good score. Okay, that depends. If you solo practice more and more problems from your end, definitely you'll get. Okay. Yes, 12th physics done and dusted. Yes, EM waves is there. That's a small topic, bro. Not that big one. Okay, 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 okay. Wasim sir will take the next marathon very soon, huh? He will take, he will take. Don't worry about that. Okay, guys. If you take the logic gates lecture, we are already done with the logic gates, huh? What was this? These are the logic gates, huh? And, nor, and. Yeah. Good night, good night, good night. So, guys, make sure you comment afterwards. So, I'll be waiting for your comments, okay? So, thank you so much. This was all about it. Take care and bye bye. Okay, see you guys very soon. Okay. Yeah. And do share this session with all of your friends, okay? And stay updated. So for next few days, we're traveling to the Bangalore. Let's see what's gonna happen over there. Okay. And we'll meet after 5 to 6 days. Okay. Then we'll continue with our marathon journey. So next we'll be starting with the 11th part 1. Okay. We'll start those chapters with the units and dimensions itself. We'll be solving all those problems which are over there. Okay, so right now I am ending this live stream. Take care and bye bye. Take care and bye bye. So I want everybody of you to basically comment down below afterwards. Okay. So thank you so much. Take care. And those students who have not liked this session yet, like it as soon as possible because liking this session is mandatory. Take care. Bye bye. See you guys very soon. Take care.